Oh gosh, oh my mic's being weird to me again. I have no idea why. It could be because I turned the volume down a little bit too much, who knows. Anyway, today I don't feel like doing anything. No, 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 no. I just wanna lay in my bed. Na, 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 na. Feel the message at the dawn. 'Cause today I swear I'm not doing anything. Nothing at all. Nothing at all. No, 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 and stare at the fan, turn the TV on, put hands in pants. This is what I drew yesterday. 'Cause nobody's gonna tell me I can't. Oh, yes, I said it. I said it 'cause I can. Alright, so it's been a long day without you, my friend. I drew this yesterday, and I kind of used a different way of drawing. I use a different brush too. The brush might seem like a different the brush I used to use, but it's different, guys. It has a little bit of size dynamic to it, and I think it kind of worked. Who knows? I don't know. Nothing at all. Why did you make him so big? It's for, like I said, I was testing. Okay, today I wanna make a meme out of a random music that I found from a good old games. Pentagon. I'll leave this here. I don't know if you know what this is. I think you guys should know. Okay, it's this part right here. That's a bit loud, isn't it? I'm sorry, guys. Oh gee. I wanna do something with this damn sound. I don't know. You know, so I can just copy this, go up here, and Y3 or Y2. I don't know. YouTube to MP3. Hello, Barry. Barry. What a good guy. What do you mean? Shopee? No. Download. Alright, we got that. And we'll go on to Toon Squid.
Understanding how the data is stored in the computer's memory, you'll be able to apply your own Instagram-like filters to make things grayscale instead, or sepia in this case. You can even flip the bits around so that the thing is a mirror image. You can blur things further, or if you really are feeling more comfortable, you can even write code that finds the edges of the image and creates works of art like these. So all that and more in problem set 4. We will see you next time.
What am I watching? Some educational stuff, you know. Me wanna learn computer science, so this is what I watch. I've watched like 11 hours out of like 24 hours of this damn videos. Data structures isn't denying the Gunner allegation. This means he's a goon. Everyone's a gooner. You know, you a gooner. Everyone is.
All right,
in this day and age, everyone is.
Week 5, which is going to be our last week in C. But what that means is that we'll have But with this week, with last week, and really all of the weeks prior, have you been hopefully acquiring, if slowly and with some challenge, like some fundamental building blocks that are still going to underlie everything we continue doing in the semester, even as we transition to so-called higher level languages. Next week, indeed, we'll introduce Python, a very popular language that does not have pointers, does not have memory management at this very low level, but that's really just because someone else wrote the code that will do that for you, and it's going to make our lives easier because it means when you want to solve a problem conceptually up here to just get real work done or build something amazing, you don't have to really get into the same weeds as we have been deliberately this week and now last. But the goal ultimately is that you better understand and can better harness then all that a computer can do, even in those higher level languages. So today we're going to focus particularly on data structures, how you might structure your
What am I eating?
memory, which really amounts to building.
You got 700 views? Damn, that's cool.
Ideas and concepts in memory using this new building block from last week, which of course are these pointers. Pointers allow you to store addresses in memory, like in variables. But with those simple addresses, we can
Okay, sorry guys, you guys might have to learn what I'm learning right now. Learn with me.
But there's going to be different ways of doing that, and today we'll focus first on what's generally known as an abstract data type. And similar to a type in C more generally,
yeah, I'm just gonna do my own things here, and then I'm gonna watch this.
Details of an abstract data type are ultimately up to you. That is to say, an abstract data type can represent one thing and can do something, but how you implement
See you at 4 p.m. Oh, okay. Bye-bye.
So for instance, in the world of computer science, a queue is actually a technical term. This is a type of data structure that we could theoretically build in code in C or really any other language, but a queue has properties just like queues in the real world. For instance, if you've ever lined up for something to get food in a restaurant, or go into a store, or wait for the airport to clear you, well, you've lined up in a queue. A queue being some sort of line. But what's noteworthy about queues are specific properties. They are first in, first out data structures, either virtually or in the human world, which is to say, the first person in the line.
Can you add Subway? No, we're gonna watch this instead.
The first person in the line should get through airport security first. By contrast, if it weren't first in, first out, you can imagine how frustrated you would be if you have this sort of inherent unfairness. In fact, if you've ever been in line at a store, a supermarket, or the like, and all of a sudden they maybe open a new line, and now the person behind you gets to kind of cut ahead and go forward, that's because they've broken the concept of the queue. So it has this inherent potential for unfairness unless you maintain this first in, first out property. This would be true too for like a to-do list, just for productivity.
First come, first served.
If you're going to have it on paper or virtually making a to-do list, ideally you probably want to go through that list top to bottom so that you actually get the first stuff you thought of done first, rather than always focusing on your most recent thought. Now, within the world of queues, there's generally two operations, two functions, if you will, that any queue would have, either in the real world or in the virtual. Enqueue is usually the technical term to mean adding something to a queue, but specifically it means adding it to the end of the queue so that someone isn't cutting in line, for instance, to go up front. And then dequeue is just the opposite. When it's time for the first person in line to be served, the time for the first person in line to go through security, they are dequeued, so to speak. So a technical concept ultimately as it's implemented in code, but it's really just a real world concept. And these are in contrast to another abstract data type that we might call a stack. And a stack, much like a stack of trays in the cafeteria, has sort of fundamentally different properties. You can still add and remove things from them, but consider what happens whenever they clean all of the trays in the cafeteria or the dining hall. They put one of the trays down here, and then the next one on top of it, and then the next one on top of it, and so forth. But of course, which tray do you presumably take as a user of that physical stack? The top one, presumably, right? Like, you're not going to futz down here and try to pull one out. And so that would seem to have an opposite property. LIFO, last in, first out, is what characterizes something like a stack. And that just makes sense, certainly in the physical world, of stacking all of those cafeteria trays, because it just makes more sense to grab the most recently added one, the last added one, first. And at least in that context, the trays don't necessarily care what order they're used in. But even then, you could imagine that maybe there's some old, dirty, nasty tray at the very bottom that like never gets used because you're constantly replenishing the stack. So there might very well be side effects of these kinds of features. You might be familiar with using Gmail, for instance, or really any email program. What you're looking at in your inbox is technically a stack, at least if you've left the defaults configured. Why? You get a new email, where does it end up? Not like 5 pages of emails later, presumably right at the top, and the next one's right at the top, right at the top, right at the top. And so if you're like me, you're guilty of eventually losing track of some emails. Why? Because you've pushed so many more emails onto the stack that you sort of lose track of the things you got earliest. Last in, first out, though, is maintained. The most recent email you get might very well be the first one you reply to, but that's not necessarily good for responsiveness to everyone else out there. Similarly, if you store like all of your sweaters in a stack like this, like a pile of black ones below which is a red and then a blue, stack might be perfectly fine for keeping things organized. It's sort of the sane way to do it if you just have a shelf in your dorm room or home. But what's going to be a side effect of using a stack to store your sweaters if they're these in this way, as opposed to a queue? Yeah. It's harder to get the red and blue ones. So presumably, you're going to much more often wear, for instance, if you will, black instead there. Now, the operations for adding things to a stack are similar in spirit, but just different vocabulary. You push something on top of a stack, even though it's more like in the tray world, you sort of place it or rest it. But pushing means adding something to the top of the stack. Also from the top of the stack. So it's not a matter of enqueuing at the end and dequeuing at the beginning. With a stack, everything's happening on top. You're pushing onto the top and then popping off of the top. Now, when it comes to actual code, how might...
My mom's calling me. Hello.
Con lấy nha cái photo của cô Phước rồi cô Phước đang đứng ngoài trước con đưa em mẹ nha.
Yeah. I don't know what's going on with my mic, but it's always turning off for some reason. I don't know why it does that. Maybe it ran off battery, but my mic doesn't use battery. Application for application to Google database. Continue running when on battery. No. Use this device. Property. Drivers is all normal. Alright. Anyway, I think we're good. That's wild. What do you mean?
We implement something like this. Well, let's just focus on really how you might implement the data structure itself, and we won't implement any functions. You might implement the notion of a stack like this. We've seen type def before. It just means define a new type of my own. Struct means here comes a structure, aka a data structure of popping
Wait.
as opposed to a queue. Yeah. It's harder to get the red and blue one. So presumably, you're going to much more often wear, for instance, if you will, black instead there. Now, the operations for adding things to a stack are similar in spirit, but just different vocabulary. You push something on top of a stack, even though it's more like in the tray world, you sort of place it or rest it. But pushing means adding something to the top of the stack, and popping means removing something also from the top of the stack. So it's not a matter of queuing at the end and dequeuing at the beginning with a stack. Everything's happening on top. You're pushing onto the top and then popping off of the top. Now, when it comes to actual code, how might we implement something like this? Well, let's just focus on really how you might implement the data structure itself, and we won't implement any functions. You might implement the notion of a stack like this. We've seen typedef before. It just means define a new type of my own. Struct means here comes a structure, aka a data structure of one or more variables within. And let's suppose, like last time we've defined already like a person data type using a separate typedef, and every person has like a name and a number or whatever. We just stipulate that person exists already. So here you might have to implement a stack, an array called
Recursive.
of some capacity. Maybe it's an array of type 10 or 100 or whatever. This is a constant here in this context, capacity. And every element in that array is a person structure. And I now have this too, size. Now this almost seems like a synonym for capacity, but maybe intuitively, anyone want to propose why I'm apparently maintaining separately the capacity of the stack, but also the size of the stack? Why these two distinctions here? Yeah.
The capacity is the maximum one.
Yeah. Perfect. The capacity is how high the stack could be, like how much room is there for those sweatshirts in my closet, for instance, whereas size is just literally at this moment in time how many sweatshirts are in the stack. It's either capacity or fewer, presumably, in total there. So what is capacity? Well, we could implement this in, perhaps a familiar way. I might just define a const somewhere else in my code, a type int, that just defines it to be capacity 50. But what perhaps is going to be the downside of implementing a stack in this way, of using an array inside here? What's the downside now of implementing a stack using an array and this size variable within? What's a caveat here, perhaps?
Array can store data.
Okay, so it's going to be harder to reach elements that aren't the last one. That is the most recently added one. So there could be some structure, so to speak, way down below. So we've seen that before too. But at some point too, a limitation of this design is what it's going to be finite, right? I can maximally fit in this example 50 sweatshirts or 50 emails or 50 cafeteria trays, which is fine, but at least it's indeed finite. And at least in the computer's memory, it might be nice to use more and more and more, maybe as more things are getting added to the computer. So maybe I make this 500, or heck, why don't I make it 5,000 or 50,000? Well, what's the trade-off there? If I want to have enough room to grow, it seems like I should just crank up the value of capacity endlessly. But why might I not want to change the 50 to 500 or 5,000 or 50,000? What's the trade-off there, perhaps, just intuitively? Yeah. Okay, you don't want to touch memory that you're not supposed to be touching. And in this case, that wouldn't be a risk per se unless you indeed overflow the stack. But there's a related issue in asking for that much memory. What would another downside be?
Segmentation faults. Have you seen Minecraft movie? No, I haven't.
Yeah, okay, exactly. So if you've got a capacity of 5,000, but you're only using one of those elements, it's awkward to say it non-technically, which is just to say very, very wasteful, right? That's just bad design. It's correct. It will work for up to 5,000 elements, but my gosh, you're wasting 4,999 extra spots, and that's not going to end well, especially if you're using more data structures in memory, like your Mac, your PC, your phone is surely going to run out of memory if you ask for that much. So it'd be nice if there was a bit more dynamism there, whether it's a stack or a queue, both of which might be implemented a little similarly in spirit, but let's conclude this abstraction by comparing.
Do I like Mickey Mouse? I have no idea. Wait, I'm kind of confused about what he said about using this and array. Why do we use this instead of the array?
This context, capacity, and every data things happening on the structure. Type def before just means define a new type of my own. Struct means here comes a structure, aka a data structure of one or more variables within. And let's suppose like last time we defined already like a person data type using a separate type def, and every person has like a name and a number or whatever. We just stipulate that person exists already. So here you might have to implement a stack, an array called people of some capacity. Maybe it's an array of size 10 or 100 or whatever. This is a constant here in this context, capacity. And every element in that array is a person structure. And I now have this too, size. Now this almost seems like a synonym for capacity, but maybe intuitively, anyone want to propose why I'm apparently maintaining separately the capacity of the stack, but also the size of the stack? Why those two distinctions here?
Lights out after 12 p.m. Supply drops are handed out every Sunday. Absolutely no guests at the lookout. System master with iron bar, refuel the generator routine.
Perfect. The capacity is how high the stack could be, like how much room is there for those sweatshirts in my closet, for instance, whereas size is just literally at this moment in time how many sweatshirts are in the stack. It's either capacity or fewer, presumably, in total there. So what is capacity? Well, we could implement this in, perhaps a familiar way. I might just define a const somewhere else in my code, type in,
person.
and just define this to be capacity 50. But
Alright then, so in this data type, there will be like the array of person and in size, I don't know.
What is going to be the downside of implementing a stack in this way? Of using an array inside here? Like what's a downside now?
Drinking chips, drinking fucking study while drawing. Oh, my thing crashed.
What's a caveat here, perhaps? Any hands? Yeah. Okay, so it's going to be harder to reach elements that aren't the last one. That is the most recently added one. So there could be some sweatshirts, so to speak, way down below. So we've seen that before too. But at some point too, a limitation of this design is what it's going to be finite, right? I can maximally fit in this example 50 sweatshirts or 50 emails or 50 cafeteria trays, which is fine, but at least it's indeed finite. And at least in the computer's memory, it might be nice to use more and more and more, maybe as more things are getting added to the computer. So maybe I make this 500, or heck, why don't I make it 5,000 or 50,000? Well, what's the trade-off there? If I want to have enough room after they clean all the trays in the cafeteria or the dining hall, they put one of the trays
Why
down
do I
here,
keep
and the
hearing
next one
memes
on
in the
top of it, and
background?
the
It's
next
my
one on top of it,
sister's
and so
PC.
forth. But of course, which tray do you presumably take as a user of that physical stack?
I don't know why.
The top
But yeah,
one,
let me try to
presumably,
fix
right?
it,
Like
don't
you're gonna
worry.
flex down here and try to pull one out, and so that would seem to have an opposite property. LIFO, last in, first out, is what characterizes something like a stack. And that just makes sense, certainly in the physical world, of stacking all of those cafeteria trays, because it just makes more sense to grab the most recently added one, the last added one, first. And at least in that context, the trays don't necessarily care what order they're used in. But even then, you could imagine that maybe there's some old, dirty, nasty tray at the very bottom that like never gets used because you're constantly replenishing the stack. So there might very well be side effects of these kinds of features. You might be familiar with using Gmail, for instance, or really any email program. What you're looking at in your inbox is technically a stack, at least if you've left the defaults configured. Why? You get a new email, where does it end up? Not like 5 pages of emails later, presumably right at the top, and the next one right at the top, right at the top, right at the top. And so if you're like me, you're guilty of eventually losing track of some emails. Why? Because you've pushed so many more emails onto the stack that you sort of lose track of the things you got earliest. Last in, first out, though, is maintained. The most recent email you get might very well be the first one you reply to, but that's not necessarily good for responsiveness to everyone else out there. Similarly, if you store like all of your sweaters in a stack like this, like a pile of black ones below which is a red and then a blue, stack might be perfectly fine for
Flaccid first out.
It's sort of the same way to do it if you just have a shelf in your dorm room or home. But what's going to be a side effect of using a stack to store your sweaters if they're these in this way, as opposed to a queue? Yeah. It's harder to get the red and blue ones. So presumably, you're going to much more often wear, for instance, if you will, black instead there. Now, the operations for adding things to a stack are similar in spirit, but just different vocabulary. You push something on top of a stack, even though it's more like in the tray world, you sort of place it or rest it. But pushing means adding something to the top of the stack, and popping means removing something also from the top of the stack. So it's not a matter of enqueuing at the end and dequeuing at the beginning. With a stack, everything's happening on top. You're pushing onto the top and then popping off of the top. Now, when it comes to actual code, how might we implement something like this? Well, let's just focus on really how you might implement the data structure itself, and we won't implement any functions. You might implement the notion of a stack like this. We've seen typedef before. It just means define a new type of my own. Struct means here comes a structure, aka a data structure of one or more variables within. And let's suppose, like last time, we defined already like a person data type using a separate typedef, and every person has like a name and a number or whatever. Let me just stipulate that person exists already. So here you might have, to implement a stack, an array called people of some capacity. Maybe it's an array of size 10.
Huh? People, okay.
Or 100 or whatever. This is a constant here in this context, capacity. And every element in that array is a person structure. And I now have this too, size. Now this almost seems like a synonym for capacity, but maybe intuitively, anyone want to propose why I'm apparently maintaining separately the capacity of the stack, but also the size of the stack? Why these two distinctions here? Yeah. Yeah. Perfect. The capacity is how high the stack could be, like how much room is there for those sweatshirts in my closet, for instance, whereas size is just literally at this moment in time how many sweatshirts are in the stack. It's either capacity or fewer, presumably, in total there. So what is capacity? Well, we could implement this in, perhaps a familiar way. I might just define a const somewhere else in my code of type int that just defines it to be capacity 50. But what perhaps is going to be the downside of implementing a stack in this way, of using an array inside here? Like, what's a downside now of implementing a stack using an array?
What is he using? He's using C. He's using C. The language
What's a
C.
caveat here, perhaps? Any hands? Yeah. OK, so it's going to be harder to reach elements that aren't the last one. That is the most recently added one. So there could be some sweatshirts, so to speak, way down below. So we've seen that before, too. But at some point, too, a limitation of this design is what it's going to be finite, right? I can maximally fit, in this example, 50 sweatshirts or 50 emails or 50 cafeteria trays, which is fine. But at least it's indeed finite. And at least in the computer's memory, it might be nice to use more and more and more, maybe as more things are getting added to the computer. So maybe I make this 500, or heck, why don't I make it 5,000 or 50,000? Well, what's the trade-off there? If I want to have enough room to grow, it seems like I should just crank up the value of capacity endlessly. But why might I not want to change the 50 to 500 or 5,000 or 50,000? What's the trade-off there, perhaps, just intuitively? Yeah.
70 knots. 70 knots.
OK, you don't want to touch memory that you're not supposed to be touching. And in this case, that wouldn't be a risk per se, unless you indeed overflow the stack. But there's a related issue in asking
really
for
used
that much memory. What would another downside be?
I don't know what Brick's onto, man.
Yeah, OK, exactly. So if you've got a capacity of 5,000, but you're only using one of those elements, it's awkward, to say it non-technically, which is just to say very, very wasteful, right? That's just bad design. It's correct. It will work for up to 5,000 elements. But my gosh, you're wasting 4,999 extra spots. And that's not going to end well, especially if you're using more data structures in memory. Like your Mac, your PC, your phone is surely going to run out of memory if you ask for that much. So it'd be nice if there was a bit more dynamism there, whether it's a stack or a queue, both of which might be implemented a little similarly in spirit. But let's conclude this abstraction by comparing, thanks to a friend of ours, Professor Shannon Duvall of Elon University, who kindly put together this graphical animation that's just under 2 minutes long that paints a picture of these two types of abstract data structures. And then we'll dive in underneath to how we might implement problems like these. If we could dim the lights dramatically.
Jack learns the fact about queues and stacks.
Once upon a time, there was a guy named Jack.
Okay,
When it came
Jack.
to making friends, Jack did not have the knack. So Jack went to talk to the most popular guy he knew. He went up to Lou and asked, "What do I do?" Lou saw that his friend was really distressed. "Well," Lou began, "just look how you're dressed. Don't you have any clothes with a different look?" "Yes," said Jack, "I sure do. Come to my house and I'll show them to you." So they went off to Jack's, and Jack showed Lou the box, where he kept all his shirts and his pants and his socks. Lou said, "I see you have all your clothes in a pile. Why don't you wear some others once in a while?" Jack said, "Well, when I remove clothes and socks, I wash them and put them away in the box. Then comes the next morning, and up I hop. I go to the box and get my clothes off the top." Lou quickly realized the problem with Jack. He kept clothes, CDs, and books in a stack. When he reached for something to read or to wear, he chose the top book or underwear. Then when he was done, he would put it right back. Back it would go on top of the stack. "I know the solution," said a triumphant Lou. "You need to learn to start using a cue." Lou took Jack's clothes and hung them in the closet. And when he had emptied the box,
Why
he
does
just
it
tossed
rhyme?
Then he said, "Now, Jack, at the end of the day, put your clothes on the left when you put them away. Then tomorrow morning, when you see the sun shine, get your clothes on the right from the end of the line. Don't you see," said Lou, "it will be so nice. You'll wear everything once before you wear something twice." And with everything in cues in his closet and shelf, Jack started to feel quite sure of himself, all thanks to Lou and his wonderful cue.
Damn. Why does it have to rhyme
right.
though?
So that paints a picture of these two abstract data structures, but if we really were to dive underneath the hood, we could implement them in a number of different ways, but we really, I think, need some building blocks via which we could solve problems like those, and we'll see today, too, some others as well. So let's rewind back to week 2, where we introduced you to your very first data structure, that is an array. And an array, recall, was just a chunk of memory whereby elements were stored by design back to back to back. It's an array of contiguous memory specifically. So with an array, we could certainly store not just one thing, but 2 or 3 or even more. And so, for instance, if we treat my computer's memory as this sort of abstraction here, and pictured here are 3 bytes or some multiplication thereof, suppose we're storing in the computer's memory an array of size 3, storing the digits 1, 2, and 3. Well, remember that if we zoom out per last week, there's other stuff going on in memory. So even if we want to add another number to this array that we didn't think of when we first started the program, like the number 4, ideally we would put it right here next to it. Otherwise, it's no longer an array. So by definition, if we're using an array, it's got to end up right there after the 3. But what else is going on inside of your computer's memory? Well, assuming your program is of any length and you've got other variables, other functions, you've been running it for a while, there's a lot going on, and your memory is being used and reused. So for instance, somewhere in memory might be immediately adjacent to this, like hello, comma, world, \0, the null character, just because maybe you have another variable somewhere in there that is storing that particular string alongside your existing array of size 3. And all of these Oscar the Grouches here really just represent what we called last week garbage values. Like, there's obviously bits there because they don't disappear. They're always going to be inside of the computer somehow implemented, but we don't really know or care what they are. They're the remnants of those bytes having been used for other older variables, previous function calls, or the like. But the problem clearly here is that, OK, 1, 2, 3 is there, but the h is here. And unless I want to start taking a byte out of my string by overriding the h with a 4, like, we just can't fit it right there. And yet, even though there's Oscars all over the place, those are indeed garbage values. And therefore, we could use that space because it's technically unused. We just don't know or care what the values are. So where could I put 1, 2, 3, 4? Well, my gosh, like, I have all this memory down here that's unused. I could certainly change those garbage values to be 1, 2, 3, 4. But to do that, I might need to do a bit of work here, right? It's not just a matter of just saying boom and it happens. Now with C and with code, I'd have to do this a little more methodically. So let me abstract away everything else that's a distraction. Let me assume that there is indeed at least 4 bytes available for 4 numbers just down here, though we could have put them in a bunch of different spots. What's involved now in moving the 1, 2, 3 to this new chunk of memory so we can add the 4? Well, I think conceptually we're going to have to copy the 1 from old to new, copy the 2 from old to new, copy the 3 from old to new, and then ultimately we can get rid of the old memory. Those 3 original bytes could now look like Oscar the Grouch and just be garbage values for all intents and purposes. But now I have room for a 4th byte wherein I can put the number 4. So this is nice, but what's a downside of this approach? What's a downside of solving the problem in this way, where the problem at hand is just to grow the array, so to speak, to increase its size, to fit 1 or more numbers? Seems pretty straightforward, but yeah. It's a downside of solving the problem in this way, where the problem at hand is just to grow the array, so to speak, to increase its size, to fit 1 or more numbers. Seems pretty straightforward, but yeah. Okay, maybe it's out of order, but I think that's okay because the order is just matters that it's relative. So long it's still contiguous, back to back to back in a different chunk of memory, I think we're okay there. It's not like I changed it to 4, 3, 2, 1, but a reasonable hunch, yeah. Yeah, like I didn't really plan ahead here. Like if I have to add another number like 5 or anything else, well, I might have to jump through these hoops again. Maybe I get lucky and maybe there's space there, but not if I have other variables and other things going on. That too might be used at some point. Other thoughts? Yeah. Slow efficiency, why? Yeah, I mean, it's just inefficient. It's sort of bad design, arguably. Why? Because I had to copy all of my original work down here. And as you note, if I want to add a 5th number, I'm going to have to copy it again and again and again and do things n times again and again. Now, maybe that's necessary. We'll soon see for sure. But it feels like this is not going to end well, especially if the array isn't of size 3 or 4, but 300, 400. Your computer ends up spending so much time just spinning its wheels. I mean, honestly, better might be this. Like if this is my same array, physically incarnated now, 1, 2, 3. It's literally on the edge of the shelf, so there's no room for the number 4. You know, maybe where we could take this story is, well, let's just find room for the 4. Like let's just put the 4, for instance, over here, replacing some available garbage value, some spare byte over here. But now wait a minute. I've broken the definition of an array, right? I can't have 1, 2, 3 and then 4 over here. So maybe there could be a mechanism if I put this thing on again, where when you get to the end of the existing elements, maybe I just somehow digitally point to the 4th array. And maybe we can kind of stitch together all of these different values in memory so that if you follow the arrows, so to speak, we can reconstruct exactly what the order is, even without having to find or make room here or pick up all of these numbers and move all of them over there. So that's perhaps the direction in which we'll go here. So let's see how we might get to that spot as follows. Let me go ahead and open up, say, VS Code here. Let me open up a program called list.c in my terminal. And let me go ahead and whip up a relatively simple program that just demonstrates what we did back in week 2 when we introduced arrays as follows. Let me include standard io.h so we can print stuff out. Let me do int main void, no command line arguments for now. Let me give myself an array called list of size 3, and I'll just hard code it to keep it simple for lecture's sake, each of which is going to be an integer. And now just so we have some specifics to talk about, let me put it list bracket 0, the number 1, list bracket 1, the number 2, and list bracket 2, the number 3. So I'm just translating into code what we just had pictorially on the screen and also physically here with these numbers on the desk. Now let's just do something mildly useful for this. How about we do for int I gets 0, I is less than 3, I plus plus. Let's just print each of these numbers out just to make sure they're indeed in memory as I intended. So %i \n, comma I, and then a semicolon. And I think that's it for now. So nothing interesting, no problem solved just yet, just a proof of concept so that now when I clear my terminal and run make list, No apparent errors at the terminal. And so when I now do /list, I should see, hopefully, from left to right,
My
1,
mic,
2, 3.
my mic.
But of course, if I want to add a fourth number now, there's no mechanism for such, certainly in the code that I just wrote. I could go back in here and change this to a 4. I could go down here and change lists, bracket 3 equals 4. I could just manually change the code, recompile the code. But of course, that doesn't give me any additional runway for the 5th or 6th number. So let me try to take a different approach, drawing some inspiration from last week. If I want to allocate memory dynamically, maybe because I don't know when I wrote the program how many bytes I want, we have another function as of last week that does not require that you commit in advance to a certain number of bytes. Via what function can you just ask the operating system for a chunk of memory? OK, so malloc, to allocate memory. Now, an array is just a chunk of memory. And even though since week 2, we've been using this syntactic sugar, this convenience of just using square brackets and indexing into it, it's just making it easier to manipulate a chunk of memory that's contiguous, all together, back to back to back. So today, just like last week, we can take those sort of training wheels off and maybe be a little more deliberate in how we allocate memory. Let me go, for instance, and do this. Let me delete my contents of my main function here, go back into main, and let me propose now that I declare, for instance, how about my list no longer as an array, but as a pointer. So int star list, and I'm going to go ahead and initialize this to be, how about a chunk of 3 integers for now? So I'm still going to hard code it.
Oh
but I'm taking
no,
a step
pointers
forward, more
again.
dynamism for now. So let me allocate 3 times whatever the size is of an int, but it's usually going to be 4 bytes as we know. So this is really going to be 3 times 4 equals 12, but it's a little more dynamic. And now, what can I do down here? Well, this is just a chunk of memory. So I can do literally list bracket 0 equals 1, list bracket 1 equals 2, list bracket 2 equals 3, and voila, achieve the exact same effect. Because again, an array is just a chunk of contiguous memory. But malloc gives you any old chunk of contiguous memory, so you can rather treat one like the other here. Now, if you really want to be cool, you could do something like this instead. You could dereference the address in list and go there. You could go down here and dereference list plus 1 and go there. But honestly, no one really writes code like this. It's just too cryptic. It's a little too far over the line, at least for most people. And so I think the syntactic sugar, as I keep describing, is just the more user-friendly square bracket notation, does the exact same thing, figures out the pointer arithmetic, and puts each of these integers, well, don't go down here and code the exact same thing, figures out the pointer arithmetic.
Lists malloc. So we basically get 3 slots. Okay.
Puts each of these integers in the right chunks therein. Now, just to be super pedantic, let me make sure if something went wrong. So if list equals null, that means that something went wrong, like my computer is out of memory, which we should check for typically. So let me just immediately return 1, signaling anything other than 0, which means success typically, just to get out of this program because something's wrong. But now let me propose that I've had a, well, let's do this. For int I gets 0, I less than 3, I plus plus, though a better design would always be to use a const, but I'm just doing this for demonstration's sake. Let's print out each of these ints too, and just make sure I didn't mess anything up. And let me open my terminal window again. Let me do make list again. OK, implicitly declaring library function malloc with type void star something something, implicitly declaring is the operative words there. What did I mess up? Yeah, I forgot the header file in which malloc is declared. I remember now, OK, that's in standard lib.h, and it's fine to look stuff like that up if you forget. So let me include standard lib.h. Now, let me clear my terminal, run make list again. OK, now we're good, /list. And now, what did I do wrong? Oh, OK, not intended, but teachable moment. What did I do wrong? Yeah. OK, not intended. But teachable moment. What did I do wrong? Yeah. Yeah, I'm printing the values of I instead of what is at location I in the array. So what I actually meant to do was print this out, thank you. So now let me recompile, make list, /list, and now, OK, those are the 3 values I was expecting, not the indices thereof. Now let me propose that for the sake of discussion that I regret having only allocated space for 3 integers, and maybe I really should have allocated enough space for 4. Now this is not how you would do this in practice, because presumably if you have a change of thought, just go back in and correct the code. But let me propose that somewhere in here is a more complicated program and time passes, ... There's a lot of other interesting code there. But at some point, I might want to give myself more memory. So how can I do this? Well, let me just ask the operating system now for 4 new bytes of memory so that we can at least in version 1 implement the idea on the board where I just copied the 3 bytes into the new 4 bytes and then added a 4th value. So I'm going to use malloc again, and I'm going to say here's a new pointer. I'll call it temp. TMP for short, which is quite common when you just need it briefly. I'm going to then call malloc again. I'm going to say give me 4 integers using size of. Let me again make sure. So if temp equals null, something went wrong. So let me just immediately return 1. And for good measure, before I return 1, let me free the original list so that I don't leak memory. So I'm not just immediately returning 1. I'm being a good citizen and remembering, well, if this malloc call did succeed, and indeed I got as far as line 18, but then line 18 failed, I should free the memory that I previously mallocked. So again, that's the rule of thumb. If you allocate it, you should be the one to free it, even before you're about to quit. Now, once I've done that, I think I need to do what we did pictorially on the screen, where I need to copy the 1, the 2, the 3 from the old array into the new. So how might I do this? Well, let me give myself a loop. So for int I gets 0, I less than 3, I plus plus, because the size of the original is still the same. Let me go ahead and treat the new chunk of memory called temp as an array itself. And so I can absolutely use these square brackets just like before. It's just a chunk of memory. I'm treating it like an array. And let me add to that value whatever's at the original list at location I as well. So this, again, is just this exercise of copying from old to new, step by step, the 1, the 2, and the 3. But I still need one additional step if my goal at hand now is to have ultimately a 4th value here. Well, I'm just going to hard code this for demonstration's sake. And I'm going to go to the very last location of temp, which is of size 4, which means the last element in temp is temp bracket 3, because it's 0 indexed, but there's 4 total spaces there. And I'm just going to arbitrarily, for the sake of discussion, put the number 4 there. And that is what happened when we proposed.
Oh my gosh, why does my mic keep turning off?
Garbage value there to that 4.
I don't know if it's because of the PC or is it because of the mic itself.
On the screen, I should now do a couple
didn't do this stuff before, so I don't know why it happens.
Earlier in cases of error.
Submit,
just to be safe. I can now free the list. And now, if I want to inform the computer that I want list, quote unquote, my variable called list, to point at not the old chunk like it originally did, but the new chunk, I think I can just do this. List equals TMP. And again, that's just saying that if list is a pointer, which it was, look at the very top line here. On line 6, I declared list to be a pointer to a chunk of memory. Temp, meanwhile, is a separate pointer to a chunk of memory. So down here, this line 33 is just a matter of my saying, OK, now, henceforth, because I've already freed the old chunk of memory, my list variable should point not at this chunk of 3 bytes, but this chunk of 4 bytes, or really 12 in total now.
I think it could be because of my PC
now,
being weird.
Such bytes. Questions now on this code, the point of which was quite simply to demonstrate how we could implement in code this idea of fairly correctly but inefficiently allocating a new array of sufficient size and then populating it with a new 4th value. Questions on what we've just done here? No? Yeah.
Even if I have questions, I cannot ask because I'm not there in the room.
Good question. At this point in the story, with line 33, do I not have two different variables pointing at the same chunk of memory? Short answer, yes. But here's where the semantics are perhaps compelling. List is the variable that I intend to use longer term and keep around in memory. And again, assume that there's even more code going on here that we just didn't write yet. So it's useful to have that variable. Temp was just kind of a necessary evil because of...
Wait, hold on. Why? Okay, I know that we free lists. Oh, okay.
Here, it would not have been correct to do this. It would not have been correct to say list on line 18 equals the new chunk of memory, because this would have represented a memory leak. If I prematurely changed temp to point not at the old chunk but the new chunk, at that point, no one's pointing at the old chunk, and so I've lost those 3 bytes. Valgrind, for instance, would yell at you for having lost as many bytes in memory. So in this case here, I do leave this as temp. Yes, it's duplicative at this point, but it's not a huge deal if it was just meant semantically to be a temporary value. But down here, at the risk of one more line of code, I still want to be a good citizen, free list, and maybe just for good measure, return 0 explicitly. But notice, it's not doing it twice per se. On line 31, what am I freeing? The original address of list, the 3 integer version. Then I change what list points at. So it's pointing at a completely different chunk of memory, this one of size 4.
Okay, makes sense.
So eventually, when I'm all done using this memory for this demonstration, I still need to free list. But at this point in the story, line 40, it's pointing at the new chunk of memory, which I similarly need to hand back to the operating system by free. Yeah. When would temp equal null? So let me scroll back up slightly. This is being a good citizen and a good programmer. Whenever it comes to using malloc, malloc can return null if the computer's out of memory. So this is maybe a much bigger program. You've got other things going on in it. And so you just don't have enough memory available to be handed. Malloc needs to signal to you that there's some error. And so it will, by convention, per the documentation, per the manual pages, return null. So this is just me being a good citizen. Otherwise, here's another error that might cause your program to crash with a segmentation fault. If you get back null, but you assume that it's good memory, going to address 0, aka null, will crash your program intentionally. Yeah? Correct. If I were to change my final line 40 here to be free temp, this would also work as well. And here, this is really a matter of design. It's a very nitpicky thing. We could probably debate it. But because at this point in the story, my main variable for remembering where the list is called list, this is sort of the more responsible way to do it, freeing the list, just so that my colleagues, my TA doesn't sort of wonder, why are you freeing temporary memory that you already freed? Like, it just is a semantic thing at this point. But good instinct. It would also work, correct? Maybe just not good design. All right, so it turns out that this gets annoying quickly, as it did in the picture of doing all of this duplication. And even though technically it's necessary to copy those values if you need a newer, bigger chunk of memory, there is at least a function in C that simplifies a lot of this for us. And in fact, let me go ahead and do this. Instead of using malloc this second time on line 18, in addition to the first time I used it on line 6, I'm actually going to try and introduce another function called realloc, which, as the name suggests, tries to reallocate memory for you. And it works a little differently from malloc. Realloc expects 2 arguments. The first one is, what is the chunk of memory that you want to try to grow or shrink? That is, reallocate to be a different size. And then you specify what size you would want. And indeed, in this case, I want 4 times size of int. And that will now give me, hopefully, a new address of a chunk of memory that's big enough to fit all 4 numbers. But what's wonderful about realloc is that it will handle all of the copying for me. So in fact, I'm going to go down here. I'm going to get rid of all of this extra for loop. And what I'm simply going to do instead is this. Once I can trust, after lines 18 through 23, that realloc worked, and it didn't return null because I'm out of memory, I can just say, OK, just immediately remember that the new list points at this new chunk of memory instead. And then I can still now do this line, but I can tweak the semantics here and just say list bracket 3, the new final location in list bracket. And I can still now do this line, but I can tweak the semantics here and just say list bracket 3, the new. I don't need to free this here. I don't need to do this. All I need now at the bottom is the final for loop to just print out these values. So in short, even though that was somewhat quick, using realloc just moves the entire copying process that I implemented myself a moment ago using a for loop. It just moves it to realloc and lets it deal with the copying for me. It's no more efficient, but at least means I'm writing less code, which is more pleasant. And hopefully the people who wrote malloc or realloc are smarter than me, and they just will introduce bugs with lower probability too. All right, that was a lot. Any questions? Good question. Why do you still need to make list equal temp as I did on line 24? So ideally, I would do this. Ideally, I would just change this line 18 to be list. That is to say, or actually, even better, ideally, I would just say realloc this list to be of this new size. But again, things can go wrong when allocating memory. You need to check a return value to see if it was successful or not. And so we need to use a return value. OK, so let's not introduce temp. Let's just use list. But here's where a memory leak might happen. In the off chance realloc fails and doesn't have enough memory for your 4 bytes. Therefore, it returns by definition null. You can't overwrite the original value of list with null to then check it. Why? Because now who remembers where the original 3 bytes were? If you prematurely change the value of list, you've lost. You've leaked memory in that sense. And so that's why, let me undo this change, I declare a temporary pointer for the sole purpose of making sure I can check the return value. And then once it's good, now I'll update the value of list. So it's sort of doing a switcheroo by making sure first that you have a new value to swap with the old. Other questions on this code? Yeah? Indeed, realloc automatically frees the previous memory for you. And better yet, it's even smarter than that. If you get lucky and there happens to be space right after your existing chunk of memory, so 1, 2, 3 garbage value, instead of 1, 2, 3 hello world, realloc won't even bother copying things from old to new. It will just say, OK, I'm going to now reserve for you more bytes than you originally asked for, so it doesn't have to waste time doing that copying. And so in that sense, this version is now not only still correct, it's even better designed because we're not wasting time with that for loop. We might have to resort to it if there is, in fact, hello world or something else in the way, but hopefully we'll get lucky and save those steps. Other questions on this manipulation of code here? Yeah, in the middle. What if you want to resize a 2-dimensional array? So very similar in spirit, whereby you can use the same trickery. Let me wave my hand at that for now, just because I think that's going to sort of significantly increase the complexity, but very same primitives. Ultimately, a 2-dimensional array is essentially just a doubly long or quadratically longer list of memory that, using square bracket notation, is doing some of that mental math for you. But it's fundamentally no different of what's going on underneath the hood. All right. So with that said, and that code under our belt, even though that's not going to be something you'll frequently need to code yourself, let's propose now how we might go about building some actual data structures ourselves. The new ingredient here being this reality that if you want to resize a chunk of memory so as to make room for things, we now have that ability. Memory addresses and pointers just give us the ability to point around at things and move things around in memory. But now that we have malloc and even realloc, you can imagine maybe rewinding, and you could implement that stack, that queue, using not an array per se, because you have to commit to an array size in advance. But if you implement your stack or your queue using a pointer, and then malloc and realloc, and maybe someone else writes all that code for you, perhaps now you can imagine that, OK, now the stack can grow or shrink by using realloc accordingly. You don't have to preemptively say, give me 5 bytes or 50 or 500 or 5,000. You can say, just give me 1 initially. And if I need more, I'll realloc, realloc, realloc. And if you keep popping things off the stack, you can realloc in the other direction and ask for fewer and fewer bytes and the operating system can take that memory back as well. So we now have this building block. Let's see what we can do with it. So we've had a few pieces of syntax in recent weeks, all of which we're going to combine now in just a slightly more clever way. So struct is this keyword in C that lets us build our own structure in memory, like a collection of 2 or 3 or more variables, like a person that we've seen before. The dot operator, recall we've used when you do have a struct, like a person, and you want to go inside of it. So like person dot name or person dot number. We did this a few weeks ago now. But the dot operator just allows you to go inside of a structure and get the individual variables within. And then the star operator, unfortunately, has a lot of uses now. One was multiplication. My God, that was easy back in the day. Now it's used to declare pointers. It's also used to dereference pointers, so to make one exist and then go to that address. Unfortunately, it's the same symbol for all of those, but it's all related. But with these 3 symbols, it turns out you're going to get one last one today. And my God, it finally looks like the concept. It turns out there's a clever way anytime you want to use the dot and the star together. That is to go somewhere and go to an address and then look inside of a structure, you can actually literally use an arrow symbol on your keyboard. It's not a single keystroke. It's a hyphen and then an open angle bracket. But at least it looks like an arrow. And we'll see indeed in code today, the things I was drawing pictorially on the screen last time with yellow arrows, you can actually now express as well in code.
Wow.
And so here we have our next data
Yo,
structure
Spice
called a
Edit, what's
linked
up?
list. And this is one of the most useful, powerful concepts in C. It's the kind of thing that you can take for granted in Java and Python and higher level languages. But today we'll see how we or others can actually build these things just using these same primitives. So a linked list is going to allow us to actually do what we, used the foam finger for last week, allow us to link together, for instance, these 3 values, maybe with that 4th value over there. And then if there's a 5th, maybe this other foam finger points even farther over way to that 5th value. The key being that you can stitch together fancier data structures without having to pick all of these up and find new space. You just have to at least connect the dots somehow. We just need to somehow point from one to the other. And that's going to make things much more efficient, it would seem. So how do we get there? So here's my computer's memory as always. Suppose that I'm storing the value 1 somewhere in there, and it's at 0x123 address, whatever. And I'm storing the number 2 somewhere else in memory, 0x456, and number 3 at address 0x789. This is not an array by definition. Why? Even though it's the only 3 things on the screen, what makes this not an array? It's not contiguous. So this violates the definition of an array. But especially since they're sequential, it kind of looks to a human like a list. So it would be nice if there were a data type called list. And there isn't in C. There will be in Python. But you know what? If I could somehow stitch together these 3 values so I can get from one to the next, then I think we could achieve the idea, the concept of a list, without this really annoying constraint that they all be contiguous as in an array. So how do I do that? Well, at the end of the day, I only have memory at my disposal, right? There's no more training wheels to take off here. This is what we've got underneath the hood of a computer. So if all I have is memory, I think the solution to this problem of stitching together those values in a list must be to spend a bit more memory. That's literally the only resource we have right now. So let me propose that if we want to create a list conceptually out of 3 values that are in random, although pictorially pretty, positions in memory, let me just add a little bit more memory to the picture. So in addition to storing the 1, I'm going to leave myself some room, a little scratch pad, if you will, to use some other bits as well. Same for the 2, same for the 3. And you can perhaps see where this is going based on last week. If I want to somehow connect the 1 to the 2, any instincts as to what I should write in this box here that would lead me effectively from 1 to the 2? What could go here? Yeah. We could store the address of 2, and so specifically, what would you have me write here?
The address.
Perfect. Ideally, I would just put in this box another integer, one that happens to be represented in hexadecimal. but that's just a base system. It's just a human thing for us to look at. I'm going to put the value 0x456 here. So let me go ahead and reveal that. 0x456 goes there. You can perhaps see further where this is going. Well, if I want to get from the 2 to the 3, I think I need to put below the 2 the address of the 3, which gives me 0x789. Now, if 3
Can I
is
see
the
the
end
animation
of the list,
so far?
I don't
What?
want to let it be some
It's
garbage
just her
value, because that
wearing
would
the
imply that
glasses.
who knows where it's pointing. I need some definitive value. And just what would your instincts be? If I want to make clear with some special sentinel value that the buck stops here, what do I put? What might my options be? Yeah, so null, not NUL per se, but NULL, which was the new keyword we introduced last week, which just read
Oh,
decimal.
goodness. I forgot what he said about
In the
the...
number 2, somewhere popping things off the stack, you can realloc in the other direction. Call we've used when you do have a person. That was easy back in the day. Now it's used to declare pointers. It's also used to dereference pointers. So to make one exist and then go to that address. Unfortunately, it's the same symbol for all of those, but it's all related. But with these 3 symbols, it turns out you're going to get one last one today. And my God, it finally looks like the concept. It turns out there's a clever way. Anytime you want to use the dot and the star together, that is to go somewhere and go to an address and then look inside of a structure, you can actually literally use an arrow symbol on your keyboard. It's not a single keystroke. It's a hyphen and then an open angle bracket, but at least it looks like an arrow. And we'll see indeed in code today, the things I was drawing pictorially on the screen last time with yellow arrows, you can actually now express as well in code. And so here we have
Nice.
our next data structure called a linked list. And this is one of the most useful, powerful concepts in C. It's the kind of thing that you can take for granted in Java and Python and higher level languages. But today we'll see how we or others can actually build these things just using these same primitives. So a linked list is going to allow us to actually do
While you're
what
watching
we,
that video,
used the foam finger for last week,
because I
allow us
wanna
to
learn
link
some
together, for instance,
coding.
these 3 values, maybe with that 4th value over there. And then if there's a 5th, maybe this other foam finger points even farther over way to that 5th value. The key being that you can stitch together fancier data structures without having to like pick all of these up and find new space. You just have to at least connect the dots somehow. We just need to somehow point from one to the other. And that's going to make things much more efficient, it would seem. So how do we get there? So here's my computer's memory as always. Suppose that I'm storing the value 1 somewhere in there, and it's at 0x123 address, whatever. And I'm storing the number 2 somewhere else in memory, 0x456, and number 3 at address 0x789. This is not an array by definition. Why? Even though it's the only 3 things on the screen, what makes this not an array? It's not contiguous. So this violates the definition of an array. But especially since they're sequential, it kind of looks to a human like a list. So it would be nice if there were a data type called list. And there isn't in C. There will be in Python. But you know what? If I could somehow like stitch together these 3 values so I can get from one to the next, then I think we could achieve the idea, the concept of a list, without this really annoying constraint that they all be contiguous as in an array. So how do I do that? Well, at the end of the day, I only have memory at my disposal, right? There's no more training wheels to take off here. This is what we've got underneath the hood of a computer. So if all I have is memory, I think the solution to this problem of stitching together those values in a list must be to spend a bit more memory. That's literally the only resource we have right now. So let me propose that if we want to create a list conceptually out of 3 values that are in random, although pictorially pretty, positions in memory, let me just add a little bit more memory to the picture. So in addition to storing the 1, I'm going to leave myself some room, a little scratch pad, if you will, to use some other bits as well. Same for the 2, same for the 3. And you can perhaps see where this is going based on last week. If I want to somehow connect the 1 to the 2, any instincts as to what I should write in this box here that would lead me effectively from 1 to the 2? What could go here? Yeah? We could store the address of 2, and so specifically, what would you have me write here? Perfect. Ideally, I would just put in this box another integer, one that happens to be represented in hexadecimal, but that's just a base system. It's just a human thing for us to look at. I'm going to put the value 0x456 here. So let me go ahead and reveal that. 0x456 goes there. You can perhaps see further where this is going. Well, if I want to get from the 2 to the 3, I think I need to put below the 2 the address of the 3, which gives me 0x789. Now, if 3 is the end of the list, I don't want to let it be some garbage value, because that would imply that who knows where it's pointing. I need some definitive value. And just what would your instincts be? If I want to make clear with some special sentinel value that the buck stops here, what do I put? What might my options be?
Null.
Yeah, so null, not NUL per se, but NULL, which was the new keyword we introduced last week, which just represents an empty pointer, if you will. Technically, the address 0x0. So literally the 0 address. And what humans did years ago, they just decided, you know what? Nothing should ever live at address 0 in memory. We're just going to reserve that one special byte to be a special signal, a sentinel value, such that if you ever see a 0 address in a pointer, it just means it's invalid. It does not exist. Now, we write that, though, a little more pleasantly for the eyes as just NULL in all caps. And that's a keyword in C as well. But of course, last week I claimed that who cares where things are in memory? And honestly, like, this quickly gets tedious even worrying about these values. So let me abstract this away and propose that if we want to remember where all of these numbers are in memory, let's give ourselves one final piece of memory that just allows us to start the whole process. Let me allocate on the left-hand side here, not room for a number like 1, 2, 3, just room for a pointer that henceforth I think I'll call list by convention, and then store in that one additional pointer a value that just kickstarts the whole process. This is the sort of treasure map, if you will, that you get handed, and this has the address of the very first actual node in memory. Now, technically, we could just start with this, but it turns out, we'll see, it's just a little cleaner to use a simple single pointer that leads to the things you care about, as opposed to just starting with the first element. Why? Well, if you ever want to get rid of this element, it'd be nice if you could at least still hang on to an empty sheet of paper that indicates that the list is empty, would be one argument for that. So again, who cares about these addresses now? Now, with a wave of the hand, let's just abstract it away. And there are our pointers. Each of those addresses in the squares at the bottom are simply pointing to the next element in the list. The jargon to introduce here would be that now that we have these integers, 1, 2, 3, but they're in these like wrappers, if you will, these structures that have metadata, that is additional data that is related to, but not the data you actually care about. This is data. This is metadata. This thing here, rectangularly, we'll call a node, N-O-D-E. And it's just a term of art that means it's like a container in code for storing some value. And it's just a data. This thing here, rectangularly, we'll call a node, N-O-D-E. And it's just a term of art that means it's like a container in code for storing some values.
I see.
This then is a linked list, and this then is the sort of graphical incarnation of like one node pointing to the other. In this case, they happen to be, by chance and by design of this desk, contiguous initially, but there's no requirement that they be such. The 1 could be over there, the 2 over there, the 3 over there. I would just need more foam fingers to point at one to the next. Questions on this concept of a linked list? Yeah, and back. Can you say that again? A good question. Do traditional arrays start with a pointer that's outside of the structure? Short answer, no. Arrays are special in C and certain other languages, and the name of an array is technically a symbol, if you will, that the program knows maps to a specific location in memory. It's just a label, a synonym for a memory address. It does not take up space.
What's the animation for?
So to be clear, the name of an array
It's a meme.
does not take up space like that
I don't know.
extra
It's not even
square
a
on
meme,
the
but
left.
like
But you do need that extra
random
square on the left when
ideas.
implementing a linked list, so that
I want to
you
try,
can determine if the list is of size 0, there's nothing being pointed at, or size 3 in this case. We're sort of taking on more responsibility.
It's a Black Ops reference, if you know what I mean. You played Black Ops, you should know.
How do you point to the next element? Can you elaborate? Good question. If each of these elements is pointing to the next, how does 3 point to the others? Short answer, it doesn't. At least in this design, we have more technically what's called a singly linked list. And as the arrows imply, it only goes in one direction. So if you somehow
The
find
numbers
in code,
now is
maybe
the
a for loop,
sunglasses. It's
maybe a while
Hudson,
loop,
man.
Somehow you're sort of
Hudson, whenever he wears his
no
sunglasses, the
way.
music starts. The one that goes like. I don't know.
The arrows
Man.
imply.
I don't know why I came up with that idea.
Implementing a linked list so that it does not take up space. So to be clear, the name of an array does.
Wait, what?
Array is technically a symbol, if you will, that the program knows maps to a specific location in memory. It's just a label, a synonym for a memory address. It does not take up space. So to be clear, the name of an array does not take up space like that.
What the? Hello. Okay. Alright, people. Let's do this one last time. My name is Miles Morales. I'm not Miles Morales. Okay, what else?
That extra
Yeah, I was asking why is only one symbol.
again. But there's no requirement that they be such. The 1 could be over there, the 2 over there, the 3 over there. I would just need more foam fingers to point at one to the next. Questions on this concept of a linked list? Yeah, and back.
My name is What?
Can you say that again? A good question. Do traditional arrays start with a pointer that's outside of the structure? Short answer, no. Arrays are special in C and certain other languages, and the name of an array is technically a symbol, if you will, that the program knows maps to a specific location in memory. It's just a label, a synonym for a memory address. It does not take up space. So to be clear, the name of an array does not take up space like that extra square on the left, but you do need that extra square on the left when implementing a linked list so that you can determine if the list is of size 0, there's nothing being pointed at, or size 3 in this case. We're sort of taking on more responsibility ourselves. Yeah?
I see.
How do you point to the next element? Can you elaborate? Good question. If each of these elements is pointing to the next, how does 3 point to the others? Short answer, it doesn't. At least in this design, we have more technically what's called a singly linked list. And as the arrows imply, it only goes in one direction. So if you somehow find in code, maybe a for loop, maybe a while loop, somehow you're sort of in code over here, you have no way in code to go backwards unless we change this to a doubly linked list where I add another box that lets me have arrows in both directions. Or maybe I just kind of make it circular and I connect the 3 back to the 1, which you can totally do, but that tends to make life harder because now you have to figure out when you're stuck in a loop in your data structure, but it's doable as well. But as is, it's a dead end by design. Other questions
All right.
on this design here? All right, well, how might we implement this structure in code? Well, let me just connect the dots to something like we've seen before here. Like this is how, a couple of weeks ago, we introduced the notion of a person, and we claimed a person might have a name and a number. Last week, of course, we took off some of these training wheels, and a string is really technically a char star in both cases, but really there's no conceptual difference beyond that. But let's use this same paradigm to implement a node as I described it in that picture. So let me get rid of the name and the number, because that's related only to a person. And let me rename this structure, for discussion's sake, to node. That then invites the question, well, what needs to go inside of a node? Well, minimally, an integer. But this is now where we need to think a little harder, just conceptually, even if you have no idea how to type it on the keyboard, what else needs to be part of a node based on these rectangular pictures that we've drawn? What more do we need? Yeah.
The next. So like when you're gonna draw.
Yeah, we need a pointer
I can't
to
draw
another
that
node.
on stream,
so
you know.
If I don't know how
I mean,
to
I can,
implement
but
this
not today.
Yet, you know, it could
don't feel
be
like drawing
something
those
like
today,
pointer
you
to
know.
another node. How do I do that?
So,
well, you know what? It turns out
I
you
need
would
some
ideally say
ideas
this.
though.
If you know that the next node is itself a node by definition, well, anytime we've needed a pointer, we just use the data type and a star. And I'm going to arbitrarily, but I think reasonably call this second square at the bottom of those rectangles next as the name of my attribute here. But node star just connotes that the next variable is going to be not a node per se, but the address of a node. And that's exactly what we did. You had me put 0x456, 0x789 in that box, which is the address of another node. So the way we would express this in code would be node star next. But we could call the variable anything we want.
Dun, dun, dun.
Now, this is a bit of a white lie, but we'll fix this right now. This code won't actually compile. C takes you pretty literally, recall. And if you use some term at the top of your file that you don't define until later in your file, you're going to see some error message, right? We've seen this when I've messed up and
Yeah.
I forgot to include the function prototypes.
Yeah. Oh no.
In here on my
Oh,
1, 2,
okay.
3, 4th line of code, I'm trying to use this new term of art that I invented here in my code called node, even though it's a CS term as well. But nowhere above this, it would seem, did I even define what a node is. It's not a data type in C. Every computer scientist knows what a node is, but it doesn't come for free with the language. So I need to do something else. Like I need this word here to come first so that I can use it here. And so we have this sort of catch-22. Like how can a structure be self-referential, that is point to another version of itself if the word doesn't yet exist?
Oh.
So the solution to this in C, which we didn't need for a person because there was no notion of listing, connecting as a list, we need one more keyword here that we didn't need for a person, and we reuse that keyword here. So kind of an annoying detail, but if we preemptively call this whole thing struct node, you can now refer to the thing on the inside as a struct node star, but then you can shorten the name of the whole thing from struct node to just node. Sort of an annoying sequence of steps, but in short, anytime you're building a node, a linked list in memory, this is just the paradigm. You use typedef, struct, the name of the thing you want to define, like node. You use that name on the inside if you want to point from one to another, and then you can shorten it down here to just be called node.
Makes sense, makes sense.
In this code here. Questions on what we just did? Well, if I rewind just a moment to that final picture, what would be the upside, to be clear, of having jumped through these hoops and added this complexity, if you will? What problem did we just solve by linking together these three values, to be clear? Yeah. Making lists that are
Dynamic?
that are not contiguous, if you will. So making lists that are not contiguous in memory, the upside of which is that if I want to add the number 4 to this list, it looks like I could choose from any chunks of available memory on the screen. I just need to sort of point from the end of the current list to wherever that other one is in memory. What I don't need to do, to be clear, is copy the 1, the 2, or the 3. Everything can just stay put, which means time-wise, I can do this much more quickly, it would seem, without copying things again and again, and even without using realloc to let it do all of the copying potentially for me. All right, but as we'll start seeing even more in the coming weeks, every time we benefit and solve some problem, we pay a price. There's a trade-off. What is a downside, as you might perceive now, of using a linked list instead of an array?
Memory?
Yeah. Yeah, I mean, we use twice as much memory because now, in addition to storing the integers 1, 2, 3, I also need to store a pointer for each of those. And honestly, even this picture is a bit of simplification. Technically, in most systems today, each int would be 4 bytes. Technically today, most pointers, though, would be 8 bytes. I just didn't want to draw this weird shape on the board where the bottom square is even bigger than the top square. But technically, we're using even more than twice as much space for these pointers. So there's that trade-off. Now, thankfully, decades after C was invented, memory is generally much cheaper nowadays. And so it's OK to sort of spend more
I mean, you did draw.
And it depends on what you
Okay,
want to
so
optimize
like
for,
you
but that's
sure you're
absolutely
unable to
here,
draw
the
them?
downside. What's another downside of
What do you mean
having transitioned
unable?
to
I can draw
linked
those.
list?
It's just that I don't
You can't
draw them
index
often.
into it. Now, I haven't even tried in code, but when you have a linked list, you can no longer use square bracket notation. Because why? Well, square bracket notation just assumes the contiguousness of memory. Location 0 is here. Location 1 is literally 1 to the right. Location 2 is literally 1 to the right, 1 to the right. These things, even though I've drawn it from right to left to just keep things pretty, there are gaps here. And this is just my interpretation of this. These gaps could be big, they could be narrow, they could be down.
Wait a minute, what?
List, you can no longer use square bracket notation. Because why? Well, square bracket notation just assumes the contiguousness of memory. Location 0 is here. Location 1 is literally 1 to the right. Location 2 is literally 1 to the right, 1 to the right. These things, even though I've drawn it from right to left to just keep things pretty, there are gaps here. And this is just my interpretation of this. These gaps could be big, they could be narrow, they could be down here, up here, they could be anywhere so long as we're linking things together in this list. The computer can't just use bracket 0, bracket 1, bracket 2 anymore because it can't do simple arithmetic and jump to like the middle. And now here's perhaps the worst price we've paid. If you don't have square bracket notation, or really you don't have contiguousness, what algorithm did we just sacrifice for this dynamism? If you rewind even back to...
What? What did we sacrifice? I don't know. Array. We can... Oh yeah, the loop thingy that goes to, I don't know, I think.
0. And we gave it a name in week 3. What algorithm can we not use now if we can't assume that the memory is back to back to back to back? Binary search. Why? Because binary search, just like the phone book back in the first week, requires being able to arithmetically jump right to the middle. Right? Take the total length of it, divide by 2, and boom, you're right there in the middle with some simple arithmetic. Here, they might be laid out, again, with these big or small gaps. There's no simple math I can do to just jump immediately to the one in the middle. And in fact, again, if this TV were bigger, the 2 could technically be in memory, be way down here, or even way over here. The foam finger could be pointing in any number of directions, depending on where malloc put the thing. There's just no way to do binary search. And so it would seem that we've paid another price, indeed, in terms of its performance. We're now talking about linear time again. So that's a regression. Now, that's also a lot. Feels like a good time for some muffins and fruit out in the lobby. And when we come back, we'll try to solve the problem we just created. So see you in 10. So we are back, and let's see if we can't now take some of these higher level concepts of like stitching together these nodes in memory and translate it to some actual code. But we'll do it step by step first before I actually start writing it in VS Code. So if Carter, you wouldn't mind helping me step through with some visuals, let me propose that line by line we solve some of the problems that we've just created for ourselves in building this thing in memory. So let's go ahead and first consider how we could build a linked list containing the numbers, indeed, 1, then 2, then 3. And let's translate each of those steps to code, and then we'll put it all together into something that actually runs. So how about the first step here will just be this, to declare a pointer called list that initially has no value, at least at this point in the story. List is the name of the variable. Node star just means that this is essentially going to be our little square over here that points to the beginning of the list. Of course, it's ideal if it ultimately has a value, because when we initially call this line of code, it just gives us, indeed, that square over here on the left. But it's got to go garbage value because there's no equal sign on the other side there. So let's propose that we do one more step here and actually initialize it to null so that if only we know that it's not garbage, it at least has some known value. And null is a good way of signifying that at this point in the story, the list is empty. Indeed, null indicates there's no nodes in the list. So that picture would now look like this, whereby let's just draw, instead of writing null everywhere, I'll just leave the squares blank when it's not a garbage value per se. It's literally OX0 or null. All right, so that's it for building a linked list of size 0. Like we're sort of done then, but we want to now add a 1 and then a 2, then a 3. So next step here might be this. If I want to allocate the first of my rectangles on our previous picture, I'm going to call malloc, and I'm going to ask for enough memory to fit a whole node. Now, technically, I think that's going to be like 4 bytes for the int and 8 bytes for the pointer, even though I did not draw it to scale on the square. But it's got a garbage. I'll call this, and then we'll put it all together into something that actually runs. So how about the first step here will just be this, to declare a pointer called list that initially has no value, at least at this point in the story. List is the name of the variable. Node star just means that this is essentially going to be our little square over here that points to the beginning of the list. Of course, it's ideal if it ultimately has a value, because when we initially call this line of code, it just gives us indeed that square over here on the left, but it's got a garbage value because there's no equal sign on the other side there. So let's propose that we do one more step here and actually initialize it to null so that if only we know that it's not garbage, it at least has some known value. And null is a good way of signifying that at this point in the story, the list is empty. Indeed, null indicates there's no nodes in the list. So that picture would now look like this, whereby let's just draw, instead of writing null everywhere, I'll just leave the squares blank when it's not a garbage value per se. It's literally OX0.
Oh gosh.
All right, so that's it for building a linked list of size 0. Like we're sort of
Hopefully
done
I didn't
then,
break it.
but we want to now add a 1, then a 2, then a 3. So next step here might be this. If I want to allocate the first of my rectangles on our previous picture, I'm going to call malloc, and I'm going to ask for enough memory to fit a whole node. Now, technically, I think that's going to be like 4 bytes for the int and 8 bytes for the pointer, even though I did not draw it to scale on the board. So that's technically going to be, what, 12 bytes? But again, size of node just figures out how many bytes I actually need dynamically. That's going to return to me the address of that chunk of memory, which apparently I'm going to...
Shh. Sorry. It usually turns off for some reason. I can just go for like high performance. Change advanced power settings. USB settings, selective suspend settings. Just disable that. PCI Express, we don't care about that. Processor mana. We don't care about this. Wireless. Maximum performance, good. Display. Yeah, we're good, we're good. Okay, hopefully it works now. I see. Hey, I drew Yujiro from Demon Slayer. I don't know. Yujiro. That sounds. Oh. My goodness, Baki. Okay. I mean, you can send it over onto my Discord server. What the heck is this? My Discord server. I put it in the description. You can go to Art Showcase. Oh, okay, that was it. You can post it here, or you can go to Art Discussion and, you know, post it here. Yeah. Anyway.
Going to store inside of a temporary variable called
guys,
n for short for node, but let's see what this does pictorially. So when this line of code is executed, I first get on the left that variable n. It's got a garbage value by default because I haven't executed the whole thing from right to left. Meanwhile, on the right-hand side of the expression, I've got now a node somewhere in memory. It happened to be free here. This is where malloc put it for me. But it does have 2 garbage values initially. But because it's a node, per my type def earlier, every node I proposed is going to have a number and a next pointer. So we can see those labeled here. But they've got 2 garbage values initially, but all I care about initially is that ultimately n is pointing at that chunk of code.
Node n. Okay.
So initially, if we could back up 2 steps, we have 2 steps.
Wait. Before that, so we got the list. Now
Or
what?
null. All right, so that's it for building a linked list of size 0. Like we're sort of done then, but we want to now add a 1, and then a 2, then a 3. So next step here might be this. If I want to allocate the first of my rectangles on our previous picture, I'm going to call malloc, and I'm going to ask for enough memory to fit a whole node. Now, technically, I think that's going to be like 4 bytes for the int and 8 bytes for the pointer, even though I did not draw it to scale.
Should I do in betweens? What in the multitasking?
Board, so that's technically going to be
Sorry,
what, 12
people.
bytes. But again, size of node just figures out how many bytes I actually need dynamically. That's going to return to me the address of that chunk of memory, which apparently I'm going to store inside of a temporary variable called n for short for node. But let's see what this does pictorially. So when this line of code is executed, I first get on the left that variable n. It's got a garbage value by default because I haven't executed the whole thing from right to left. Meanwhile, on the right-hand side of the expression, I've got now a node somewhere in memory. It happened to be free here. This is where malloc put it for me. But it does have 2 garbage values initially. But because it's a node, per my type def earlier, every node I proposed is going to have a number and a next pointer. So we can see those labeled here. But they've got 2 garbage values initially. But all I care about initially is that ultimately n is pointing at that chunk of code. So initially, if we could back up 2 steps, we have 2 steps. So we have 1 step forward. We have this line of code gives us this variable here, which has garbage. When this side of the expression is executed, that allocates the memory. And then when we copy from right to left the address of that chunk of memory, that's what gives us conceptually this arrow, and the garbage goes away because that's a valid pointer now. Of course, there's still 2 garbage values there because we haven't set this node to store a number like the number 1. So let's go ahead and execute one other line of code like this, which, while cryptic looking,
Wait a minute.
this variable here, which has garbage, when this side of the expression is executed, that allocates the memory. And then when we copy from right
Oh, okay. I forgot that n is a freaking pointer. My goodness gracious.
to left, the address of that chunk of memory, that's what gives us conceptually this arrow, and the garbage goes away because that's a valid pointer now. Of course, there's still 2 garbage values there because we haven't set this node to store a number like the number 1. So let's go ahead and execute one other line of code like this, which, while cryptic looking, is just an application of ideas we've seen in week 4 and prior.
Okay. Go to n, which means it will go here, this node, and then it would go to the number, which is the top slot, and it changes to 1. Okay, get it.
Star n means to start at this variable and go there. Follow the arrow is what the star or the dereference operator does for us. And then the dot operator, recall, when we first introduced structs, like for a person struct, allows us to go at the number field or the next field. So if I do star n, and then in parentheses to make sure order of operations is preserved, dot number, and then assign it the actual number 1, which puts the 1 in the top of that rectangle. Now, admittedly, this syntax is not very user-friendly. It's annoying to remember. You have to have the parentheses. So there's another syntax for this. Whenever you're doing 2 things like this in code, dereferencing a pointer that is going to an address, and then further using the dot notation to go inside of the structure you find that, wonderfully C gives us this syntax whereby you can just change the star and the parentheses and the dot to just be an arrow. And again, it's not a single character on your keyboard. It's a hyphen and then an open angled bracket. But I kind of like the semantics of this because this code now pretty much matches the picture. N arrow leads you to the value that you want to access or ultimately change in this way. There's one step, though, we've forgotten, of course, which is that we can't leave this garbage value here because the garbage value is some unknown value that effectively is pointing who knows where. And we don't want to accidentally misinterpret that garbage value as being a valid address and risk going there. So, of course, what value should we put here instead? Our old friend null, just to signify that this is indeed the end of the list. And we could do that with a line of code like this. And again, we'll connote as much by just leaving that empty box blank.
Okay.
So now we have a list of size 1. Let's go ahead and add the second number to it, as with these lines here. List equals n allows us to remember that indeed we have this list here. So if we can step 1 step forward, here's what the picture now looks like. And technically, let's go one step further here. This is now really what's going on in memory once my list of size 1 exists. My main variable called list is pointing at exactly that first node. At this point in the story, I don't need to know or care about the temporary variable that I called n, even though it might very well still be there. But indeed, this now represents that linked list. Let's now indeed add the number 2. So with the same line of code as before, I'm going to allocate another node, size of node. Ideally, I would be checking for null here, but we're doing the juicy parts only on the slides. Let's now go ahead and depict that. So what happens with this? This brings back our n pointer, which might have been there the whole time, but we're doing this step by step. It's a garbage value, though, because we haven't yet copied from right to left. Malloc, of course, gives us a second chunk of memory, which maybe ends up there with 2 garbage values by default. I've omitted the labels now just because they're still going to be number and next, respectively. Once we copy from right to left, the garbage value indeed becomes an arrow. Oscar disappears because it's now indeed a valid pointer pointing here. Now, the values themselves, number and next, are invalid garbage values. So here is where we can now start using our new syntax, like the arrow notation, or the star and the dot if you prefer. And we can change the value of n, follow the arrow, to number, and that becomes 2. Similarly, we can do this again and set n arrow next. So start at n, follow the arrow, access the next field, and set that equal to null. Now, we're not quite done yet because we haven't actually linked things together. So here's now where things get interesting. How do I combine these two? Well, let me propose this. Let me propose on our next line here, we actually update for now list equal to n. That is to say, whatever address this is, whatever it's pointing at, change list to be the same address. That is, point at the same thing. So if n is pointing here, let's change list to point here and go ahead and do
What's my opinion on Good Media? I mean, depends on what you're talking about. I like them clean. Wait, I don't know. Stop asking me random stuff, man. I don't know, man.
Don't like this. Can you go one further step? This is bad. What is wrong about my sequence of operations here, where I up that Carter if you could, n is pointing at, change list to be the same address. That is, point at the same thing. So if n is pointing here, let's change list to point here. And go ahead and do that, Carter, if you could. I don't like this. Can you go one further step? This is bad. What is wrong about my sequence of operations here, where I updated list to point at my new node?
There's 2 of them?
Yeah. Yeah, we lost the pointer to the other node. So I don't even care about the ordering, 2, 1 or 1, 2. The bigger problem now, as the lack of arrows over there suggests, is that I have a memory leak. I have orphaned my original node in the sense that nothing is pointing at it anymore. Now, absolutely, I could fix this by adding some temporary variables. I could add it to the mix, but at this point in the story, I have not done any such recollection thereof. So let me back this up and let's go forward in the slides. This is where we left off a moment ago. I think I need to take into account order of operations. And I'm going to keep this simple. I'm not going to care about the order of the numbers for now. I'm fine with a list that is 2 and then 1. So with that said, let me go ahead and update, I think, this box here to point at my original node. So let's see how we can do this in code. OK, n arrow next. So n arrow next should equal the current list. And this is a little weird again, but recall what list is. List is this pointer here that just contains the address of the original address of the list. Or, equivalently, it contains this arrow, whatever it's pointing at. So what this means in this line of code, n bracket next means start at n, follow the arrow, access the next pointer, and set it equal to whatever list equals. So if list is pointing here, then next should point there as well. This, I think, is safe because now we have redundancy. Now we've got 2 pointers pointing at the original list. And now I think we can do another step whereby we update list to equal n, same line of code before that got us into trouble, but I'm doing it second now instead of first. When I execute list equals n, this now sets list equal to the same thing that n equals. And so now I have successfully inserted my new node containing 2 into the list. And in fact, if we advance one more, we can just clear up the clutter, assume that the temporary variable is gone from the story. Now we have a linked list where, admittedly, ordering is wrong. It's 2, 1 instead of 1, 2, but at least it's linked correctly, and I didn't orphan or leak any memory. Questions on this sequence of steps here? Yeah, and back.
Ooh.
Yeah, spot on. So this would fall under that category of a stack, if you will, although I've not called it that by name because I just pushed the number 2 onto this data structure, if you will. And indeed, it ended up at the beginning of the list instead of the end. And so here's where we see a distinction between an abstract data structure, which is where we began. A stack is a thing like the pile of sweaters that just has push and pop properties and LIFO access, last in, first out. How do you implement something like that in memory? Well, it would seem that you could implement the notion of a stack here, not for sweaters, but for numbers, using a linked list, so long as you implement insertion, aka pushing, by prepending new values to the list, by prepending again and again. And if, Carter, you don't mind hitting the keyboard one more time, if I wanted to add the number 3 now, you could imagine prepending it to the list. Why? Well, honestly, especially as this list gets longer and longer, I kind of like the appeal of prepending these elements. Why? Because even if this list gets crazy long and way, way out here, you didn't notice me following all of the arrows earlier to do the insertions. If I want to insert a 4th number, a 5th number, a 6th number, all I have to do is like insert it here, if you will, point it at the original start of the list, then update this pointer, and done. And I would say that's like 2 steps.
Which section? I don't know. What do you want? Do you want? Is it like a finished art? You can post it in art showcase maybe. But if you like, it's not finished, I mean, you can still post it in here. But like, if you want to like have questions, maybe you're not, then I guess art showcase. But if you want to ask questions like, oh, I have problems with this and that, you can post it in art discussion. Doesn't matter, anywhere's fine. But art showcase will save your for a longer period of time, hopefully, without being pushed away by these comments or whatever. I don't know what I'm saying. I don't even know what that gives me.
Or take, it's not going to be n steps, as it would be if I had to append the new nodes to the end of the list. Now, of course, we've sacrificed ordering of these numbers. They're literally in the opposite order, or whatever order they were inserted in, but that might very well be OK, depending on the goal at hand. All right, thank you to Carter for stepping through this. What if now we wanted to translate this? Oh, sure, thank you. It's all for you, none for me in this example. So here we have perhaps a way of translating this now to some actual code. And this will be the last of like the sort of intense code here, just to give you a sense of how we can translate this idea now to actual steps. So this is list.c in VS Code here. Let me go ahead and make a couple of changes up top. Let me go ahead and how about declaring a node using typedef, struct node using our new framing as before. I'm going to give every node a number, as I proposed, and every node a pointer to the next element, which is going to be
okay, it's not perfect, but it's finished.
I'm going to
Okay.
simplify the whole name as just node. So all of that is the exact same typedef that we proposed earlier. Now, let me go ahead and get rid of all of this code, which we wrote earlier, and recall that this was the most recent version that was not a linked list. This was just an array that we allocated and then reallocated. So this is sort of the old way of doing things, but it was inefficient because we might have to lean on a for loop or lean on realloc to copy everything around. We're now going to re-implement the notion of a list as an actual linked list, not as an array. So my main function now might do something like this. And I'm going to really just copy the lines of code that we just stepped through on the board. So let me give myself a special variable called list that's going to be initialized to null. And this is just my pointer, the square on the left-hand side of the screen, that represents the start of the list. And if it's null, it means the list is empty. So done. I'm done implementing a linked list of size 0. Well, now, how do I want to run this code? Well, let me propose, for the sake of discussion, that this version of the program will take command line arguments. So I want to be able to do something like this. I want to run this program ultimately and type in 3 command line arguments like this, 1, 2, 3. And I want my program in a couple minutes to allocate 1, 2, 3 nodes and stitch them together, just like the visualization on the board. I could use getInt, but it's just going to be faster if we use command line arguments. So again, I'm just borrowing some concepts from week 2. But none of that's possible yet until I change my code here. So let's do this. Int argc string argv, but you know what? We know that strings are not actually a thing anymore, so I can change my command line argument definition to be what it really is. It's really char star, but it's the exact same thing as in week 2. Just strings are no more, at least without the training wheels on anymore like last week. And now let me do this. For int I equals 1, I is less than argc, I++. So what I'm doing with this loop is I just want to iterate over the command line argument. So I have one number at a time from the prompt. What else do I want to do here? Well, let's go ahead and...
I should pay attention. Wait, what? Okay, so okay, so we're just going to pass in a number in the terminal to run the program instead of like having to enter it directly. Or maybe like code another input line in the code. I don't know. Maybe, yeah.
Okay, let's get a number. So int number equals argv bracket I. So a couple of notes here. One, I'm starting my for loop at 1 instead of 0, but I'm going up to argc. Argc is argument count, how many words are at the prompt. Why am I starting at 1 instead of 0, though, given my goal? Why am I starting at 1? Yeah. Yeah, so the first value in argv is actually the name of the program. That's obviously not a number, so I want the second value. So I'm going to start iterating over those command line arguments at I equals 1. So that's all. I just want to get the actual numbers at the prompt. Unfortunately, argv bracket I is a string, aka char star. That is not an int. So this line of code won't work. But can anyone think back to like week 2 where we had a function for converting strings to integers? Anyone? Yeah, so a to I is a function that converts ASCII to an integer, assuming what you give it as an argument looks like a number, like 1 or 2 or 3. So let me fix this. Let me actually do the conversion. If I were really being careful, I would error check this, make sure that there's no digits, just like you might have in problem set 2. But for today's purposes, I'm just going to assume the honor system that the user, me, is going to run the program correctly. All right, so now that I have a variable containing the number from the command line, let's just allocate a node for it. So let me do node star n, just like we did in the visualization, and let's malloc enough space for the size of one such node here. I now need to just be super safe. So if n equals null, like if I'm out of memory, you know what? Let me go ahead and just immediately return 1 here. Otherwise, if that's not the case, let me go ahead and update the number field of this new node, which at line 24 does exist because it did not return null. So I did not exit early with return. And let me just store whatever number the human typed in first. So the return value of a to I, which per line 17 is in my variable called number. And then let me go ahead and just prepend this to the list. Let me go ahead and say that.
Oh, what? Hold on. And malloc. Okay, map allocation. Blah, blah, blah. Okay. Int number.
This next field first has a known value null, just so that we get rid of that second garbage value. And let me go ahead and now prepend it to the list. So if I want to prepend it, that means this new node must have a next field that points to the current beginning of the list. And again, the goal here is to prepend. So whatever the current list is, let's change it so that this new node points to that existing list. And now, step 2, as before, was to update the actual list to point at this node. So recall in red on the screen before, I screwed up originally, and I only did this line by moving the pointer too early, if you will. But I fixed that once Carter helped me rewind, and we got rid of the red line, which indicated error, and I just do n arrow next to change the next field of this new node to point to the existing list. So I'm not orphaning anything.
Wait. Hold on a minute. Huh? Number equals to string to I, and it's arg vi that starts with 1. What does it mean? Okay, so we get the number to equal to the... Okay, so if we start the program, whatever this program is, list, and then we say like 5, then we get this number. It starts from 1. Huh? So it's just get... Oh, yeah, okay, get it. But why is it argc? Oh, argc is counting the number of stuff after here. Hello, Jono Laguitan. Okay, I think I get what he means by this code. So basically, I don't know why I'm explaining it to you guys, but I'm just gonna explain this for myself. So basically, he runs the program, which is lists. Then he put numbers in here, like 5, 7, 8, 9. Then the program will start making a list of these numbers. So it's gonna put 5 in here, right? And then the next number we put in the back of the list, and then 8, and then 9. So that's basically what the program is doing. Okay, I get what he means now. Okay, let's move on. Oh my gosh.
All right, at this point in the story, I think my code is correct.
Okay, next is node. Okay, everything, he explained this all already, but now this bottom part here. And next equal lists. So it sets to null first, and then it will set it to lists. Okay, so there's a problem with this. Maybe he'll fix it later, because we don't know if there's any other stuff. I don't know, maybe. Anyway, n gonna list, and then list equal n. Wait a minute. Okay, so it map allocation. Even in vacation, can escape from computer science. No, you're not the ones that are learning. Don't worry, I'm not dragging you into this. Give me a second, let me draw her hair real quick. Oh my gosh. Okay, so let me try to figure out what the code do, okay? So we got the node n here. Got n. Got the list, of course. And we point to a number, or like a freaking... There, this is number. This is the next. So this points here, and it sets the number to the current number, which is the number in this line here. For example, list 1 2 3. For example, list 1 2 3. This brush is not good for writing. So the first number will be 1. Okay, the next is set this to null. So let's just call this 0. And then next will be set to lists. This will be set to list, so this will be a pointer. Set to lists. Okay, list is pointing to this, right? And then this will point to that. Why though? Oh no, next we point to itself? Huh? Wait a minute, what the heck? Wait, maybe list hasn't been like pointed yet. What the heck?
Not batting very well though today, but I think my code is correct, but the program doesn't do anything interesting. So it would be nice to kind of now...
Wait. Okay, so he have a list that is null first. List that points to nothing. Just might as well do this. List. Okay, so we know it's a pointer. it has like nothing in here, so it's a null. Okay, so first this null. Okay, so it gets the number, the first number right here. It puts into here, so we got that one, and is into this. Okay, whatever. Okay, so number will be number. Next would be null, but then he set the next to the lists. Apparently. Like this. So the next points to the lists. Huh? What? Equal list. So it's basically null. Why though? But then lists equal n. Okay, lists equal n, which means now lists we point itself to this. Okay. List will point itself to this. But then this will be still be null first because this happens first, and then this will be the number first one here. Okay. Alright, good. But then what? What next? And then if we have another number here, he said it would be appended or prepended. So the num here would be 2 because this is the second one. And then the next would be null. Okay. And then the next would be list. Okay, next would be list. Next would be the list, which means it would point into this, which means this is now not blank, but it's actually pointing somewhere. And then the list would point to n, which was pointing to 2, which means list is now pointing to 2. Oh, I get it now. Okay. Too much computer science in. Okay, so much for art stream, I guess. Anyway, let's move on to this. I think I get it.
List, so I'm not orphaning anything. All right, at this point in the story, I think my code is correct. Not batting very well, though, today. But I think my code is correct. But the program doesn't do anything interesting. So it would be nice to kind of now iterate over this linked list in memory, whatever its order is, and print things out. Well, how do we do that? Well, it turns out if you want to iterate over a linked list, the general paradigm is to do something like this. To define a temporary variable, I could call it temp, but another convention that you might as well see is called pointer, PTR, for short. But you can call it anything you want. And you can have a temporary variable first point at the first node in the list. And then you think another convention paradigm. How do we do that? Well, I think my code is correct, but the program doesn't do anything interesting. So it would be nice to kind of now iterate over this linked list in memory, whatever its order is, and print things out. Well, how do we do that? Well, it turns out if you want to iterate over a linked list, the general paradigm is to do something like this. To define a temporary variable, I could call it temp, but another convention that you might as well see is called pointer, PTR, for short. But you can call it anything you want. And you can have a temporary variable first point at the first node in the list. And then in some kind of loop, like a while loop, you point it at the second node in the list. And then you keep iterating. You point it at the last node in the list. And then eventually you iterate too far, effectively pointing at null, at which point your while loop can presumably terminate. So how do I implement that idea of allocating a temporary pointer that just points at each node in the list and lets me print out, ultimately, each of those numbers? Well, let's go back to my code here. And let me do this. Let me go ahead and declare this temporary pointer.
It's raining.
Who drink all the milk?
You
Drink the milk không chịu không? Quay cái gì?
Alright, people. It's raining. Rain, rain, go away, come again. Na 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 na.
Which is going to be a node star also. Why? Because it's the address of the node, the first, the second, the third. And I'm going to set that equal to whatever the beginning of the list is. So that is going to be equivalent to this version of the picture here, where pointer is just temporarily pointing at the first node in the list. It's not pointing at list per se. It's pointing at the first node in the list, which list is also pointing at itself. All right, once I've done this, I think I can translate this to code that's a little new, but it's conceptually familiar perhaps now. While that pointer does not equal null. So while I have a valid pointer, like my finger or that arrow is pointing at an actual node in memory, well, let me go ahead and print it out. So let me print out with %i\n whatever is in the current node at the number field within. And again, this is going to have the effect, hopefully, of first printing the 3. And I think I just need to now update the pointer so that on the next iteration, it's pointing at the next value. So if this is where the story is, how do I update pointer to point at the second element of the list? Well, I want pointer to point at the 2, and I want pointer to eventually point at the 3. Well, how do I do that? Well, the way in code I can follow these arrows is as follows. If I currently have pointer pointing at this node, but I want to point it at the next node, I can borrow this pointer here. So whatever this address is in the first node, aka the next field, I can copy that into pointer, because then pointer will point at whatever this is pointing at by just setting one equal to the other. So once I've done that, the picture will become this. And how do I translate that to code? While new syntax is surprisingly straightforward, all I need to do is say pointer after printing it equals whatever pointer currently is, but grab its next field instead.
Oh, this is all coming together. Back when I was coding games, I used this type of stuff to the state machine and whatever. I don't know if you guys understand it, but I don't know. I used to make video games as like, as a hobby, but then my mom told me not to do it anymore because I have to focus on graduating. What games? Not really games. I mean games, yeah, but before that I coded in I coded mods for Minecraft as well, which on my alt account I do have it here. This is the game. This is the game I used to make. I don't know if you guys can see it on my head. It's just, let me just shrink this down, or maybe just turn this off entirely. Wait, does it? Oops. Lingangu liguli guli wajan lingangu lingangu. Okay, it doesn't. Okay, good. So I'm just gonna put this back here again. Alright, so this is the game I used to make. This is a simple game. It's a simple game, a platformer game, but like parkour-ish. You see, you can grab the ledge. No matter where is it. This is 2 years ago. Like this, it will automatically, grab the ledge for you. So here you guys can grab on the left, or you can grab on the right. You guys can press space to go up, but you guys have to move into the platform by yourself. So yeah, but if you want to jump on the opposite side, you will press the opposite side and you press jump, and it will do the same amount of force as the wall jump. And if you want to drop, just press down, you will drop. So there you go. And the last thing, oh, I don't know how I made it. So wait, there's a download link. Please still be here. Oh damn, it's still here. Oh no. I thought it was here. Why? Oh hell no. Come on, man. What's wrong with my car? Wait, let me try to... I don't know. I forgot what the mega account I used to have, but not this mega. Mega, not VN. Wait, mega. Wait, mega. There you go. Mega.io. Freaking. Wait, let's log in here. Okay. I'm just gonna. Alright, privacy purposes. I forgot. I don't even know what kind of account I used to store it in. But let me try to remember, And please enter a valid Linggang guli 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 wacha linggang gu linggang gu linggang guli 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 wacha linggang gu linggang gu linggang guli 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 wacha that's just linggang guli 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 wacha linggang gu. This one, guys, a Cape lover.
링강 구리 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 와차 링강구 링강구 링강 구리 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 와차 링강구 링강구 링강 구리 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 와차 링강구 링강구
You cannot say that is not. It's a good version of it, okay?
구리 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 와차 링강구 링강구 링강 구리 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 와차 링강구
Skip. Oh no, I don't have it. Oh hell no. Skip. What's your password? Wait. Media shared item. I do not have it here. Oh, my mic's weird again. What the frick's going on with my PC? I have no idea. Why just keep turning off by itself? I have no idea. Okay, but apparently I cannot get it, guys. It does not work. Well, too bad, guys. Man, what's wrong with Mega?
Is the dash.
Bro, I intentionally put it here. But why did Mega remove it? Why? Why?
You press the dash button, you will dash.
Look at this. It's so cool, right?
And
you can
guys
roll.
Can dash twice at the same time, and then limitation. And that's why you should take care of your stamina more, you know. So let's talk about something else, which is player forgiveness. I don't know why I call it that. Press space, you will jump and fall pretty fast. But if you hold the space button or the jump button, you will be on air for a longer time. But if you want more, then I will have to change.
Oh my gosh.
Which is pretty cool. But it's kinda, yeah, not good. So next thing is that the ledge detection. As you can see, if I hit my leg right there, it will push myself up. Like so.
Oh my gosh, man. I don't know. Back then, I was like this crazy dude. I don't know what crazy means, but like, I put everything into a game. It's so good. I put a lot of features. Look at all of these mechanics, you see? It's crazy how I did it.
Yeah, you know, this game is all about momentum, so yeah. Oh gosh, sometimes it's kind of glitches, but don't worry, it fixes itself. So, what do you guys think of the movement so far? I will good, so we'll have this because it's too much of a difference. So if you go like that,
you see, like it protects you from bumping your head onto like something. It's crazy. I don't know. Oh my god, I spent too much time on this damn thing. Anyway, let's move on to like the older stuff, which is the mod in Minecraft, the gun. I put guns in Minecraft, and okay, all of this was in my old PC, but it got broken and I lost every single one of it. The code the code file was very long. I spent too much time on it. Look at this. This was like April 8th, 2023, and the first video I ever spent, like the first version of this, was like March. So it's exactly, I spent 1 month. Entirely, that one entire month was just me coding this damn thing.
and then you
I made gun in
it
Minecraft.
goes down a lot because of you know, gravity.
I put sound effects on everything too.
So it is that. Yeah, the bullets now have some sort of you know, what is it called? Yeah, velocity and mass. So for different types of guns, the bullets will fly different.
You can reload, you can shoot. There's like, I added like a pistol here. Oh, I added freaking hit markers too, which is crazy.
It's turned like some kind of greenish. hit
Holy guacamole.
You just normal hit. But if it's turned blue, it means it's dead, either dead or a crit hit. 83. It's kind of random.
And then there's like M4.
You hit it. Very.
Look at that! How did I make this? I was so good, oh my gosh.
Damage is
Oh, no.
actually higher.
Oh, I lost everything, oh my
You can
gosh.
actually one shot a guy.
Look at that, man. Oh my
But if you
gosh.
shoot far away, yeah.
Oh my
takes
gosh,
2 shots. And it
dude.
depends on whether you crit and
There's crit too? Well, I don't know.
kill a guy. So, but if you stay far away, the damage will be lowered. So yeah, there's that. And the suppressor again. Yeah, it's not that high. Exactly where it has to be around.
Oh, yeah, there's a freaking sniper too.
There you go. And yes, it can one shot literally everyone.
Oh, look at that. Oh my gosh, dude. What a good time to be.
Yeah.
Oh my goodness.
And how much
I made all of the model myself, by the way. I made the... Oh my gosh. I made everything by myself, okay? I mean, yeah, basically. There's no assets, no whatsoever. Even the resource pack, the model... okay, not the sound effects. It was actually from the game itself, the Modern Warfare game itself. But
You may
yeah.
ask, let's find out. That's the crit. A crit would do.
Okay, let's check the
You have it
shotgun.
shoot. Very close range. It is close
I made the reloading stuff pretty complicated,
range,
but it works. It works very well.
but yeah, it's hard to hit,
Look at this.
but the damage is pretty high.
You see
So
the
if you
chamber? I don't know how I came up with the chambering system. Look at that.
don't hit.
Okay, so there's nothing in the chamber, okay? So you just reload, and then when you chamber, one of it will go into the chamber, and you have one extra slot that you can put your another shotgun shells
Damage
in.
is pretty high.
Look at that!
So if
What
you're
the
not
frick, man?
Sneaking, it will like this. It will spread a lot, but if you shift, it will spread less. So let me demonstrate.
Oh
Yes.
my goodness.
Yeah, it still can one shot literally everyone. But because of the velocity that it have, the further it gets, the less damage it gets.
Okay, this is what this is not. This is like the simpler version. I actually made like reloading animation. I will show you later, but now let's give you guys what it means. Oh, I also added grenade. And grenade was like the worst thing to code, okay? Because when you throw it, it bounces, right? It bounces, and because Minecraft was such like has such a limited amount of like the language that it uses isn't as low level, so it's very hard for me to that low level point to like get the physics working. So I have to do extra layer on top, which makes the whole thing a lot more complex.
Frag, it works the same thing as always.
Look at that.
If you stand far away, it doesn't hit you, but if you stand a little bit closer, yeah,
You see, like damage and stuff, it's crazy, man. I don't know how I did all of this back
a
then.
little bit of damage, but if you stand closer, you
See?
get an instant death.
I even made the stim shot. Look at
Oh,
this
yeah?
damn thing. The stim shot, when you stim, you heals, right? Look at that. I made the animation. See?
If you stand a bit too close, instant death. Yeah, instant death. So there's that.
I made the map for the whole thing. I did invite my friends to play it. I tried optimizing it so much that it can be played in multiplayer which is a very good thing. And I was fun playing with my friend.
Smokes.
But I lost it. Okay, yeah, freaking lost it, dude.
Smokes is just
The smokes too.
simple.
Yeah, look at the smokes,
It's just
man.
smokes.
It's
It's gonna
crazy.
make your game lag, but yeah, you still cannot see through it. Yeah.
Look at this thing, man. What the hell?
Even if you turn off the particles in your settings, it will still show up because I put it into force.
I don't know if I have the amount of patience to implement everything back into the game again.
Because I put the command to force, which means no matter what.
And then there's the flashbang.
It's the most annoying part of the throwable. So if you throw here, the range is crazily far. You get blindness, but also which I didn't for some reason. I don't know. I think I got covered behind the button. You cannot hear the gunshots. A little bit, but it's kind of laggy. Is that you get hit and you almost die? Yes. From it. Okay, if you press shift, if you sneak, and then you throw. Health bar. Okay, let's talk about armor plate again. Yeah. So let's talk about armor plate. So okay. So you have one bar of armor now, and if you use another one, you get the second armor plate. Every time you do it, it will show up for you. Third armor plate. Third armor plate's worn. And after the third armor plate, you cannot do it anymore. It will show you. It will say you can't wear more than 3 armor plates. Armor. And reset the map.
Okay. Oh yeah, anyway. I should have checked. Oh gosh. As I added the ADS, and then there's also the reload animation, tactical run. Look at this. It's so crispy, oh my gosh. Look at that, man, what the hell? Look at the reload animation. This is like 1-1 with the Call of Duty game. Look at that. Reload. Look at that thing. Oh my gosh, man. See? Look at that thing. I added animations and all crap. Look at that. So good. Oh my gosh. I was like cracked back then, dude. I was like a big fan of the game, you know? I even...
Hey everyone, welcome to my
I added a lot of stuff like spread. Look at this.
Accuracy to the game, which I call it spread. I don't know why it's called like that. It sounds wrong. But
I added like features, you know, like...
It is what it is. And,
look at this.
Okay, so we have spread one, which is very like accurate shots, which give you accurate shots. As you can see, the bullets doesn't go in straight lines anymore. It just go for spread two.
Okay, it's lagging.
Don't want.
Yeah, so basically
the opposite. You sneak to shoot and you right click to aim. I tried to make this as easy to understand.
oh yeah, the
as
sniper
possible,
was so
but
much better back then too.
Minecraft.
But then
I
I
don't know how to
optimized
change
it and it got
item.
worse. Look, there's
added the
animations and
bolt
stuff.
mechanic.
It's just
That's the bolting.
crazy.
This is the tactical reload. Yeah, it's
Look at
simple
that.
precision.
The sniper was so good too. Oh my gosh. You can quick scope people, which is
Yeah.
crazy.
I have a feeling about.
But then I optimized it, it got worse, whatever. And then there's like this thing.
Hey guys, welcome to the guns too. Is that the range is decreased again for we
Oh, where's the
create flanks.
shotguns? Where's the shotgun? There it is. Look at the animations.
Shot is 6 bullets. It shoots 6 bullets per shot. So it doesn't crash your games. Oh, and new update, a few update for other guns too, is that the range is decreased. Server Bryson 800 from Modern Warfare 2, and I used its real name, 2019 Modern Warfare. So
Show
it's
the
not going to be
reload.
like video game, you know, get it right. But still, let's talk about grenades now. Yeah. Yes, I added a new shotgun. You can both do the pump action in not aiming and in aiming. This is the side load. If it's
I don't know
empty,
what
side
what I
load
was on
and
back then. Look at this. Look at
if
this
I hold right
animation.
click, it will cancel.
You can cancel
So,
the
there's
animation
that.
too.
If you aim, the spread will be
Oh, this is
less.
too good.
If you not aim,
Oh, I miss those
it will
days.
spread more. And every shot is 6 bullets. It shoots 6 bullets per shot.
Oh man,
29.
look at this. It's too good. Oh my gosh, what now? I think that's it. I think that's everything I made back then. It was too good, but then I lost everything, sadly. Oh my gosh, I was like addicted. I didn't play COD back then, I just watched people play it. You were probably on art enhancing steroids. What do you mean? I was coding.
Hey everyone, what
I was just coding stuff.
yeah,
Look at
that's
this.
what
Guns in Minecraft.
kept me
I don't know what happened to me back then. I was too enthusiastic with coding. But then I had to go back to study.
you're heading into?
So, it's sad that I cannot download this anymore.
If you hit a wall, you will slide.
Well, it's time to let go. Don't worry guys. After I finish this computer science course, I'll be able to make another one. Don't worry guys. Just stay with me, okay? Oh no, my keyboard doesn't work no more. Yes, what? What's wrong with my keyboard? Da-da-da-da-da. Yes, I mean, you need to animate as well. Oh yeah, but still, it's funny how like back then. I mean, I don't know what happened back then. I mean, it was something, you know. I don't know. Connect, please. Oh my goodness. Please connect. Wow. It doesn't connect. Oh, what the hell, man. It was something. Yeah, something, bro. It was drugs in the world. I don't know, man. Apparently it doesn't connect anymore. For some reason. It said connected, but it doesn't work. What the heck? What do you mean, hold on?
Common paradigm when iterating over a linked list and you're using some temporary variable like pointer,
Nah, I ain't doing
you
that.
can simply set pointer equal to pointer next. And what that means here is as follows. If this is pointer, pointing from here down to here. Pointer next is follow the arrow, grab the next field. So if you set pointer equal to this thing, that's the same thing as pointing this at this same box. And indeed, if I'm
just gonna use
advance
fingers
to the next slide, even though the arrows are
select
technically
stuff
pointing
now.
at different parts of the rectangles, that's just for graphics sake, pointer is now pointing at the second node. And when I do this again on my next iteration, it points at this. And then this last step, notice, when I keep doing pointer equals pointer next, this will become eventually this value. But what's this value in this linked list?
Oh, it works
It's
now.
null, technically. So this arrow will eventually take on this value when I set pointer equal to pointer next. And at that point, PTR, my temporary pointer, is going to be null. So it might as well look like this pictorially. And what does that mean for my loop? Once pointer is null,
sucks.
you've walked off the end of...
Hey man, unless you're enthusiast about it. I feel I did not had a laptop back then, but the pile of sketches from these days pale in comparison to those. Really? Maybe it's the sketchbook that is something. Can you really learn coding and animate at the same time? I mean, I can. It's like animating doesn't use much brain power. Learning computer science does use a bit more power, so it's really balanced out, I guess, hopefully. Let me get some water, you know, drink some water, eh?
It's 12. Ăn gì đi, ăn đi.
Go. Anyway.
of the linked list, what's going to be true of this loop here, started in line 32?
32? Oh yeah, we're just going to search, iterate to through the linked list, I guess.
Any observations here? What's going to be true? What will happen now as soon as we hit the end of the list? Yeah, sorry. The loop is going to break out. Why? Because line 32, which is constantly asking, while pointer does not equal null, well, if pointer finally equals null 3 steps later, the while loop is now done. And so what I can do at the end of this program, once I've printed out those values, well, first let's go ahead and open my terminal window. Let's make list. OK, a compile /list, and let me try the same values, 1 and 2 and 3. That's going to, again, allocate 1 node, 2 node, 3 nodes by prepending each of those values, and it's then going to iterate over them from left to right. And so when I hit enter now, what should I see on the screen if my code is correct?
3, 2, 1.
What will I see if I were to just call it out?
3, 2, 1. 3, 2, and
2,
1.
1, because I've prepended presumably. And here we
Okay,
go.
see ya,
I
Natuk.
indeed see 3, 2, 1. So the list is backwards, but all of the elements are there. Now, technically, if I ran Valgrind on this, Valgrind would not be happy because I have never freed any of my memory. So I should probably now have a second loop here that does something like this. Let me again set pointer equal to list. I don't need to redeclare it because I've already created this thing on line 31. I just want to reset it to be the beginning of the list again. And now I can do the same kind of thing. While PTR not equals null, go ahead and do this. Well, I don't want to just do free pointer and then do pointer gets pointer next. Why? My goal is to free all of my memory, but I think this is going to get me in trouble. Pointer equals list just gives me a temporary pointer that points at the 3, and then eventually the 2, and then the 1. How? Well, while pointer not equal null, I'm freeing the pointer. So this is like saying to malloc, free that node, free that node, free that node. But what's the problem with what I've just done here?
Free next. Oh, because if you free it, it's already gone, so there will be no next. The value of next will be not there, so you cannot go through the next one. So basically you have to free the number first, then you go to the next one to, like, I don't know. So okay, basically you don't free it first because it's gonna free the number, I mean the next one to, I don't know.
This code is technically buggy, yeah. Exactly. After you call free on pointer, you are, by social contract with C, not allowed to touch pointer anymore. It is invalid. Now, it's still going to be a number, it's still going to be a pattern of bits, but it's invalid. And you'll very often get a segmentation fault if you tempt fate in that way. So I can't free the pointer and then use it literally the next line. The solution
So I have to, you have to go to there and then use looking at X. What?
Like our swapping of the liquids last time was to maybe just have a temporary variable. So I can do a switcheroo. And so a common way to solve this problem to get the order of operations right would be to do something like this. Give yourself a temporary pointer like node star next. Set it equal to the place you want to go next. So
looking at X. Which X? What X?
One step ahead. Now you can free pointer. And then you can update pointer to be that next value. So essentially, you need like two hands now. You create on line 41 another pointer that if this is pointing at the first node, the 3, your new pointer is pointing at the 2 temporarily. So now you can tell malloc via free, release this memory, but I haven't forgotten where I want to go next. And so I can now continue on. So a common paradigm for just iterating over these nodes and then freeing them. A couple of observations. Strictly speaking, I could have consolidated this. I don't need 2 loops to print the nodes and then free the nodes. I could do that all at once, but let's assume that there's other stuff of interest in my program, and I don't want to just immediately free it. There's one other bug that I should probably address here. There is still a potential memory leak up here, and this one is super subtle, though Valgrind would help you find it. Notice that in this loop here, when I'm calling malloc, this line of code is fine if the first line of malloc fails and returns null. I immediately return it.
Okay. I do not recommend you go on there, but whatever. It's your choice. I'm not gonna stop you. But it's... if something happens, it's your responsibility. Don't tell me, okay? If you go there, why would you want to tell me that you go there, huh? What's your intention on telling me that, huh? Look at his alt. Oh my gosh. Dude, she's 9. Oh my gosh. The frick, Ginger Ale. You are an irresponsible person. You're too late, man.
And I'm done. But what if the second call, but not the first, or the third call, but not the first or second fail? This line of code has me returning immediately. You really need to do some garbage collection, so to speak, whereby you really need to go in and free any nodes that you did allocate successfully earlier. Honestly, that's going to be a pain in the neck. We won't do that here. But probably what I'd want to do is write a function called freeList or something like that, and call that function to free any nodes I had previously created. So it's not quite at the finish line, but the building blocks are indeed here. Questions on this code? And I think it's safe for me to promise that it won't escalate further from that. Questions on this? No? Well, let me show you one alternative that you might prefer. And I'm pretty sure this isn't an escalation. It's just an alternative formulation. Another way you can iterate over nodes in a list could be this. Instead of a while loop, for instance, let me actually show you one other piece of syntax here. You could technically use a for loop. You could give yourself a node pointer here that is initialized to the list. You can then check in your for loop that it's not equal to null. And then you can do your update as usual like this. Either of these are equivalent, even though this one I suspect looks scarier. It's doing the exact same thing one line instead of two, but there's no reason we can't use for loops instead of while loops to achieve the same idea. But I'll leave these two as demonstrations of one approach or the other. But that's just like in week one, for loops, while loops, whatever looks simpler to you, even though admittedly neither of these probably looks super clean. All right, so let's take things back to things more conceptual here. Up until now, we've been inserting elements into this linked list by prepending them. Let's consider what the running time then is of these operations. So if I've got a linked list of size 3 or size n more generally, time has passed and I've added a lot of things to it, what's going to be the running time, for instance, of searching a linked list for some value? And I'll tell you already, it's not log n, because again, binary search is off the table, as per before break. So what might the running time be of searching a linked list for some value, like 2 or 3 or 1 or 50? What might the running time be? Oh, O of, I heard it over here, O of n and y. Who was that? Oh, in the middle here? Why O of n? Exactly. You're going to have to go through every item in the list, starting from the left, from the beginning, which is how we've been drawing things and connecting the dots. And in the worst case, the element might very well be at the very end, so it's going to be big O of n. What about insertion? How many steps in terms of big O notation has it been taking me to insert elements into the linked list using this prepend design? Yeah, so it's technically constant time, big O of 1. And again, 1 is just representative of any constant. It could technically be 2 steps or 3 steps or even 10 steps or 100 steps. But if it's always finite and fixed, then indeed you can say it's in big O of 1. Now, why is that? Well, again, no matter how long this list gets, so long as there's memory available for me, I can just kind of create a little splice at the beginning of the list to put in the new node, update the original list, and I'm on my way. And it keeps getting longer, even though it might not be spread out in memory. So big O of 1 is possible with these linked lists if I indeed prepend things. Of course, if I prepend things, everything's going to get out of order, potentially. And we're going to have maybe the stack property instead of a queue property. So we might want to do things slightly differently. So instead of doing this, whereby we kept prepending, suppose we append to the end of the list instead. So if we now insert the 1, the 2, and the 3, as we might want to for a queue, to maintain that fairness property,
Hopefully you
we might
are
start with an empty
normal.
list. We might add the 1. We might append the 2, append the 3, and so it just is sort of laid out differently in memory. And again, if I can come to you in the middle, what's the running time of search? Again, when the linked list uses this append implementation. Yeah, still big O of n, because in the worst case, you're going to have to go through the whole list just to find it. And notice, it doesn't matter if you have an intuition now that the bigger numbers might very well be at the end. You have no way to jump to the end. You have no way to jump to the middle or do anything resembling binary search. Every search has to start from the left and follow the arrows again and again. All right, so I don't think we've done any better there. And in fact, what is insertion's running time now in big O? When we're appending to the list in this way, as we might to implement a queue instead of a stack. What's the running time of inserting a new value?
N?
Big O of?
N.
So not big O of 1 in this case, but big O of?
N.
N, because if I'm appending, by definition, I have to start here and traverse the whole thing looking for the end. Now, this is a bit of an overstatement, right? You could obviously optimize this slightly by maybe adding another variable that always points to the last element, sort of a cheat sheet, a shortcut that gets you all the way to the end. That's
just
totally
got here.
fine. It doesn't really fit the traditional definition of a singly linked list, but there's absolutely smart engineering solutions to these kinds of problems. But as designed, it would indeed be big O of n to insert to if you've got to go all the way to the end and you're not using a little extra memory to get yourself there quickly. Well, what if we want to take things one last step and not just append blindly? Because even though I inserted 1, 2, 3, if I inserted them in random order, they would end up in random order. What if you want to maintain a sorted list from smallest to largest? Well, then you might want to insert numbers like this. Starting from an empty list, we might have a 2. Then we might try inserting a 1, but we want to keep it sorted. So now we're going to prepend in our code. But then you might want to insert a 4. So you would append the 4, because you're probably going to look for the right spot to insert it. Then we're going to insert a 3. And this one's getting a little annoying, because now you have to like iterate over the list, look for the right spot, and then do a little smarter of a splice. But it's possible.
What do you mean, like, for ADHD? I mean, this is computer science, who's gonna sit here and watch me watch
you're
computer
probably
science?
Gonna look for the right spot to
Do I
insert
know
it.
San?
Then we're gonna insert a 3, and this one's
You
getting a
San,
little
no.
annoying because now you have to
I
like
do not know.
iterate
I know
over
the
list,
normal.
look for the right spot, and then do a little smarter of a splice, but it's possible, but you don't want to orphan the 4, for instance, and then ultimately we get back to this question. What would the performance be of your linked list if you're trying to maintain sorted order? Well, search.
Okay, sorted order will take like n squared, probably. But it could be log of n.
It's going to be big O of n for the same reasons as before. What about insertion? Big O of what?
Insertion
For
sorts?
inserting into a sorted linked
It was.
list.
I think it would be n.
Yeah, in the worst case? Yeah, it's still big O of n. So it's no worse than,
Right, yeah.
it's not really any better than appending, but we gain the additional property of maintaining a sorted list, which might very well be useful if you're sorting your contacts in your phone or something like that, where it just makes sense to maintain sorted order. Now, in the code for online today, if you take a look at some of the final versions of code, like list6.c and list5.c, as we'll post on the website, you can actually see code that will solve all 3 of these problems. The prepend version that we wrote live, the append version, which we talked through, as well as this sorted order one, but I think I'll avoid showing it live just because I do think that starts to escalate quickly. But I think we have enough of a building block if we're comfortable with prepending to at least solve some real-world problems with these linked lists. Questions then on linked lists, which we'll now leave behind on their own, but now use this technique to solve fancier problems, but much less code. Questions on linked lists? All right, so to recap, we've kind of taken a sidestep with linked lists. Like, we have this dynamism now where we can grow and shrink our chunks of memory without over-allocating or accidentally under-allocating, as in the world of an array. We don't have to worry about copying values endlessly, because once you allocate the node, it can just stay wherever it is in memory, and you can just maintain, you can just stitch it together somehow. But unfortunately, we've sacrificed what we started the class with in week 0, which was like binary search, divide and conquer, which was like gave us that log n running time, which was really compelling if you think back to the demonstrations and the visuals. Can we get the best of both worlds? Can we get the sort of speed of binary search, something logarithmic, but the dynamism of something like a linked list? Well, we can actually.
This is a lot for you to take in. You started playing Deltarune. I don't know what that game is, sadly.
I think if we start to think not in a single dimension, just the x-axis, if you will, but 2 dimensions, such that our data structures can maybe now have width and height, if you will. And so a tree is perhaps the right term here, much like a family tree. If you have sort of your elders up here in the tree and then the branches below them for their children and grandchildren and the like, that's actually what a computer scientist means when they talk about trees. Not a tree that grows up like this, but really one that typically is depicted growing down, although this is just an artist's depiction no matter what. But there are certain types of trees in the world called binary search trees that are structured on paper and visually like a family tree, but they have a special property that lends themselves to exactly that feature.
Damn, that's a lot of data structures.
Binary search. So for instance, here is an array back from week 2, and I've sorted a whole bunch of numbers herein from 1 to 7. We know we can do binary search on this structure if it's implemented as an array, but what feature do arrays, to be clear, not have that linked lists do? Today's kind of a seesaw. Like, what did we just gain by adding linked lists that arrays do not allow?
The dynamic.
Yeah, you can insert more elements without having to copy or moving everything else around. Like right now in this single dimension, if these values to the left and or right are already used, then you have to move everything. And that's where we started today's story. So arrays kind of paint you into a corner because you have to, by definition, decide in advance how big they are. Well, couldn't we have some kind of array that can still grow but still is contiguous so we can do binary search in some way? Well, yes, if we sort of rethink how we implement binary search. Let me propose that I've chosen these 7 elements in the array, much like the lockers from week 2, to be ordered from smallest to largest. I've highlighted now in yellow the middle element here. And if we were telling the story of week 2 going left or going right, let me highlight in red the middle elements of the left half and the right half. And then let me further highlight in green the other elements in between those. And there's actually a pattern here, as you might notice, whereby there's 1 yellow in the middle, and then there's the 2 red and the 4 green. There's kind of an implicit structure there, if you will. And what if I do start to think in 2 dimensions, and instead of laying out an array of lockers like this on the x-axis only, what if I kind of like slide the 4 up and pull the 1, the 3, the 5 down, and kind of draw this in 2 dimensions instead?
Roots.
Well, let me do that.
Yeah, it's roots.
As by separating these things like this, such that now let me propose that each of these squares, maybe it doesn't have to be contiguous. It can be anywhere in the computer's memory. But I can't have these crazy gaps among them. How could I perhaps keep these things connected conceptually? What should I add to the picture, if you will?
Binary search, huh?
Yeah. Say again? So branches, metaphorically here, and more technically in the language of C, maybe just some arrows, some pointers. So I won't bother drawing things as rectangles constantly. Let me propose that we're now just abstracting away what a node is. But let me claim that each of these squares now is a node. And a node might have a number, but it might also have a pointer. Heck, maybe even 2 or more pointers. And let me draw those now. I don't care about addresses like 0x1, 2, 3, 4, 5, 6, 7, 8, 9 anymore. Let's just draw our pointers with arrows. But now let me propose that we could very well think about this as a tree storing what was previously array data, but now each of these nodes can be anywhere in memory. And moreover, even though I've kind of painted myself into a corner visually on the screen, so long as there's more memory in the computer, I could put the number 0 over here. I could put the number 8 over here. And if I'm smart, I could probably...
This is a Harvard level knowledge.
If I want to insert other numbers like 2.5 or 1.5 or values in between, you know, I bet we could kind of make room by swiveling things around and just kind of hanging things off of these branches slightly differently. And so what does this gain me? Well, if I instead start to model my data not single dimensionally, but in 2 dimensions, and I connect those nodes with these pointers, what can I now do? I think I just gave myself back binary search. Why? Suppose I'm searching for the number 5. How do I find it? Well, just like in a family tree where you might visually start reading from top to bottom, I'm always going to start from the so-called root of a binary search tree. This is just like the list pointer that kicks off the whole linked list process. This is the so-called root. All right, here I am at the number 4. I want to find the number 5. What decision can I make when I see that I'm currently at the number 4? Just like the phone book from week 0. Where is 5 not? It's not to the left. And if I had built a little mobile here or something, we could very dramatically snip off this branch. This is like very low budget animation. These nodes could like fall to the ground, and we're left with half of essentially a tree. But what do I now know? It's obviously the 5 to the right. So let me go to the right. 6 is obviously not the one I'm looking for. But what do I now know about the 5? Well, 5 is less than the 6.
Makes
so
so
I can
much
sort of
sense now.
snip this off here because I know it's not going to be down there, and I can follow the
Whoever
remaining
thought
arrow
of
here,
this
and
was
voila, I just found it.
crazy.
And now, without getting into the weeds of the math, I've got here, 7 elements. That's roughly 8 if I round up. And if I do some log base 2, I actually, 1, 2, 3 is the key detail here. The height of this tree is 3 because I took a list of size 7 and I halved it and I halved it in order to let it dangle in these 2 dimensions, plus or minus 1 for rounding's sake. So what do I get back? I now have binary search, but it's not like the middle of the middle of the middle. I now follow these arrows in one of 2 directions. So each of these nodes now has an int and maybe a left pointer and a right pointer. But you can call them anything you want. And so I've gotten back binary search and dynamism, because if you want to add 0 or 8 or 9 or 10, we can just dangle them at the bottom of the binary search tree. So what would this look like in code, but we won't actually implement it?
Dude, I can't. Oh, it's your fault, man.
Well, here.
And if she's gonna check it or not, it's her fault, man. It's not my fault for posting it. My goodness gracious.
Was previously our definition of a node for a linked list, which was one-dimensional.
Why are you sorry
if you will.
me? It's not my responsibility. Oh my gosh.
No, it might bounce up and down on the screen. It was still just a line, if you will. Well, let me get rid of the single pointer in the linked list. Let me make a little bit of room here in this typedef, and let me propose that we just add 2 pointers, each of which is a struct node star. One will be called left by convention, one will be called right by convention. And so long as someone, not me, not today, not in class, writes the code that stitches together this data structure too, handling both the left child and the right child, so to speak, I think we can indeed stitch together that 2-dimensional structure. And moreover, once you have this in memory, you can translate pretty elegantly to code binary search itself using a principle we talked about recently too. Here is, for instance, a function that I'll write by just clicking through steps called search, whose purpose in life is to return a Boolean, true or false. The number I'm looking for is in the tree. This search function, therefore, takes 2 arguments. The number I'm looking for, called number, and then a pointer to the tree, the so-called root of the tree. Now, how can I implement binary search in code? Well, recall our brief discussion of recursion. It turns out recursion is a beautiful technique, and honestly, more obvious technique when you have 2-dimensional structures, which finally, after 5+ weeks, we now do. Here's maybe my first line of code here. If the tree is null, then obviously return false. You've handed me an empty tree. There's nothing going on. Obviously, the number you're looking for is not going to be here. So that's my maybe whose purpose together.
Wait a minute.
One will be called right by convention. And so long as someone, not me, not today, not in class, writes the code that stitches together this data structure too, handling both the left child and the right child, so to speak, I think we can indeed stitch together that 2-dimensional structure. And moreover, once you have this in memory, you can translate pretty elegantly to code binary search itself using a principle we talked about recently too. Here is, for instance, a function that I'll write by just clicking through steps called search, whose purpose in life is to return a Boolean, true or false. The number I'm looking for is in the tree. This search function, therefore, takes 2 arguments. The number I'm looking for, called number, and then a pointer to the tree, the so-called root of the tree. Now, how can I implement binary search in code? Well, recall our brief discussion of recursion. It turns out recursion is a beautiful technique, and honestly, more obvious technique when you have 2-dimensional structures, which finally, after 5+ weeks, we now do. Here's maybe my first line of code here. If the tree is not
What is this nightmare combo? You down for Roblox? Nah, I don't play Roblox.
then obviously return false. You've handed me an empty tree. There's nothing going on. Obviously, the number you're looking for is not going to be here. So that's my safe base case to make sure I don't screw up and recurse infinitely. Well, what else might be the case? Well, if the number I'm looking for is less than the tree's own number. And now recall that tree is a node star. So even though I'm calling it a tree, it's really the current node that's been passed in. So if the number I'm looking for is less than the current node's number, then I must know that the number I'm looking for is to the left, so to speak. So how can I solve that? Well, this is where the magic of recursion. Just return whatever the answer is to calling search again, but on a subtree, if you will. This is the sort of equivalent of snipping off half of the tree. Pass in the left subtree, if you will, with the same number. Else, if the number you're looking for isn't less than the current node's number, but greater than, snip off the other subtree instead and just return whatever search says it finds in the right subtree here. And then there's a fourth and final case. What else could be true logically? Yeah. Perfect. If the number you're looking for equals the number in this node, then I'm just going to return true. And you might recall from our recurring discussions of design, I don't strictly need to ask that explicitly. Either there's no node, it's to the left, it's to the right, or you found it. So I can just whittle that down as usual to an else. And this now returns my true. So here too, this is where recursion, once you get comfy with it, sort of gets pretty elegant and cool in the sense that, wow, even though there's a lot of lines here, I mean, there's only a few interesting lines. A lot of it's like curly braces at that, which strictly speaking I could get rid of. And so recursion lends itself to elegance when it comes to traversing these 2-dimensional data structures as well. So that is in code how you might implement something like search. questions then on these trees? We have dynamism. We can insert more nodes to them. They're faster because we get binary search back. But, there's got to be a price paid. Any downsides or question or downside? OK, let me come back to that in just one sec. Downside, though, what price have we paid for this dynamism and for this binary searchability? Even though I've abstracted it away in the picture. Say again? We're using a lot of memory, right? I'm kind of misleading you now because I'm just drawing these little squares with the simple numbers, but there's actually 3 things in there: a 4-byte integer, an 8-byte left pointer, a 8-byte right pointer. So we're already up to 20 bytes now to store individual ints. That's probably OK, though, if memory is relatively cheap and voluminous as it nowadays is. But these are the kinds of trade-offs. And here, too, you see a hint of why some people still do like and use C. And in fact, it's so omnipresent because when you have C, you can really fine-tune how much memory is being used, for better or for worse, under the hood. As we transition soon to Python, these decisions get made for you. And you have much, much less control about how much memory is being used by your program because someone else made those design decisions for you. Question? Is it bad if we don't know the parent node? Not necessarily. There's no reason why you need to have pointers in both directions. However, that can lend itself to efficiency. By spending more space and having arrows go up too, you can actually save more time when searching the tree in other contexts. This, though, would be the canonical way, the typical way to implement it. But absolutely, just like a doubly linked list, that could help you solve other problems too. All right, so turns out I'm kind of overselling binary search trees. There are perversions of them, so to speak, whereby they won't actually behave as advertised. For instance, here's a good situation. Suppose you've got an empty tree initially, and you insert the number 2. Well, it's got to go somewhere, so it might as well become the root of this binary search tree. And let's assume that someone wrote the code to do this. Now you want to insert the number 1, and you want to maintain the searchability of this tree. Well, it's important to note that binary search tree is different from tree.
I think
if you just got a tree in memory.
I think this thing is messing with my mic or something. System. Performance, memory saver. Optimal period of time. There's something about this. Continue background app. Brave is closed. Close window when closing last tab. There's something about this app. You know what? Screw you. I don't need the memory saver. It feels like the memory saver is hurting my computer.
There is no social contract with where the numbers need to go. They can be completely random.
Okay, and now I lost it. I lost where he was.
Actually behave as advertised. For instance, here's a good situation. Suppose you've got an empty tree initially, and you insert the number 2. Well, it's got to go somewhere, so it might as well become the root of this binary search tree. And let's assume that someone wrote the code to do this. Now you want to insert the number 1, and you want to maintain the searchability of this tree. Well, it's important to note that binary search tree is different from tree. If you've just got a tree in memory, there is no social contract with where the numbers need to go. They can be completely random all over the place. Binary search tree means that you can do binary search. Means that any node here is going to be greater than every node here and less than every node here. And that's a definition. It's a recursive structural definition that must be true to be a binary search tree, or BST. So if we maintain that property ourselves, let me insert 2. Let me insert 1. 1 belongs there by that definition. Let me insert 3. 3 belongs there by that definition. But I kind of got lucky in that I, in the story, inserted 2, and then 1, and then 3. Let me propose a sort of perversion of the algorithm whereby we just get unlucky. Let me propose that we insert 1 first. And then we insert 2. Well, where does 2 go? Well, logically, it goes to the right because it's larger. All right, now the user inserts 3. Where does it go? OK, it goes there, logically. And how does this story unfold? The user inserts 4, 5, 6. It's wonderfully sorted in advance by luck. But this is a perversion of the structure in what sense? It's still technically a binary search tree. But what does it look more like? It really is devolving, if you will, into a linked list. And so if you, the programmer, don't implement a binary search tree with some kind of repairs going on, such that as soon as something gets, whoa, a little too long and stringy, I think I can fix this. It's going to be an annoying line, a number of lines of code, which we're not going to write here or in a pset. But we could kind of pivot this thing, right? And we could just rejigger things so that the 2 becomes the new root, the 1 becomes the left child, the 3 becomes the right child. But that's what, like 2, 3 plus lines of code. It's possible, it's doable, but it's extra work, it's extra code. So unless you write that code, though, and maintain balance of these trees, just because it's a binary search tree does not mean its height is going to be log base 2 of n. The height could be n, in which case you don't get those properties. So when it comes to looking up in a balanced binary search tree, yes, it's log n. But if it's unbalanced, if you don't add that additional logic and those repairs, so to speak, it could devolve into big O of n. And this is a whole category of algorithms and fanciness that you would explore in a higher level course on algorithms and data structures. There's lots of way to do that sort of fixing that I'm alluding to in the picture there on the screen. All right, a few other data structures, if you will, toward an end of a sort of computer science holy grail. So log n is repeatedly a really good place to end up. We started in week 0 when we got log n. We lost it earlier today by introducing linked list, but we just got it back, albeit at the price of spending more space. But the holy grail, so to speak, when it comes to algorithms would not be big O of n, certainly. Definitely not n squared, like our bubble sorts and selection sorts, and not even big O of log n. What's better than all of those? It's big O of 1, constant time, right? That's the holy grail, because if we could store huge amounts of data but find it instantly in 1 step, or 2 steps, or heck, even 10 or 20 steps, but independent of the size of the data structure, that's pretty powerful. I mean, that's the secret sauce of the Googles and the Twitters of the world, trying to get back results really, really fast. Well, it turns out another abstract data type or abstract data structure might be something called a dictionary, just like the Merriam-Webster or Oxford English dictionaries that you might know, which associate, say, words with definitions. Well, you can think of a dictionary really abstractly as this, like 2 columns, maybe on a spreadsheet of sorts, where the left column represents something and the right column represents something else, like the word is on the left and its definition is on the right. And that's almost literally what a dictionary is on paper. You've got all the words and all the definitions right next to it. But more generally, in computing, a dictionary really just has not words and definitions per se, but key value pairs. This is a term of art, and we're going to see this again and again, especially as we transition to web programming, keys and values. Key is what you use to look for something. The value is what you find ultimately via that key. So that's the generic term there. We've seen key value pairs really in the past. In week 0, we talked about your contacts in your iPhone or Android phone being an app that has a whole bunch of contacts, presumably alphabetized by first name or last name or the like. Well, one of those contact cards ultimately has someone's number, for instance, like John Harvard in this case. So in that type of application, the keys is the name, like John Harvard, that you use to find information, and the value is the number that you find there. Or if there's more information, like where he lives and email address and the like, the whole contact card could be the value thereof. The key is what you use to look up John Harvard. Now, back in week 0, and rather, the corresponding table then, if we draw this in 2 columns, wouldn't be word and definition or key value generically. It would be name and number, for instance. So we're just slapping some new terminology on this old contacts problem. Well, this is the picture we drew way back in week 0, whereby I claimed that log of n was really, really good. And indeed it was, and has been since. But the holy grail would indeed be something more like this, in this dashed green line, constant time. And maybe not literally 1 step, but a fixed number of steps that even as the problem gets huge and you go way, way out on the right of the x-axis, the problem does not depend on the the time to solve the problem does not depend at all on the size of the problem itself. You can have 1,000 contacts or 100,000 contacts. Constant time means it takes the same number of steps no matter what. Well, how can we get to that point? Well, there's a couple of final building blocks today, and there's one called hashing. And this is something that will recur a few times, but for now, hashing is all about taking as input some value and outputting a simpler version thereof. So for instance, here's a gratuitously large deck of cards, which are all the more visible as a result. And in a deck of cards, typically you've got like, what, 52 cards, plus maybe the jokers and whatnot. And each of those cards has a number of sorts and a suit on it. And here are literally 4 buckets on the stage. And how might I go about sorting these cards? Not just by number, but also by suit. Well, you could certainly like spread them all out and sort of make a mess of things and just kind of reason your way through it and get everything in order according to suit and ordered by number. But most of us, even if you don't have 4 buckets at home, probably are going to do something a little more intuitive, feels like an optimization, where if I find like the 9 of hearts, I'm going to put that into the hearts bucket. The king of spades, I'm going to put that into the spades bucket. The jack of diamonds over here. And I'll do this with the queen of diamonds and the ace of clubs here and the 3 here and the 10 here. And even though it's still going to be 52 steps, why am I, and maybe at home, like why would you perhaps do this step first? What's the value of bucketizing the values in this way? And that actually is kind of a term of art. What's the value of doing this first before you sift through and try to sort the numbers? Yeah? Yeah, it's easier to make sure you're not missing anything, and it's taking a problem of size 52 and shrinking it into 4 problems of size 13, if you will. And so that just kind of helps simplify things, maybe reduces the probability of errors or the like. And what I'm doing here, to give it a technical term, is that I'm hashing the values. I'm taking as input a card like this, and I'm reducing it more simply from a larger domain to a much smaller range, if you will. So here's a domain of like 52 possibilities. I want to map that to a range of 4 possible outcomes: the diamonds, the clubs, the hearts, or the spades here. And by doing that, I'm just shrinking the size of the problem. So hashing does that. It's like literally an f of x type arrangement.
I cannot see, it's too small.
And you get back a simpler known value. Well, a hash function, more technically, is the algorithm or even the math or even the code that you pass the size of the problem, and you is the algorithm or even the math or even the code that implements that idea, converting something bigger to something smaller to this indeed finite range of values. And it turns out that hash tables are a wonderful application of arrays and linked lists to try to leverage the best of both worlds. The goal being theoretically to achieve that holy grail of constant time, and that's going to be a bit of an overstatement because you're not always going to achieve it exactly, but at least we can get a little closer there too. So with hash tables, you have something that looks like this. This is just an array. This is an artist's rendition of drawing it vertically instead of horizontally, but that's just a detail graphically. And this array, for instance, maybe is of size 26. And where am I going with this? Well, how does Apple, how does Google store your contacts alphabetically in your phone and search for things quickly? Well, they probably alphabetize, at least in English, according to A through Z. Or if we convert that to numbers, it's like, what, 65 through whatever, or really 0 through 25. So suffices. If we're using an array of size 26, we start counting at 0 and we count up to 25. But let's abstract that away as just letters of the alphabet. So maybe what Google and Apple are doing in your phone is storing all of the A's up there, all of the Z's down there, and everything else in between. And so this works pretty well if you start adding your friends and your family. So for instance, and I'll get rid of the letters so as to not distract, Albus might go in that first spot because A, you subtract the 65, maps to 0, so we put him in the first bucket, the A bucket. Maybe Zacharias ends up all the way at the end there, and then in the middle might be Hermione. And if you do this ... you keep adding all of your classmates, you might get a contacts database that has all of this data herein. Now, each of these nodes, they're drawn differently because this is just another artist's rendition. These rectangles, these long rectangles, represent a contact card, like John Harvard's that's got the name, maybe email, definitely phone number, and things like that. So this seems great. Why? How can I find Albus? Well, I go to the A bucket. How do I find Zacharias? I go to the Z bucket. How do I find Hermione? I go to the H bucket. But, I've done this very deliberately. What problem will arise eventually, assuming you have enough classmates?
Person with the same name,
yeah,
or like
too many people, too many contacts for all of the available spaces in the array. There's still some room here, but I'm pretty sure if I think back to this particular class, we've got not Hermione, but also Harry, who's also an H, Hagrid, who's also an H. So where do I put them? I could just put them arbitrarily in any of the open spots, but then you lose the immediacy of jumping right to the H, right to the A, right to the Z. But now that we have linked lists, we can kind of combine these ideas, right? Use an array to get to the first letter of the name you care about. And then if you have a collision, so to speak, whereby someone's already there, you don't do something stupid like put Harry down here just because it's available, or maybe Hagrid down here just because it's available, because then you're losing the immediacy of the
I just
lookup.
posted in the server.
Why don't you just kind
Okay.
of stitch them together in a linked list? Now, what does this mean?
Oh,
This
okay.
means for most of the characters here, you have constant time lookup. You look up Albus, boom, you're done. Zacharias, boom, you're done. Okay, Harry, Hermione, Hagrid, it might be 1, 2, or 3 steps. So that's actually devolving into something linear. But here we make a distinction today between theoretical running times, which we keep talking about, and honestly, clock on the wall running times that actual humans care about. This is way faster than a linked list because you don't have to search every name. It's even faster than an array because you don't need to do binary search. You can literally, for most of the names, find them in constant time, 1 step. And again, it's not theoretically constant because if you only befriend people who have H names, it's going to be a crazy long linked list anyway. So again, it really kind of depends on what the nature of the data is here, but this is pretty close to constant time. And in fact, how could we get even closer? How could we reduce the probability of collisions for the H's or any other letters? How could we avoid putting too many H names together? Say a little louder. Okay, yeah, so we could add another dimension, if you will, but let's not add a third dimension per se, but let's indeed look at not just the first letter of everyone's name, but the first and the second. And in fact, let's see if that gets us a little further along. So let me go ahead and propose, if you go through the whole Harry Potter universe, there's actually a lot of collisions if we keep going. And so we've got the L's here, the R's, the S's, and so forth. Well, let's clean this up here. Hermione originally went to the H location, but let's decrease the probability of collisions there and everywhere else. Instead of putting Hermione, Harry, and Hagrid all together, let's go ahead and do this instead. Instead of labeling these buckets A through Z, let's just give ourselves more buckets. So in fact, this might be H. Well, instead of H, maybe this should be HA. And then this should be HB, HC, HD, HE, HF. Now, some of those are a little nonsensical because I can't think of names that match most of those. But it's deterministic. At least we know the bucket will be there, which is important even if it's empty. And now we can put Hermione here. We can put Harry here. But uh-oh, we didn't do this perfectly well. Hagrid still collides. So let me come back to you. How can we reduce the probability of Harry and Hagrid colliding? Yeah, so we could look at the third letter. OK, so let me try that. Instead of HA, let's look at HAA, HAB, HAC, dot, 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 HAQ, dot, 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 HEQ, HER, HES, and so forth. And now I think those names, and probably all of the others we saw, are now much more cleanly distributed. There's much lower probability of collisions unless two people have like almost the same.
It's there. Okay, let me see. Oh, I see. Yes. Oh, okay. I see the problem here. You should make like the lines a little bit brighter, you know? Because look at this. If you look at it from afar, you cannot see the lines. You can barely see it. This guy, it looks good because of the contrast, because it's clear. And yeah, this one is a bit. The lines here is a bit dark. You can make it a little lighter. Okay, secondly, why is the thumb inside? Shouldn't it be outside if you're doing this pose? The thumb should always be outside. If it's pointing, you know, facing up. The palm side is facing up. No, but overall it looks very cool, you know. I like the pose. I don't know why this guy is like this, but yeah, I guess. You can try to make your head a little more 3D, but if it's your style, I'm not gonna say much. This guy's circle. I mean, yeah, but it's not gonna stick right out like this. There should be a little bit of face the cam. Okay. So Okay, if it's like that, then this circle head guys are kind of weird. Okay, if you look here, okay, look at my demonstration. If the neck points up like this in this type of, for example, perspective, per se, I don't know, right? His head would, if he point like that, his head should be something like this. You see the overlapping here? See if his head like this, it looks more 3D. But if you say he always look at the camera, it should move it a little bit down to face the camera, like so. You lazy? Okay, yeah. I mean, I'm just saying, man. Oh no, I messed up. Oh, I did it. Okay, yeah, I'm just saying, man. But yeah, you can just change the lines inside of this character to be a little bit lighter. It doesn't have to be completely white, just a little bit lighter, so there's a bit of contrast, you know, so it's easier to see the muscle and stuff. But yeah, overall it's very cool, I guess. And again, why is the thumb from the... Okay, the thumb's fine. But yeah, I don't know. the thumb here is kind of bugging me, I don't know.
Names, or one is like a prefix of the other, but even though we're now closer than ever to constant time, because the odds that we hit a collision and have to devolve to a linked list are much lower, what's the downside that's not completely obvious from how I've depicted this on screen?
Memory.
What's the price I'm paying here? Yeah. This is a huge amount of memory. The number of cells here in the array is now, what, 26 times 26 times 26 for the first, the second, and the third possible characters, all combinatorically combined here. That's a lot. I didn't even draw them. I have the ... to evoke that instead. That's a huge amount of memory. This is a very sparse data set now, and odds are you're going to waste so much memory, even for the names like HAE, HA, like HEQ. Like, I can't even think of names. So many of those buckets are going to be empty, not to mention the AAA and the ZZZ and everything else in between. So it's a trade-off, and it might be too expensive a trade-off, and so you might have to tolerate something like the collisions we had earlier, whereby even though they might very well happen, at least you are decreasing the probability by perhaps having more buckets like this. And in fact, if I rewind now to where we might have gone with this, here's how we might represent these nodes in the tree. Previously, in the past, we've had a person who had a string name and a string number, aka now char star. And so here now might be how, in this hash table, we represent someone's name and number, as well as a pointer to the next element in the list. Let me rewind just to the picture here. We keep drawing different shapes because, again, these are abstractions. Who really cares if they're to scale now? We've got enough room for the person's name. Not pictured on the screen is Hermione's number, but that's somewhere in this rectangle. But yes, pictured here in this little square is a pointer to the next node in the list. So by storing name and number, maybe her address, maybe her mailing address, whatever, in addition to a pointer, allows each of these nodes to be connectable, just like the nodes in a linked list. But where they're starting is in an array. So the array gets us like 1/26 of, or gets us
oh my gosh, it's so much.
Name and number.
Look like invincible art.
Not to mention the AAA and the ZZZ and everything else in between. So it's a trade-off, and it might be too expensive a trade-off, and so you might have to tolerate something like the collisions we had earlier, whereby even though they might very well happen, at least you are decreasing the probability by perhaps having more buckets like this. And in fact,
computer science so fun, yeah, I guess.
If I rewind now to where we might have gone with this, here's how we might represent these nodes in the tree. Previously, in the past, we've had a person who had a string name and a string number, aka now char star. And so here now might be how, in this hash table, we represent someone's name and number, as well as a pointer to the next element in the list. Let me rewind just to the picture here. We keep drawing different...
Wait, give me a sec. Okay. Okay, we can hear it. Okay. Too loud. Oh, oops. Subletter. Delete all. Dun, 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 dun. Okay, we need like a little pause, you know, before the big showdown. Oh, there's gonna be more frames. Dun, 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 dun. Oh, shush.
Shapes, because again, these are abstractions. Who really cares if they're to scale now? We've got enough room for the person's name. Not pictured on the screen is Hermione's number, but that's somewhere in this rectangle. But yes, pictured here in this little square is a pointer to the next node in the list. So by storing name and number, maybe her address, maybe her mailing address, whatever, in addition to a pointer, allows each of these nodes to be connectable, just like the nodes in a linked list. But where they're starting is in an array. So the array gets us like 1/26, or gets us, narrows the problem from size 26 to 1, gets us to the linked list in question. Hopefully it's a single person, or perhaps it has more than that. Meanwhile, what is the hash table itself? The hash table, the whole thing, is literally just an array. I've hard-coded the simplest version of size 26, but what do each of those boxes in the vertical array represent? Just a pointer to potentially a node in a linked list. And if there's no one there, if there's no one in location Y or X or the like in that universe, well, it's just a null pointer, signifying there's no one there. But if there is, it's going to be a...
You know, I'm actually... Yeah, I've been watching this. Because I just graduated from high school and I'm going to university, and I'm taking, you know, computer science. I just want to learn beforehand, you know. I mean, like, I will learn all of it again. It's good to learn beforehand, then you don't have to like worry too much of like, oh, I missed this, because lecturer. Because if the lecture is done, you cannot rewind, you know. So I don't know.
Pointer to a valid node.
In September. Oh, it's same here. I'm going to university in September too. Around September, October, I guess. But we're still waiting for, like, I don't know which school I'm going to. Hopefully the good one. You know, like, I'm selecting the school, the high end, the mid-range, and the low end, or the one that you have to pay a lot of money. So yeah, hopefully I have enough qualifications for a good one, so I don't have to pay for as much money, because the one that got was the one that supported by the government, the university that got money support from the government, would be a bit cheaper to pay than the one that is outside of the government. You know, I don't know. I don't know how to explain that, but you get the idea. Hopefully
we can get to any of the others.
It's like public school and private school. You know, public school is by the government. It's basically less money or free. I don't know. Who knows? But the private school is like separate from the government. They do their own thing, so it's a bit more expensive and stuff
as well. And that so-called hash function, just like the one I did with the greeting cards, well, it's just a black box, if you will, but implemented somewhere in code, like in C. And so if you pass in albus, what is the hash value of albus? Well, in the first version of the story with 26 buckets, it should be a 0. If you pass in Zacharias, it should be 25. And so just as my cards were being hashed to one of 1, 2, 3, 4 values, now these names are being hashed to one of 26 possibilities, or 26 times 26, or 26 to the third power, if you have more and more granularity than that. Questions.
I knew he was gonna say that.
Now of this idea of a...
Wait, I need to rewind. Oh wait, damn, it's 1:30 now. I gotta go eat lunch, guys. Oh my goodness. And I'm not hungry, but it's lunchtime, so I'm just gonna lunch. I'm gonna be right back. I'm just gonna cook, and I'll sit here, you know, and watch. Oh my gosh. I'm really sorry for spamming the animator. But there's a new one, you can find him by typing "roll my first video." And so really sorry. What? Spam. But there's a new animator, you can find him typing "roll my first video," search bar. Roll my first video in the search bar. YouTube? What do you mean by I'm not gonna go anywhere? I'm just gonna get the food. I'll be right back, so don't worry. Remain, don't eat. Die, man. Come back soon, yeah. I'll be right back, guys. Alright. Well, I'm back with my food, and yeah, I'm just gonna eat real quick, and I'll be right, and then I'll back to drawing, okay? We're currently at here. I'm just gonna charge my iPad. In the meantime, you playing Forsaken? I don't know what that game is, unfortunately. I don't play games much, you know. Jump scares. I'm sorry. Anyway,
we're being hashed to one of 1, 2, 3, 4 values.
let's try continue watching this.
Now these names are being hashed to one of 26 possibilities, or 26 times 26, or 26 to the 3rd power if you have more and more granularity than that. Questions on this implementation now of this idea of a hash table? If you say that again with the null.
Wait, what?
And more granularity than. On this implementation now of this idea of a hash table.
What the heck is Ginger Ale talking
say that
about?
again with the null. Oh, well, good question. So if there's so much sparseness, there's all of these empty cells in the array, couldn't you just go in and free them or delete them or just kind of shrink the array and not have AAA and AAB and AAC only have the prefixes, 2 or 3 characters that you need? You absolutely could do that, but now what you lose is the arithmetic benefit of being able to map each letter to a number. If you start freeing up unused space, you don't know that Zacharias is necessarily at location 25. Albus is still going to be at location 0, but if you've deleted some of the elements in the middle, Zacharias could be at 24 if you've deleted one, 23 if you've deleted another, and so you don't have that arithmetic immediacy that you need in order to index into the array with constant time. And the same is going to be true if it's 2 letters or 3 letters. You need to be able to trust that you can do some quick math and jump to the right index in constant time. And that's, again, the appeal of these arrays. So when it comes to the running time of a hash table, inserting values into it, searching for values therein, at the end of the day, it technically is big O of n, because in the craziest case, you might have a huge, fancy hash table, but everyone in the universe has a name starting with H, and then it just evolves into a really long linked list, just like a binary search tree could do the same. But if you choose a smarter hash function, maybe you mitigate that and you don't rely only on the first letter, but on the second or the third as well, or some other combination of that input, and make your hash function smarter. Odds are, if you get a good hash function, you want to get it to be more of like order of n divided by k, where k means constant mathematically, and so k is the number of buckets. So ideally, you want like a uniform distribution. You want like this many people here, this many people here. You don't want there to be some or no people. You want a uniform statistical distribution. And maybe you get that from human names, maybe you don't, but that's kind of the challenge of a hash function. Of course, big O of n over k is not a thing, because we always throw away constants like k, so it's still big O of n. But again, the distinction today is that, OK, yes, academically, you learned in CS50 that, sure, it's big O of n. But my God, it's 26 times faster if you do the hash function well, and you spread everyone out over the hash table. And that's the appeal of these kinds of structures. And we've got one more for you, if I may, something now known as a trie. So it turns out that a trie is even cooler, if you like this kind of thing, in that it does not devolve into big O of n. It is truly constant time. But there's going to be a price. There's going to be a gotcha. A trie is sort of a fancier tree, and it's short for retrieval, but pronounced.
Did he just mention gotcha?
Pronounced trie for weird historical. Going to be a price. There's going to be a gotcha. It is truly constant time. But there's going to be a price. There's going to be a gotcha. A trie is
a gotcha. Okay, whatever.
Sort of a fancier tree, and it's short for retrieval, but pronounced try for weird historical reasons. But a try is a tree, each of whose nodes is an array. Right? So this is all like crazy mashups now. People started inventing data structures just by combining different ones. So unfortunately, a lot of the good ideas are taken, but you just have benefits from certain aspects of those data structures, and combining them ideally gives you the best of both worlds, so to speak. So here might be the root of a try. It's literally a big node, a big rectangle, but it's actually an array. So there's like 26 locations in this picture here. And here's how you use a try, for instance, to store names just like the hash table. You treat each of the elements of that array in that node as like a letter of the alphabet, so A through Z, or 0 through 25. And if you want to store someone's name in here, you do so as follows. If you want to store like an H, you index into the H location. And if you want to store the second letter of someone's name, like an A, well, you add another node below it, and such one is connected to the other. And you then identify the A in that array. And then you go on and maybe put a G, if the goal is to store, spoiler now, Hagrid in this data structure. And then the R and the I and then the D. But when you get to the D, the end of the name, you have to somehow flag that this is the end of a name that we've embedded into this data structure. So whereas all of these are called out in white just to make obvious what we're connecting to what, green has to be like a bool that's true, that just indicates like the buck stops here. Like D is the last letter in someone's actual name. And what's kind of cool now about a try is that we can repeat this for other names as well. So for instance, here's where we might put
Okay, sorry guys. I just dropped something. That was fine. Okay, everything's fine. I can just clean it up. Anyway, I'm done eating now. Joe, sorry, man. Anyway, let me get some more drinks. I mean, water. Because I don't want to be dehydrated. So I'll be right back real quick. Đang hâm cái nồi cơm lại á. Mấy có ăn đây tự nhiên trứng ăn xong rồi cái chén trộn bớt mấy cái đồ kia xuống. Okay. I'm back, everyone. Now, continue.
Put Harry as well. And notice they share a common prefix, HA for Hagrid, HA for Harry. So we're reusing some of these nodes, some of these arrays. We can even slip Hermione in here too, borrowing only the H, but she gets the H, then the E, then R, R-M-I-O-N-E, and so forth. And we mark at the end of her name too that she's in there. Now, what's the takeaway here? Well, what is the running time of a try? How many steps does it take to find someone in this data structure? And let me zoom out so that it sort of suddenly becomes a massive data structure with even more in it. Maybe it looks, sorry. No, I'll keep it on this one. Maybe it looks a little something like this with just these three names. But how many steps does it take to find Hagrid or Harry or Hermione, no matter how many names are in this data structure? There's 3 at the moment, but it takes what? H-A-G-R-I-D. So 6 steps to find Hagrid. H-A-R-R-Y. 5 steps to find Harry. H-E-R-M-I-O-N-E. 8 steps to find Hermione. But notice that those steps are only dependent on what? The lengths of the humans' names. And let's assume that no one's going to have a infinitely long name. It's going to max out at what, like 8, maybe 18, maybe 20, 30. There's actually some pretty long human names out there, but it's going to be finite. You know it's bounded, whereas most contexts, n could grow forever. So what's compelling here is if you assume that the longest name is, I don't know, 50 for the sake of a theme here, then you know that finding anyone in this data structure will take you no more than 50 steps. 50 is thus a constant, which means you have big O of 1 running time. It doesn't matter if there's 1 million people in this phone book or 1 billion people in this phone book. That's going to definitely add more nodes to it, but it's still going to take you H-A-G-R-I-D, 6 steps to find Hagrid, H-A-R-R-Y, 5 steps to find Harry, even if there's 1 billion other people in that data structure. So now we actually do seem to have constant time if you assume that there's going to be a bound on the length of the name. Why don't we use tries for everything then? What's the price we're paying for this data structure, even though we've represented just 3 characters here? Yeah. It's a lot of memory, yeah, and you can see it even with these 3 names. Most of the squares on the screen are empty, like bytes and bits that are there and are allocated, and they need to be there because you need to be able to do that arithmetic thing of this being 0, this being 25, so you can jump from boom, 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 boom based on each of the letters. But it's a hugely sparse data structure, which means it takes up a crazy amount of memory. Now, maybe that's tolerable, especially for short names, but that's going to be the trade-off as well. And this is such a tension in computing. Almost anytime you want to improve time, you want to speed up the efficiency, the speed of your algorithm, you're going to spend space. If by contrast you want to decrease the amount of space, you might very well have to increase the running time. And it is indeed this seesaw back and forth, and you, your colleagues, your company need to decide what resource is the most precious. Heck, it might be just much harder to code one of these data structures than another. You're a human, your time is valuable. Do you really want to spend hours implementing a try when, hey, in 30 minutes I can bang out an array nowadays, or a linked list even? There too, development time is going to be yet another resource, and why sometimes there's good code or bad code, it depends on what you're prioritizing. So what do each of these nodes look like in a try? Well, we can keep calling it a node. This is a very generic term for just a container in these data structures. In this story, though, let me claim that everyone has a number, like a phone number, a string, aka char star. Every node has 26 children, or technically an array of size 26, that can point to more of these nodes. Notice that I don't need to store the name of someone in a try, because it's implicit in the path that you take to find them. So that's a minor optimization, but it saves us some space. But this would be just a different data structure we could use to actually solve this problem as well, albeit at a very expensive cost. And what do we need our variable to be that stores the try? Just like before, we just need a single pointer that hangs on to the root of this structure that's null if it's empty, or non-null if it's actually pointing at something. Any questions then on tries? And if it's feeling like a lot, the fire hydrant, it is. We started with arrays, then linked lists, then tries, but questions. Or not. And what do we actually? Sometimes it's in or string. Hey, in 30 minutes, you might very well have to increase the running time. And it is indeed this seesaw back and forth, and you, your colleagues, your company need to decide what resource is the most precious. Heck, it might be just much harder to code one of these data structures than another. You're a human, your time is valuable. Do you really want to spend hours implementing a try when, hey, in 30 minutes I can bang out an array nowadays, or a linked list even? There too, development time is going to be yet another resource, and why sometimes there's good code or bad code, it depends on what you're prioritizing. So what do each of these nodes look like in a try? Well, we can keep calling it a node. This is a very generic term for just a container in these data structures. In this story, though, let me claim that everyone has a number, like a phone number, a string, aka char star. Every node has 26 children, or technically an array of size 26, that can point to more of these nodes. Notice that I don't need to store the name of someone in a try, because it's implicit in the path that you take to find them. So that's a minor optimization, but it saves us some space. But this would be just a different data structure we could use to actually solve this problem as well, albeit at a very expensive.
All right. Brave doesn't work too well. I got scammed. I thought Brave was a good browser, but Brave, gosh, it's laggy. It might save memory, but it uses too much computational power, so I'm gonna use Microsoft Edge instead. Said later. Microsoft Edge is still something very cool. Give me a second, go everyone. I need to get my stuff working again. Is this the right one? Oh yes, this is the right one. Okay. Import favorite. Delete. What is this? Tab group. Nope. Okay, so extension. Okay, we got those. Okay, give me a second, guys. I'll be quick. Tabs. Oh, it saved all of this. Oh, it saved all of this, which is amazing. Good thing it's saved. Alright, people. We can try to like... We don't need these. I don't need this.
Increase the running time. It is time. It is
okay, I have officially, I don't know if officially is the right word, but like I've moved back to Microsoft Edge, mainly because Brave is slow, and it is slow, very slow to be honest. It's not like slow, but it's sometimes very computationally heavy that it kind of ruins my microphone. I think that's the problem, and I don't want to unplug and plug my microphone all the way every time. So yeah, it's kind of hard to get the thing working. Anyway, no, app, default app. Gonna get this to Microsoft Edge again. There you go. What else? File type. Went on Google, googling one. Okay, I can see where this is going. Link, gully, watch your link. I need a PDF file. Where's the PDF file? Portable distributional file, I think. I don't know. ABCD, okay, QRST. Oh wait, ABCDFGHIJK element OP O and P. There you go. PDF. Okay, Microsoft Edge. Okay, good.
time. It is indeed this seesaw back and forth, and you, your colleagues, your company need to decide what resource
Oh well, what is it like?
is the most precious. Heck, it might be just much harder to code one of these data structures than another. You're a
I have returned, and what games you want to play? What are you guys talking about?
human, your time is valuable. Do you really want to spend hours implementing a try when, you know, hey, in 30 minutes I can bang out an array nowadays, or a linked list even? There too, development time is going to be yet another resource, and why sometimes there's good code or bad code. It depends on what you're prioritizing. So what do each of these nodes look like in a try?
Huh? Yeah. Keep it close. Okay. I should delete all of these because I'm happy. Clap along if you feel like a room without the roof. Because I clap along, and if you know, yeah, wanna truth. Yeah, before actually animating all of these. Okay, my microphone keeps turning off. I have no idea why.
Well, we can keep calling it a node. For a human, your time is valuable. Do you really want to spend hours implementing a try
I don't know what's going
hey,
on.
in 30 minutes I can bang out an array nowadays, or a linked list even? There too, development time is going to be yet another resource, and why sometimes there's good code or bad code depends on what you're prioritizing. So what do each of these nodes look like in a try? Well, we can keep calling it a node. This is a very generic term for just a container in these data structures. In this story, though, let me claim that everyone has a number, like a phone number, a string, aka char star. Every node has 26 children, or technically an array of size 26, that can point to more of these nodes. Notice that I don't need to store the name of someone in a try, because it's implicit in the path that you take to find them. So that's a minor optimization, but it saves us some space. But this would be just a different data structure we could use to actually solve this problem as well, albeit at a very expensive cost. And what do we need our variable to be that stores the try? Just like before, we just need a single pointer that hangs on to the root of this structure that's null if it's empty, or non-null if it's actually pointing at something. Any questions then on tries? And if it's feeling like a lot, the fire hydrant, it is. We started with arrays, then linked lists, then tries. But questions on how we've just assembled from these basic building blocks? Yeah? A good question. Why is this not size 26? It's just like with the just like with the linked list before. It just tends to be in code convenient to have a separate additional pointer that's small that just points to the beginning of the data structure, because that way it can be null, thereby clearly indicating there are no nodes, the whole structure is empty. If you allocated one of those nodes, you absolutely could, but then you'd be just wasting space even if it's empty, and it creates an ambiguity. So just having a single pointer linked to the beginnings of all of these things is a good thing. Other questions now on tries, or trees, or hash tables, or arrays? So what problems might arise? Well, here's a counter example. What names are manifest in this try here?
Daniel.
Even if it's empty, and it creates an ambiguity. So just having a single pointer linked to the beginnings of all of these things is a good thing. It just tends to how we've just assembled from these basic building blocks. Yeah? A good question. Why is this not size 26? It's just like with the linked list before. It just tends to be in code convenient to have a separate additional pointer that's small that just points to the beginning of the data structure, because that way it can be null, thereby clearly indicating there are no nodes, the whole structure is empty. If you allocated one of those nodes, you absolutely could, but then you'd be just wasting space even if it's empty, and it creates an ambiguity. So just having a single pointer linked to the beginnings of all of these things is a good thing. Other questions now on tries, or trees, or hash tables, or arrays? So what problems might arise? Well, here's a counter example. What names are manifest in this try here? Feel free to just call it out. What do you see? Danielle and Daniel. So presumably if these are two names here, one of which is a prefix of another, notice that the data structure still works. And I chose, a friend's name and then appended a couple of more characters to it that's also a name because we have here D-A-N-I-E-L, and the green technically is implemented as a bool or something like that that indicates a word stops here. But we don't want to preclude storing Danielle as well, who's a superstring, if you will, of Daniel. And so that's OK, too, so long as the structure allows for the pointers to keep going. So even that works out OK, whereas it might not have otherwise. And in terms of the running time, just to be clear, at the end of the day, tries do give you actual constant time for insertions, lookups, deletions, and the like, because it's dependent only on the length of the input, the key, if you will, and not on how many other people are in your phone or address book.
Hello, Zero.
I now thought we'd included a visual. If you've gotten out into the square, anyone recognize this? OK, Sweetgreen, a local salad place. What are we looking at here, and what's its connection to today? You're about to become all the geekier in the real world because you will start to see data structures everywhere. What is this? Or how does this work maybe in salad form? Who's been to Sweetgreen? OK, either of you. So how does this work? OK, good. So if you order a salad for someone named L, when it's ready, they put it in the L section here.
It's lagging.
And so this is kind of a set of key value pairs, right? If L is the first letter of someone's name, the value hopefully is the salad. And so what you kind of have here is a dictionary, key value pairs, where it's not words and definitions, it's names and salads. And you can think of this, too, as kind of a hash table. Why? Even though it actually doesn't fit on one long shelf, because the store is only so big, this is really an array. And apparently A is missing, or maybe it's around the corner. But this array just happens to wrap onto multiple lines, but it's still conceptually a single dimension. But suppose two people have the name L. What do they do typically? Yeah, so maybe if they want to put that much effort into it, they might look at the second letter and then the third letter. Odds are this is not that interesting a problem to solve optimally in that way, but they probably do start stacking the salads on top of each other, maybe scooching it over just a little bit. And so what do you have there? Well, now if you start to view the lens through like CS50 glasses, like, OK, you have an array, and then you have like these linked lists that are sort of growing here. But even then you run into a problem. Why? Because it's not really a linked list, because at some point you're going to hit the boundary here. So it's kind of like an array of arrays, because you can only fit, what, like 3 or 4 salads here. And so long story short, we started today deliberately talking about real world things like stacks and queues. And even though it did escalate quickly into binary search trees and hash tables and tries, even those things are everywhere, even though they don't call them as such. These are just solutions to problems. And now, with this final week of C under your belt, you have all the more of a technical toolkit by which to implement these things in code. Next week, we'll be able to trust that someone else solved all these problems. We'll introduce Python, and lines of code like this will finally become lines of code like that. So that's the promise ahead, and we'll see you. Lines of code like this will finally become lines of code like that. So that's the promise ahead, and we'll see you next time.
Yeah. What week is it? What the heck? I don't know what week this is, but like we went through a lot of stuff.
All right, this is CS50, and this is week 6, wherein we finally transition from Scratch to C to now Python. And indeed, this is going to be somewhat of a unique experience in that just like a few weeks past, perhaps for the first time, and now today, you're going to learn a new language. But the goal isn't just to throw another fire hose of content and syntax and whatnot at you, but rather to really equip you all to actually teach yourself new languages in the future. And so indeed, what we'll do today, what we'll do this coming week, is sort of prepare you to stand on your own. And once Python is passé and the world has moved on to some other language in some number of years, you'll be well equipped to figure out how to wrap your mind around some new syntax, some new language, and solve problems as well. Now, you'll recall in week 0, this is where we started, just saying hello to the world. And that quickly escalated just a week later in C to B something much, much more cryptic. And if you've still sort of struggled with some of the syntax, find yourself checking your notes or your previous code, like that's totally normal. And that's one of the reasons why there are languages besides C out there, among them this language called Python. Humans over the decades have realized, gee, that wasn't necessarily the best design decision. Or humans have realized, wow, you know what? Now that computers have gotten faster with more memory and more faster CPUs, we can actually do more with our programming languages. So just as human languages evolve, so do actual programming languages. And even within a programming language, there's typically different versions. We, for instance, have been using version C11 of C, which was updated in 2011. But Python itself continues to evolve, and it's now up to version 3 plus. And so there, too, these things will evolve in the coming days. Thankfully, what you're about to see is Hello World for the third time, but it's going to be literally this. None of the crazy syntax above or below, fewer semicolons, if any, fewer curly braces, and really a lot of the distractions get out of the way. So to get there, let's consider exactly how we've been programming up until now. So you write a program in C, and you've got hopefully no syntax error, so you're ready to build it, that is compile it. And so you've run make, and then you've run the program like /hello. Or if you think back to week 2, where we took a peek underneath the hood of what make is doing, it's really running the actual compiler, something called clang, maybe with some command line arguments, creating a program called hello, and then you could do
It works. Why? Why? It sometimes does that. I don't know why. Configure. Sometimes it break. The sink is flooded with cake left over. What do you mean? Set up microphone. Where desktop microphone. Nope. Train your understand you, but no advanced speech options. What do you mean by that? What are these? I just need it to not turn off by itself. Details, description, USB audio device, property, drivers detail. Okay. Events started. USB audio. I don't know what's going on here. I can send it to you. It's this. Okay, you don't have to. Adding snap in to console. What? No. Oh my gosh, what's happening? Never mind then. Should I turn on these two on? I have no idea.
/hello. So today, you're going to start doing something similar in spirit, but fewer steps. No longer will you have to compile your code and then run it, and then maybe fix or change it, and then compile your code and run it, and then repeat. The process of running your code is going to be distilled into just a single step. And the way to think of this for now is that whereas C is frequently used as indeed a compiled language, whereby you convert it first to zeros and ones, Python's going to let you speed things up, whereby you, the human programmer, don't have to compile it. You're just going to run what's called an interpreter, which by design is named the exact same thing as the language itself. And by running this program in installed in VS Code or eventually on your own Macs or PCs, this is just going to tell your computer to interpret this code and figure out how to get down to that lower.
Sometimes when the PC got like super laggy and then it just stopped working, which is weird. The mic, I mean.
Or level of zeros and ones, but you don't have to compile the code yourself anymore. So with that said, let's consider what the code is going to look like side by side. In fact, let's look back at some
lagging. Oh my gosh, what's going on here? Oh, I get it. Oh, come on. I know why. 5,000 only. Ultra low, look ahead, adapted quantizations. Just gonna turn these twos on just in case anything happens. Buffer frames, okay, too, okay. Hopefully it doesn't break my PC. About this. OBS, right? Yeah, it is OBS. I need to change the resolution a little bit like that, so it doesn't break my PC. If I just keep, yeah, there you go. I lowered the resolution, but it won't hurt much, you know.
Scratch blocks, just like we did with C in week 1, and do some side-by-sides, because even though some of the syntax this week and beyond is going to be different, like the ideas are truly going to be the same. There's not all that much intellectually new just yet. So whereas in week 0 we might have said hello to the world with this purple puzzle piece, today of course, or rather in week 1 it looked like this in C. But today, moving forward, it's going to quite simply look like this instead. And if we go back and forth for just a moment, here again is the version in C, noticing the very C-like characteristics. And just at a glance here, in Python, I claim it's now this. What do you apparently need not worry about anymore?
The semicolon.
What's gone?
Semicolon.
So semicolon is gone, and indeed you don't need those to finish most of your thoughts anymore. Anything else? So the \n is absent, and that's kind of curious because we're still going to get
Hello, my mic break again because of some laggy thing. I have no idea. Break thy computers. I'm installing Java Oracle. Java, right? Java to like code or something. I don't know. I don't know what's going on. My goodness. Give me a second. I need to like monitor this. What is GPU doing there? Memory doesn't use that much memory. CPU was. I don't know what's causing
a new line, but we'll
what causing all of this. But let's see. Okay, let's see. OBS is actually using a lot. Okay. Crash handler. Container. What are the things that is running in the background that makes my my PC run so bad? Yo, grab a plate or shh. What do you ask me that? It's for I'm not gonna answer that, alright? Come on, man.
See that it's become the default, and this one's a little more subtle, but now the function is called print instead of printf, so it's a little more familiar in that sense. All right, so when it comes to using libraries, that is code that other people have written, in the past we've done things like hash include cs50.h to use cs50's own header file, or standard IO, or standard lib, or string, or any number of other header files you have all used. Well, moving forward, we're going to give you for this first week a similar cs50 library, just very short-term training wheels that will quickly take off, because in reality it's a lot easier to do things in Python, as we'll see. But the syntax for this now is going to be to import the CS50 library in this way. And when we have now this ability, we can actually start writing some code right away. In fact, let me switch over to VS Code here. And just as in the past, I'll create a new file, but instead of creating something called .c, I'm going to go ahead and create my first program called hello.py using code space hello.py. That, of course, gives me this new tab. And let me actually quite simply do what I proposed, print quote unquote hello world without the \n, without the semicolon, without the f in print. And now let me go down to my terminal window, and I don't have to compile it. I don't have to do /. I instead run a program called Python, whose purpose in life is now to interpret my code top to bottom, left to right. And if I run Python of hello.py, crossing my fingers as always, voila. Now I have printed out hello world. So we seem to have gotten the new line for free in this sense, where it's automatically happening. The $sign isn't weirdly on the same line like it once was in week 1, but that's just a minor detail here. If we switch back to now some other capabilities, well, indeed, with the CS50 library, you can also not just import the library itself, but specific functions. And you'll see that temporarily we're going to give you a helper function called getString, just like in C, that just makes it work exactly the same way as in C. And we'll see a couple of other functions that will just make life easier initially, but quickly will we take those training wheels off so that nothing is indeed CS50 specific. All right, well, how about functions more generally in Python? Let's do a whirlwind tour, if you will, much like we did in that first week of C, comparing one.
I will make it short and add me. Break up play. What is going on? Are we flipping? What? Ly gì? À here. Coffee. Trời ơi. Cái chừng rớt. Cái chừng rớt không phải đổ.
One to the other. So back in our world of Scratch, one of the first programs we wrote was this one here, whereby we asked the human their name. We then used the return value that was sort of automatically stored in this answer variable as a second argument to join, so that we could say hello David or hello Carter. So this was back in week 0. In week 1, we converted it to this. And here's a perfect example of things like escalating quickly. And again, this is why we start in Scratch. There's just so much distraction here to achieve the same idea. But even today, we're going to chip away at some of that syntax. So in C, we had to declare the argument as we had to declare the variable as a string here. We, of course, had the semicolon and more. Well, in Python, the comparable code now is going to look more simply like this. So semicolon is again gone on both lines, for that matter. So that's good. What else appears to have changed or disappeared? Yeah. Yeah, so I didn't have to specifically say that answer is now a string. And indeed, Python is dynamically typed. And in fact, it will infer from context exactly what it is you are storing in that variable. Other details that seem a little bit different. A little bit different. What else jumps out at you here? I'll go back. This was the C version. And maybe focus now on the second line, because we've rather exhausted the first. Here's now the Python version. What's different here, yeah? Yeah, there's no %s anymore. There's no second argument at the moment, per se, to print. Now, it is still a little weird. It's as though I've deployed some addition here arithmetically, but that's not the case. Some of you have programmed before, and plus, some of you might know means what in this context? So to combine, or more technically, anyone know the buzzword? Yeah. To concatenate. So to concatenate is like the fancy way of what Scratch calls joining, which is to take one string on the left, one string
concatenate, bro,
on the right, and to join them together, to glue them together, if you will. So this is not addition. It would be if it were numbers involved instead. But because we've got a string, hello, comma, and another string implicitly in this variable based on what the human typed in response to this getString function, that's going to concatenate hello, comma, space, and then David or Carter or whatever the human has typed in. But it turns out there's going to be different ways to do this in Python. And we'll show you a few different ones. And here, too, try not to get too hung up on or frustrated by all of the different ways you can solve problems. Odds are you're going to be picking up tips and techniques for years to come if you continue programming. So let's just give you a few of the possible ways. So here's a second way. You could print out hello, comma, David or hello, comma, Carter. But what has changed? In the previous version, I used concatenation explicitly. And the space here is important grammatically, just so we get that in the final phrase. Now I'm proposing to get rid of that space, to add a comma outside of the double quotes as well. But if you think back to C, this probably just means that print similar in spirit to printf, can take not just one argument, but even two. And in fact, because of this comma in the middle that's outside of the double quotes, it's hello, comma, and then it will be automatically concatenated with, even without using the plus, to whatever the value of answer is. And by default, just for grammatical prettiness, the print function always gives you a space for free in between each of the multiple arguments you pass in. We'll see how you can override that down the line, but for now, that's just another way to do it. Now, perhaps the better, if slightly cryptic way to do this, or just the increasingly common way, is probably this third version, which looks a little weird too. And probably the weirdness jumps out. We've suddenly introduced these like curly braces, which I promised were mostly gone, and they are. But inside of this string here, I've done a curly brace, which might mean what, just intuitively? And here's sort of an example of how you learn a new language. Just kind of infer from context how Python probably works. What might this mean? Yeah. Yeah, so this is an indication, because of the curly braces, because this is the way Python was designed, that we want to plug in the value of answer, not literally ANSWER. And the fancy word here is that the answer variable will be interpolated. That is, substituted with its actual value. But, and this is actually weird looking. This was introduced a few years ago to Python. What else did I have to change to make these curly braces work, apparently? Yeah. Yeah, there's this weird f. And so it's sort of like part of printf, but now it's inside the curly, it's inside the parenthesis there. This is just the way Python designed this. So a few years ago, when they introduced what are called format strings, or f strings, you literally prefix your quoted string with the letter f. And then you can use trickery like this, like putting curly braces, so that the value will be substituted automatically.
Hello,
if you forget the f, you're going to literally see hello, comma, curly brace, answer.
I'm sorry, man. How do you say your name? FX Animates. I'm sorry, man. Oh my gosh. I'm sorry. Anyway, for those who are new here, I'm sorry for the video on the right side. If you want to listen, Archive. Oh, okay, thank you. Archive X Animate. Okay, I see. XA Animate, okay. Anyway, for those who are new here, I'm sorry for the video on the right, but if you want to learn something about computer science, you can listen, or maybe you just watch me do this. I don't know, man. I'm trying to learn computer science.
Can use trickery like this, like putting curly braces, so that the value will be substituted automatically. If you forget the f, you're going to literally see hello, comma, curly brace, answer, close curly brace. If you add the f, it's indeed interpolated. The value is plugged in. All right, questions on how we can just say hello to the world via Python?
You thought I was watching Bitcoin? Okay.
Yeah.
I ain't into those things.
If you do this without the f, if you omit the f, you will literally see HELLO, comma, curly brace, ANSWER, close curly brace. So in fact, let's do this. Let me go back to VS Code here quickly. I've still got my file called hello.py open. And let me go ahead and change this ever so slightly. So I'm going to go ahead and let's say from CS50 import getString. And that's just the new syntax I propose using to import a function from someone else's library. I'm going to now go ahead and ask the question, let's go ahead and use getString, storing the result and answer. So getString, quote unquote, what's your name, question mark. And then on this line, I'm going to deliberately make a mistake here, exactly to your question. Let me just say hello, comma, answer. And just this. Now, even though answer is a variable, Python's not going to be so presumptuous as to just plug in the value of a variable called answer. What it's going to do, of course, is if I type in my name, whoops, I typed too fast. Let me go ahead and rerun that again. If I run python of hello.py, type in my name and hit enter, I get hello, comma, answer. Well, let me do one better. Let me apply these curly braces as before. Let me rerun python of hello.py. What's your name? DAVID. And here's again the answer to your question. Now we get literally the curly braces. So
you gotta really practice coding again. For what? What you wanna do with coding? Hello, Laguitan. I don't know how to say his name. Sorry.
It's just going to be to add the f there, rerun my program again with DAVID, and now hello, comma, David. So this is admittedly a little more cryptic than the ones with the plus or the comma, but this is just increasingly common. Why? Because you can read it left to right. It's nice and convenient. It's less cryptic than the %s. So it's sort of a new and improved version, if you will, of printf in C, based on decades of experience of programmers doing things like this. Questions on printing in this way? We're now on our way to programming in Python. Anything? All right. Well, what more can we do with this language here? Well, let me propose that we consider that we have, for instance, a few other features that we can add to the mix as well. Namely, let's say some data types as well. So let me flip over here to back to the slides. And there's different data types in Python, as we'll soon see. But they're not as explicit as we already saw by using a string from getString. You don't have to explicitly state what it is. But you saw, recall in C, all of these various data types. And then in Python, kind of nicely enough, this list is about to get shorter. And so here is our list in C. Here is an abbreviated list in Python. So we're still going to have strings, but they're going to be more succinctly called strs now, str. We're still going to have ints for integers. We're still going to have floats for floating point values. We're even going to have bools.
It's drawing with coding. To answer your questions, I studied practice code because I have to hack the hacker to his own code. Okay, that's nice.
For true and false. But what's missing now from the list is long and floats. And why is that? Or rather, long and double. Well, recall that in C, those used more.
Wait, what? Something's doesn't make sense here. You hack the hacker. Why do you code? Because that's not coding. If you hack the hacker, that's not coding. That's basically it's the internet thing. It doesn't relate to coding at all.
Bits. Well, in Python, the smaller data types previously, int and float, themselves just use more bits for you. And so you don't need to distinguish between small and large. You just use one data type, and the language gives you a bigger range than before. It turns out, though, there's going to be some other features as well of Python, these data types, one of which will be called range, another of which will be list. So
I meant it differently. I have no idea. They are using different computing know how you hack them back. Yeah, it's internet related connection. I don't know how what she meant by like hacking, you know. Man, you probably is okay.
On will be arrays. We'll actually use something.
Wait, yeah, right. What can I say? Right? I'm still learning. There's nothing I can say to like I probably cannot understand you. You understand more than me, so.
Literally called a list. Tuples, sort of like XY pairs for coordinates and things like that. Dict for dictionaries. So we'll have built-in capabilities for storing keys and values, we'll see. And even a set. Sort of mathematically, a set is like a collection of values, but it automatically gets rid of duplicates for you. So other features as well of Python, these data types, one of which will be called range, another of which will be list. So gone will be arrays. We'll actually use something literally called a list. Tuples, sort of like XY pairs for coordinates and things like that. Dict for dictionaries. So we'll have built-in capabilities for storing keys and values, we'll see. And even a set. Sort of mathematically, a set is like a collection of values, but it automatically gets rid of duplicates for you. So all of these things we could absolutely implement in C if we wanted, and indeed in problem set 5, you've been implementing your very own spell checker using some form of hash table. Well, it turns out that in Python you can solve those same problems, but perhaps a little more readily. In fact, let me go back over here to VS Code, and let me propose that I do the following. Let me go ahead and create a file called dictionary.py. Let me propose that I try to implement, say, problem set 5, our spell checker in Python instead of C, and achieve ultimately the same kind of behavior whereby I'll be able to spell check a whole bunch of words. So this is jumping the gun a little bit, because you're about to see syntax we'll revisit over the course of today. But for now, I've got a new file called dictionary.py. and let me begin to create some placeholders for functions. We'll see in just a bit that in Python you can define a function called check, and that check function can take a word as its input, and I'll come back to this in just a moment. In Python, I can define a second function like load, which itself will take a whole dictionary, just like in problem set 5, and I'll go ahead and come back to the implementation of this. Meanwhile, we might similarly implement a function called size, which takes no arguments, but ultimately is going to return the size of my dictionary of words. And then lastly, for consistency with problem set 5, we might define an unload function whose purpose in life is to free any memory that you've been using just to give it back to the computer. Now, odds are whether you're still working on Speller or have finished Speller, like you wrote a decent amount of lines of code, and indeed it's been, by design, a challenge. But one of the reasons
What a great way to start my day. Just woke up. Hello. See ya.
for these higher code and anything on Speller using, we might go looking for the course of sheets to find some form of hash table. Well, it's implement in C if we want duplicate, and even a set. Sort of mathematically, a set is like a collection of values, but it automatically gets rid of duplicates for you. So all of these things we could absolutely implement in C if we wanted, and indeed in problem set 5, you've been implementing your very own spell checker using some form of hash table. Well, it turns out that in Python, you can solve those same problems, but perhaps a little more readily. In fact, let me go back over here to VS Code, and let me propose that I do the following. Let me go ahead and create a file called dictionary.py. Let me propose that I try to implement, say, problem set 5, our spell checker, in Python instead of C, and achieve ultimately the same kind of behavior whereby I'll be able to spell check a whole bunch of words. So this is jumping the gun a little bit, because you're about to see syntax we'll revisit over the course of today. But for now, I've got a new file called dictionary.py. And let me begin to create some placeholders for functions. We'll see in just a bit that in Python you can define a function called check, and that check function can take a word as its input, and I'll come back to this in just a moment. In Python, I can define a second function like load, which itself will take a whole dictionary, just like in problem set 5, and I'll go ahead and come back to the implementation of this. Meanwhile, we might similarly implement a function called size, which takes no arguments, but ultimately is going to return the size of my dictionary of words. And then lastly, for consistency with problem set 5, we might define an unload function whose purpose in life is to free any memory that you've been using just to give it back to the computer. Now, odds are whether you're still working on Speller or have finished Speller, like you wrote a decent amount of lines of code, and indeed it's been, by design, a challenge. But one of the reasons for these higher level languages like Python is that you can stand on the shoulders of programmers before you and solve very common problems much more quickly, so that you can focus on building your new app or your web application or your own project to solve problems of interest to you. So at the risk of crushing some spirits, let me propose that in Python, if you want a dictionary for something like a spell checker, well, that's fine. Go ahead and give yourself a variable like words to store all of those words, and just assign it equal to a dictionary, or dict for short in Python. That will give you a hash table. Now, it turns out in Speller, recall, you don't need to worry about words and definitions. It's just about spell checking the words. So strictly speaking, we don't need keys and values. We just need keys. So I'm going to save myself a few more keystrokes by just saying that technically in Python, using a set suffices. Again, a set is just a collection of values with no duplicates. But they don't necessarily have keys and values. It's just one or the other. But now that I have, on line 1, I claim, the equivalent in Python of a hash table, I can actually do something like this. Here's how I might implement the check function in Python. If the word
It's crazy here.
passed
What do you
into
mean?
this function is in my variable.
Wait a minute.
To worry about words and definitions. It's just about spell checking the words. So strictly speaking, we don't need keys and values. We just need keys. So I'm going to save myself a few more keystrokes by just saying that technically in Python, using a set suffices. Again, a set is just a collection of values with no duplicates. But they don't necessarily have keys and values. It's just one or the other. But now that I have, on line 1, I claim, the equivalent in Python of a hash table, I can actually do something like this. Here's how I might implement the check function in Python. If the word passed into this function is in my variable called words, well, return true. Else, go ahead and return false. Done. Wait, you're thinking, if anything at all, maybe we want to handle lowercase instead of just uppercase and lowercase. Well, you know what? In Python, if you want to force a whole word to lowercase, you don't have to iterate over it with a loop. You don't have to use any of that C-type functions or anything. Just say word.lower, and that will convert the whole thing to lowercase for parity with the dictionary. All right, how about something like the load function in Python? Well, in Python, you can open files just like in C. For instance, in Python, I might do open the dictionary argument in read mode, just like fopen in Python. I might do something like this. For each line in that file.
What? File equal open dictionary, okay.
Let me go ahead and add to my words variable that line. And then let me go ahead and close that file. And I think I'm done. I'm just going to go ahead and return true just because I think I'm already done. Now here too, I could nitpick a little bit. Technically, if I'm reading in every line from the file, every line in the dictionary ends with technically a \n, but there's an easy way to get rid of that, just like you might in C with an alternative syntax. What I'm actually going to do is this.
Load file, add line. File, open, okay, dictionary, read. For line in file, okay. Word.add line. Words.add line. What? I have no idea.
Let me grab from the current line, the current word, by stripping off with reverse strip. rstrip, a function we'll again see, that just gets rid of the trailing new line, the \n at the end of that line. And what I really want to do then is add this word to that dictionary. Meanwhile, if I want to figure out what the size
Add the word of the line and I see.
is of my dictionary.
Okay. Kind of get it. Ouch. Word equal line strips. What? There's no
Trailing
okay.
new line, the \n at the end of that line. And what I really want to do then is add this word
sucka.
to that dictionary. Meanwhile, if I want to figure out what the size is of my dictionary, well, in C, you're probably writing code to iterate over all of those lines, and you're just going to count them up using a variable. Not so in Python. You can just return the length of those words. And better still, in Python, you don't have to manage your own memory. No more malloc, no more free, no more manual thinking about memory. The language just deals with all of that for you. So you know what? It suffices for me to just return true and claim that unloading is done for me.
Damn.
And that's it. Again, whether you're in the middle
Ka-chow.
of or
Hello,
already
Skylar.
finished, this might perhaps suggest some frustration, but also enlightenment in that this is why higher level languages exist. You can build on top of the same principles, the same ideas with which you've been struggling even this past week, but you can now express yourself all the more succinctly. Like this one line implements a hash table for you, and all of this now just uses that hash table in a simpler way. Any questions now on this? Keeping in mind that the point, nonetheless, of Speller and PSET 5 is to understand what's really going on underneath the hood. And better still, to notice this. This might seem all rather amazing, but let me go ahead and do this. I've actually got a couple of versions of Speller written here, and I've got a version written in C that I won't show the source code for, but I'm going to go ahead and make that version of Speller in C. And I'm going to go ahead here and, let's say, split my window here for just a moment. And I'm going to go into a Python version of Speller, really that I just wrote. And on the left-hand side here, let me go ahead and run Speller, the version I compiled in C, using a big text like the Sherlock Holmes text, which is a whole lot of words in it. And on the right-hand side, let me run Python of speller.py, which is a separate file I wrote in advance, just like we give you speller.c. And I'll similarly run this on the Sherlock Holmes text. And I'm going to do my best to hit enter on the left and the right of my screen at the same time. But we should see, hopefully, the same list of misspelled words and the timings thereof. So here we go on the right. Here we go on the left. All right. Sort of a race to see which one wins here. C is on the left. Python is on the right. OK. Interesting. Hopefully, Python's close behind. Note that some of this is internet delay, and so it might not necessarily be a crazy number of seconds, but the system is indeed using, if we measure at a low level, how much time the CPU spent executing my code. C took a total of 1.64 seconds. That was pretty fast, even though it took a moment more for all of the bytes to come over the internet. The Python version, though, took what? 2.44 seconds. So what might an inference be? I mean, one, maybe I'm just better at programming in C than I am in Python, which is probably not true. But what else might you infer from this example? Should we maybe give up on Python, stick with C? No? So what might be going on here? Like, why is the Python version that I claim is correct, and I think the numbers all line up, just not the times, where's the trade-off here? Well, here again is sort of this design trade-off. Yeah. Yeah, exactly. In order to save the human programmer time, there's a lot more features built into Python, more functions, more automatic management of memory, and so forth. And you have to pay a price. Like, someone else's code is doing all of that work for you. But if they've written some number of lines of code, those are just more lines of code that need to be executed for you. Whereas here, the computer is, at the risk of oversimplifying, only running my lines of code. So there's just less overhead. And so this is a perpetual trade-off. Typically, when using a more user-friendly, a more modern language, one of the prices you might pay is performance. Now, there's a lot of smart computer scientists in the world, though, trying to push back on those same trade-offs. And so these interpreters, like the command I wrote, Python, technically can, especially if you run a program again and again, they can actually sort of secretly behind the scenes compile your code for you down to zeros and ones, and then the second, the third, the fourth time you run that program, it might very well be faster. So this is a bit of a head fake here in that I'm running them once and only once, but we could get benefit over time if we kept running the Python version again and again and perhaps fine-tune the performance. But in general, there's going to be this trade-off. Now, would you rather spend the 60 seconds I wrote implementing a spell checker, or the 6 hours, 16 hours you might be or have spent implementing the same in C? You know, probably not. For productivity's sake, this is why we have these additional languages. Just for fun, let me flip over to another screen here.
Give me a second, guys. I have stuff to
Python that's actually on my,
fix right here.
On my own Mac instead of the cloud, so that I can actually do something with graphics. So here I just have a black and white terminal window on my very own Mac, and I've pre-installed Python just like we've done for VS Code in the cloud for you. Notice that I've got this photo of perhaps one of your favorite TV shows here with the cast of The Office. Notice all of the faces in this image here. And let me propose that we try to find one face in the crowd, sort of CSI style, whereby we want to find perhaps the Scranton Strangler, so to speak. And so here is an example of this guy's face. Now, how do we go about finding this specific face in the crowd? Well, our human eyes obviously can pluck him out, especially if you're familiar with the show. But let me go ahead and do this instead. Let me go ahead and propose that we run code that I already wrote in advance here. This is a Python program with more lines of code that we won't dwell on for today, but it's meant to motivate what we can do from a pillow library, implying a Python image library. I want to import some type of information called some feature called image, so that I can manipulate images, not unlike our own problem set 4. And this is kind of powerful. In Python, you can just import face recognition as a library that someone else wrote. From there, I'm going to create a variable called image. I'm going to use this face recognition's library's load image file function. It's a little verbose, but it's similar in spirit to fopen. And I'm going to open office.jpg. I'm going to then declare a second variable called face locations, plural, because what I'm expecting to get back, per the documentation for this library, is a list of all of the faces locations that are detected. All right, then I'm going to iterate over each of those faces using a for loop that we'll see in more detail. I'm going to then infer what the top, right, bottom, and left corners are of that face. And then what I'm going to do here is show.
Wait, what?
From a pillow library, implying a Python image library, I want to import some type of information called some feature called image, so that I can manipulate images, not unlike our own problem set 4. And this is kind of powerful. In Python, you could just import face recognition as a library that someone else wrote. from there, I'm going to create a variable called image. I'm going to use this face recognition's library's load image file function. It's a little verbose, but it's similar in spirit to fopen. And I'm going to open office.jpg. I'm going to then declare a second variable called face locations, plural, because what I'm expecting to get back, per the documentation for this library, is a list of all of the face's locations that are detected. All right, then I'm going to iterate over each of those faces using a for loop that we'll see in more detail. I'm going to then infer what the top, right, bottom, and left corners are of that face. And then what I'm going to do here is show that face alone. If I
Top, right, bottom, left. Face image equal image. Top, bottom. What the frick is this? Face. Okay, face locations.
I've detected the face in question. So let me go ahead here and run detect.
Wait, let me.
Verbose, but it's similar in spirit to fopen. And I'm going to open office.jpg. I'm
Okay.
going to then declare a second variable called face locations, plural.
Face locations. I don't know why it's plural, but. And then the music, I need to change the music. Music makes you lose control. Wait a minute. Okay. A little more. Then you have a new viewer, acknowledge them. Oh, the weird FNAF fan, hello. Why is your name like that? Oh my gosh, there's too much going on right now. So, okay, thank you. Okay, I either want to color it, or is this only about Python? Which one? The video? No, it's actually a full course. Harvard CS50 is full course on computer science, you know.
Because what I'm expecting to get back, per the documentation for this library, is a list of all of the faces' locations that are detected. All right, then I'm going to iterate over each of those faces using a for loop that we'll see in more detail. I'm going to then infer what the top, right, bottom, and left corners are of that face. And then what I'm going to do here is show that face alone if I've detected the face in question.
Wait, what?
So let me go ahead here and run detect. So let me that face. And then what I'm going to do here, faces using a for loop that we'll see in more detail. I'm going to then infer what the top, right, bottom, and left corners are of that face. And then what I'm going to do here is show that face alone if I've detected the face in question. So let me go ahead here and run detect.py. And we'll see not just the one face we're looking for, but if I run python of detect.py, it's going to do all of the analysis. I'll see a big opening here now of all of the faces that were detected in this here program. Okay, some better than others, I guess, if you zoom in on catching someone, typical Angela. If you now want to find that one face, I think we need to train the software a bit more. So let me actually open up a second program called Recognize that's got more going on. But let me, with a wave of a hand, point out that I'm now loading not only the office.jpg, but also toby.jpg to sort of train the algorithm to find that specific face. And so now, if I run this second version, recognize.py, with Python of recognize.py, hold my breath for just a moment. It's analyzing presumably all of the faces. You see the same original photo, but do you see one such face highlighted here? This version of the code found Toby, highlighted him with this green, and voila, we have face recognition. So for better or for worse, this is what's happening increasingly societally nowadays. And honestly, even though I didn't write the code live, because it's a good dozen or more lines of code, it's not terribly many. And literally all the authorities, all we have to do is import face recognition, and voila, you have access. Like, these technologies are here already. But let's consider for just a moment, how did we find Toby? Like, how might that library, even though we're not going to look at its implementation details, how does it find Toby and distinguish him from all of these other faces in the crowd? What might it be doing intuitively? Think back even to pset 4, like what you yourselves have access to data-wise. Yeah?
Should I color it? Or should I just leave it black and white? I think I should leave it black and white because it's gonna take forever for me to color. Because if I color, I gotta shade them. But if I gotta shade them, it's gonna take insane amount of time. So I don't really. Just leave it black and white too. Yeah, tried Python and only knows very basic stuff. You know, Python is only the language. You gotta know like how the thing works and how you use them to your advantage. I don't know, man. I'm still learning. I cannot say much.
A lot of people are saying from that reference image to this image, that's going to say, hey, a lot of similar pixel arrangements here.
Yeah, exactly. And to summarize for camera here, we have trained the software, if you will, by giving it a photo of Toby's face. So by looking for the same or really similar pixels, especially if it's a slightly different image of Toby, we can perhaps identify him in the crowd. And what really is a human face? Well, at the end of the day, the computer only knows it as a pattern of bits, or really at a higher level, a pattern of pixels. So maybe a human face is perhaps best defined in general as like 2 eyes and a nose and a mouth, that even though all of us look similar structurally, odds are the measurement between the eyes and the nose and the width of the mouth, the skin tone, and all of these other physical characteristics are patterns that software could perhaps detect and then look sort of statistically through the image, looking for the closest possible match to these various measurements, shapes, colors, and sizes, and the like. And indeed, that might be the intuition, but what's powerful here again is just how easy and readily available this technology now is. All right, so with that said, let's propose to consider what more we can do with Python itself, get back to the fundamentals so that you yourselves can start to implement something along those same lines. So besides having access to things like a getString function, the CS50 library provides a few other things as well. Namely, in C, we had these. But in Python, we're going to have fewer. In Python, our library short term is going to give you not only getString, but also getInt and getFloat. Why? It's actually just kind of annoying, as we'll soon see, to get back an integer or a float from a user and just make sure that it's an int and a float and not like a word like cat or dog or some string that's not actually a number. Well, we can import not just the specific function getString, but we can actually import all of these functions one at a time like this, as we'll soon see. Or you can even in Python import specific functions from a file. One of you asked a while back, when you include something like cs50.h or standardio.h, you're actually getting all of the code in that file, which potentially can add bulk to your own program or time. In this case, when you import specific functions from Python, you can be a little more narrowly precise as to what it is you want to have access to. All right, so with that said, let's go ahead and see what conditionals look like in Python. So in the left-hand side again here, we'll see Scratch. And here, for instance, was just kind of a contrived example asking if x is less than y, then say x is less than y. In C, it looked like this. In Python now, it's going to look like this instead. And here's before in C. and here's after. And just to call out a few of the obvious differences, what has changed in Python for conditionals, it would seem? Sort of, what's the difference? Yeah. Yeah, so there's no more curly braces, and indeed you don't use those. What appears to be taking their place, if you might infer? What seems to have taken their place? What do you think? So the colon at the start of this line here, but also even more important now is this indentation below it. So some of you, and we know this from office hours, have a habit of like indenting everything on the left, right? And it's just kind of this crazy mess to look at. Frustrating for you, surely, but C and Clang is pretty tolerant when it comes to things like white space in a program. Python, They realized years ago that let's help humans help themselves and just require standard indentation. So 4 spaces would be the norm here, but because it's indented below that colon, that indeed indicates that this now is part of that condition. Something else has gone missing versus C in this conditional. What else is a little simplified? Yeah, so no more parentheses. You can still use them, especially when you need to logically to do order of operations like in math. But in this case, if you just want to ask a simple question like if x less than y, you can just do it like that. How about when you have an if else? Well, this is almost the same here with these same changes. In C, this looked like this. And it's starting to get a bit bulky, at least if we use our curly braces in this way. In Python, we can tighten things up further. Even though strictly speaking in C, you don't always need the curly braces.
Yeah,
but
I'm
here,
just trying to make
gone are
it...
the parentheses again. Gone are the curly braces. Indentation is consistent, and we've just added another keyword else with a colon, but no more semicolons as well.
Oh, wait, just
How
leave
about
it like
something
this,
larger
something
like this?
important.
An if else. This one's a little curious, but in C it looked like this. If else. In Python, it now looks like this. And there's perhaps one curiosity here that honestly, all these years later, I still can't remember how to spell it half the time. What's weird about this? What do you spot as different? Yeah, over here. Yeah, instead of else if, it's elif. Why? Apparently else space if was just too many keystrokes for humans to type, so they condensed it into this way. Probably means it's a little more distinguishable too for the computer between the if and the else too, but just something to remember now. It's indeed elif and not else if. All right, so what about variables in Python? I've used a couple of them already, but let's distill exactly how you define and declare these things as well. So in Scratch, if we wanted to create a variable called counter and set it equal initially to 0, we would do something like this. Specify that it's an int, use the assignment operator, end the thought with a semicolon. In Python, it's just simpler. You name the variable, use the assignment operator as before, you set it equal to some value, and that's it. You don't mention the type, you don't mention the semicolon or anything more. What if you want to change a variable like counter by 1, that is incremented by 1? You have a few different ways here in C. We saw syntax like this, where you can say counter equals counter plus 1, which again feels like illogical. How can counter equal counter plus 1? But again, we read this code really right to left, updating its value by 1. In Python, it's almost the same. You just get rid of the semicolon. So that logic is there. But recall in C, we could do something slightly different that we can also do in Python. In Python, you can also more succinctly do this. Plus equals, and then whatever number you want to add, or you can even change it to subtract if you prefer. Sadly, gone is something you've probably typed a whole lot. What was the other way? You can add 1.
Plus plus.
Plus plus is no more, sadly, in Python. Just too many ways to do the same thing, so they got rid of it in favor of just this syntax here. So keep that in mind as well. What about loops? When you want to do something in Python again and again? Well, in Scratch, in week 0, here's how we meowed 3 times specifically. In C, we had a couple of ways of doing this. This was like the more mechanical approach where you create a variable called I, you set it equal to 0. You then do while I is less than 3, the following, and then you yourself increment I again and again. Mechanical in the sense that like you have to implement all of these gears and make them turn yourself, but this was a correct way to do that. In Python, we can still achieve the same idea. But we don't need the int keyword. We don't need any of the semicolons. We don't need the parentheses. We don't need the curly braces. We can't use the plus plus, so maybe that's a minor step backwards if you're a fan. But otherwise, the code, the logic is exactly the same. But there's other ways to achieve this same idea. Recall that in C, we could also do this. You could use a for loop, which it does exactly the same thing. Both are correct. Both are arguably well designed. It's kind of to each their own when it comes to choosing between these. In Python, though, we're going to have to think through how to do this. So you don't do the same for loop as in C. The closest I could come up with is this. where you say for I, or whatever variable you want to do the counting, in, literally, the preposition, and then you use square brackets here. And we've used square brackets before in the context of like arrays and things like that. And the 0, 1, 2 looks like an array in some sense, even though we've also seen arrays with curly braces. But these square brackets for now denote a list. Python does not have arrays. An array is that contiguous chunk of memory back to back to back that you have to resize somehow by moving things around in memory, as per 2 weeks ago. In Python, though, you can just create a list like this using square brackets. And better still, as we'll see, you can add or even remove things from that list down the road. This, though, is not going to be very well designed. This will work. This will iterate in Python 3 times. But what might rub you the wrong way?
Why are you guys so proud of not sleeping enough, huh? Does that make you feel stronger? Like, seriously, man.
Wrong way about this design, even if you've never.
No, like seriously, that's the problem, man. He said he's totally fine. Like he's proud that he's actually. We're just talking, okay? Why don't you guys talk in private then? Why are you guys chatting in my chat? Huh? Whose fault now, huh? You guys started the conversations. And then I accidentally overheard it. Then it's my fault, huh? He doesn't mean it, it's the proud way, just stating the fact. Okay then. But seriously though. Whatever.
Seen Python.
I'm just gonna leave you guys to your own business, I guess.
How does this example not end well? Yeah. Yeah, like if you're making a large list, you have to type out each one of these numbers, like comma 3, comma 4, comma 5, comma ... 50, comma ... 500. Like surely that's not the best solution to have all of these numbers on the screen wrapping endlessly on the screen. So in Python, another way to do this would be to use a function called range, which technically is a data type unto itself. And this returns to you as many values as you ask for it. Range takes some other arguments as well, but the simplest use case here is if you want back the numbers 0, 1, and 2, a total of 3 values, you say, hey, Python, please give me a range of 3 values. And by default, they start at 0 on up. But this is more efficient than it would be to hard code the entire list at once. And the best metaphor I could come up with is something like this. Like here, for instance, is a deck of cards. This is sort of normal human size. And there's presumably 52 cards here. So writing out 0 through 51 on code would be a little ridiculous for the reasons you note. It would just be very unwieldy and ugly and wrapping and all of that. It would be the virtual equivalent of me like handing you all of these cards at once to just deal with. And right, you know, they're not that big, but like it's a lot of cards to hold on to. It requires a lot of memory or physical storage, if you will. What range does metaphorically is if you ask me for 3 cards, I hand you them one at a time like this, so that at any point in time, you only have one number in the computer's memory until you're handed the next. The alternative, the previous version, would be to hand me all 3 cards at once or all 52 cards at once. But in this case, range is just way more efficient. You can do range of 1,000. That's not going to give you a list of 1,000 values all at once. It's going to give you 1,000 values one at a time, reducing memory significantly in the computer itself. All right, so besides this, what about doing something forever in Scratch? Well, we could do this literally with a forever block, which didn't quite exist in C. In C, we had to hack it together by saying while true, because true is by definition, TRUE, always true. So this just deliberately induces an infinite loop for us. In Python, the logic's going to be almost the same. And infinite loops in Python tend to actually be even more common, because you can always break out of them, as you could in C. In Python, it looks like this. And this is slightly more subtle, but gone are the curly braces, Gone are the parentheses, but ever so slight difference too. Capital T for true, and it's going to be a capital F for false. Stupid little differences. Eventually, you're going to mistype one or the other, but these are the kinds of things to keep an eye out and to start recognizing in your mind's eye when you read code. Questions now on any of these building blocks? Yeah? In the for loop was it was set to 0 on the first iteration, then 1 on the next, then 2 on the third. And the same thing for range, it just doesn't use up as much memory all at once. Other questions now on any of these building blocks of Python? No? All right, well, let's go ahead and build something a little more than hello. Let me propose that over here we implement maybe the simplest of calculators here. So let me go back to VS Code here, open my terminal window, and open up, say, a file called calculator.py. And in calculator.py, we'll have an opportunity to explore some of these building blocks, but we'll allow things to escalate pretty quickly to more interesting examples so that we can do the same thing ultimately as well. And in fact, let me go ahead and do this moreover. I've brought some code with me in advance. For instance, something called calculator 0.c from the first week of C. And let me go ahead and split my window here, in fact, so that I can now do something like this. Let me move this over here, calculator.py. So now I have on the left of my screen calculator.c, or calculator 0.c, because that's the first version I made, and calculator.py on the right. Let me go ahead and implement really the same idea here. So on the right-hand side, the analog of including cs50.h would be from cs50 import get int, if I want to indeed use this function. Now I'm going to go ahead and give myself a variable x without defining its type. I'm going to use this getInt function, and I'm going to prompt the user for x, just like in C. I'm then going to go ahead and prompt the user for another int, like y, here, just like in C. And at the very end, I'm going to go ahead and do print x plus y. And that's it. Now, granted, I have some comments in my C version of the code, just to remind you of what each line is doing. But I've still distilled this into like 6 lines, or really 4 if I get rid of the blank line. So it's already perhaps a bit tighter here. But there's also, it's tighter because something really important historically is missing. What did I say?
Get in.
Seem to omit altogether that we haven't really highlighted yet. Yeah, the main function is gone. And in fact, maybe you took for granted that it just worked a moment ago when I wrote hello, but I didn't have a main function in hello either. And this too is a feature of Python and a lot of other languages as well. Instead of having to adhere to these long-standing traditions, if you just want to write code and get something done, fine. Just write code and get something done without necessarily all of this same boilerplate. So whatever is in your Python file, left indented, if you will, by default, is just going to be the code that the interpreter runs top to bottom, left to right. Well, let me go ahead now and run code like this. Let me go ahead and open back up my terminal window, run Python of calculator.py, and I'll do x is 1, y is 2. And as you might expect, it gives me 3. Slight aesthetic bug. I put my space in the wrong place here, so that's a newbie mistake. Let me fix that aesthetically. Let me rerun Python of calculator.py, type in 1, type in 2, and voila, there is now my same version again. But let me propose now that we get rid of this training wheel. We don't want to keep taking 1 step forward and then 2 steps back by adding these training wheels. So let me instead do this. In my version of calculator.py, suppose that we take away already the training wheel that is the CS50 library here. And let me instead then use just Python's built-in function called input, which literally does just that. It gets input from the user. And it stores it, as before, in x and y. So this is not CS50 specific. This is real world Python programming. Well, let me go ahead and run again Python of calculator.py. And of course, if x is 1 and y is 2, x plus y should of course still be 3. It's apparently 12, according to Python, until CS50's library gets involved. But does anyone want to infer what just went wrong? Yeah. Exactly. The input function, by design, always returns a string of text. After all, that's what the human typed in. And even though, yes, I typed the number keys on the keyboard, it's still coming back as all text. Now, maybe we should use like a getInt function. Well, that doesn't exist in Python. All you can do is get text input, a string from the user, but we can convert one to the other. And so a fix for this, so that we don't accidentally concatenate, that is join x plus y together, would be to do something like this. Let me go back to my Python code here. And whereas in C, we could previously do typecasting. We could convert one type to another. That generally wasn't the case when you were doing something complex like a string to an int. You could do a char to an int and vice versa. But for a string, recall there was a special function in the C-type library called a to I, like ASCII to integer. That's that closest analog here. And in fact, the way to do this in Python would be to use a function called int, which indeed is the name of the data type too, even though I have not yet had to type it. And I can convert the output of the input function automatically from a string immediately to an int. And now, if I go back to my terminal window, rerun Python of calculator.py with 1 and 2 for x and y, now I'm back in business. So that then is for instance and 2 for x and y, now I'm back in business. So that then is, for instance, what the CS50 library does, if temporarily this week, is it just deals with the conversion for you. And in fact, bad things could happen if I type the wrong thing, like dog or cat instead of a number, but we'll cross that bridge in just a moment as well. All right, what if we do something slightly different now with our calculator? Instead of just addition, let me go ahead and do, how about, instead of addition, let's do division instead. So z equals x divided by y, thereby giving me a third variable z. Let me go ahead and run Python of calculator.py again. I'll type in 1, I'll type in 3 this time. And what problem do you think we're about to see? Or is it gone? What happened when I did this in C, albeit with some slightly more cryptic syntax? When I divided one number, like 1 divided by 3. Anyone recall? Yeah. Yeah, so it would round down to the nearest integer, whereby you experience truncation. So if you take an integer like 1, you divide it by another integer like 3, that technically should be 0.33333 infinitely long. But in C, recall, you truncate the value. If you divide an int by an int, you get back an int, which means you get only the integer part, which was the 0. Now, Python actually handles this for us and avoids the truncation, but it leaves us still with one other problem here, which is going to be, for instance, not necessarily visible at a glance. This looks correct. This has solved the problem in C, so truncation does not happen. The integers are automatically converted to a floating point value. But what other problem did we trip over back in week 1? What else got a little dicey when dealing with simple arithmetic? Anyone recall? Well, the syntax in Python's a little different, but let me go ahead and do this. It turns out in Python, if you want to see more significant digits than what I'm seeing here by default, which is a dozen or so, let me go ahead and print out z as follows. Let me first print out a format string, because I want to format z in an interesting way. And notice this would have no effect on the difference. This is just a format string that, for no compelling reason at the moment, is interpolating z in those curly braces using an f string or format string. If I run this again with 1 and 3, we'll see indeed the exact same thing. But when you use an f string, you indeed have the ability to format that string more precisely. Just like with %f in Python, you could start to fine-tune how many significant digits you see. In C, in Python, you can do the same, but the syntax is a little different. If you want the computer to interpolate z and show you 50 significant digits, that is 50 numbers after the decimal point, syntax is similar to C, but it's a little different. You literally put a colon after the variable's name. .50 means show me the decimal point and then 50 digits to the right. And the f just indicates, please treat this as a floating point value. So now if I rerun Python of calculator.py, divide 1 by 3, unfortunately, Python has not solved all of the world's problems for us. This, again, was an example of floating point imprecision. So that problem is still latent. So just because the world has advanced doesn't necessarily mean that all of our problems from C have gone away. There are solutions using third-party libraries for scientific calculations and the like, but out of the box, floating point imprecision is still an issue. Meanwhile, there was one other problem in C that we ran into involving numbers, and that was this, integer overflow. Recall that an integer in C only took up, what, like 32 bits typically, which meant you could count as high as 4 billion, or maybe if you're doing positive and negatives, as high as 2 billion. After which, weird things would happen. The number would go to 0 or negative, or just it would overflow or wrap back around. Well, wonderfully in Python, they did at least address this, whereby you can count as high as you want. And Python will just use more and more and more and more bits and bytes to store really big numbers, so integer overflow is not a thing. With that said, Python is limited to how many digits it will show you on the screen at once as a string, but mathematically, your math will be correct now. So we've taken a couple steps forward, one step sideways, but indeed, we've solved some of our problems here. All right, questions now. Overflow is not a thing. With that said, Python is limited to how many digits it will show you on the screen at once as a string, but mathematically, your math will be correct now. So we've taken a couple steps forward, one step sideways, but indeed, we've solved some of our problems here. All right, questions now on any of these examples thus far? Question. All right, well, how about another problem that we encountered in C? Let's revisit it here in Python as well. So let me go ahead and on the left-hand side here, let me open up a file called, say, compare. Let's see. How about a file called compare3.c on the left? And let me go ahead and create a new file on the right called compare.py. Because recall that bad things happened when we needed to compare two values in C. So on the left here is a reminder of what we once did in C, whereby if we want to compare values, we can get an int in C, stored in x, a getInt in C, stored in y. We then have our familiar conditional logic here, just printing out if x is less than y or not. Well, we can certainly do the same thing ultimately in Python by using some fairly familiar syntax. And let's just demonstrate this one quickly. Let me go over here too. I'll do from CS50 import getInt, even though I could do this instead with the input function itself. X equals getInt, and I'll prompt the user for that. Y equals getInt, and I'll prompt the user for that. After that, recall that I can say without parentheses, if x is less than y, then print out, without the f, x is less than y. Then I can go ahead and say else if x is greater than y, I can print out quote unquote x is greater than y. If you'd like to interject now, what did I screw up? Anyone? Yeah. elif, right? So elif x is greater than y, else, this part's the same, print x is equal to y. So there's not all that much there's no new logic going on here, but at least syntactically it's a little cleaner. Indeed, this program's only 11 lines long, albeit without any comments. Let me go ahead and run Python of compare.py. Let's see, is 1 less than 2? Indeed. Let's run it again. Is 2 less than 1? No, it's greater than. And let's lastly type in 1 and 1 twice. X is equal to y. So we've got a pretty side-by-side one-to-one conversion here. Let's do something a little more interesting than in C. How about I open instead something where we actually compared for a purpose? So if I open up from from earlier in the course, how about agree.c? Which prompt the user to agree to something or not. And let me code up a new version here called agree.py. And I'll do this on the right-hand side with agree.py. But on agree.c on the left, notice that this is how we did this sort of yes-no thing in C. We compared C, a character, equal to single quotes y, or equal to single quotes little y, and then the same thing for n. Now in Python, this one's actually going to be a little bit different here. Let me go ahead and in the Python version of this, let me do something like this. We'll use getString. Well, actually, no, we'll just use input in this case. So let's do s equals input, and we'll ask the user the same thing. Do you agree? Question mark. Then let's go ahead and say, if s equals, how about y? How do I do this? Well, a few things. Turns out I'm going to do this. S equals little y. Then I'm going to go ahead and print out agreed. And elif s equals capital N or s equals lowercase n, I'm going to go ahead and print out not agreed. And I claim for the moment that this is identical now to the program on the right, the program on the left in C. But what's different? So we're still doing the same kind of logic, these equals for comparing for equality. But notice that nicely enough, Python got rid of the two vertical bars, and it's just literally the word or. If you recall seeing ampersand, ampersand to express a logical and in C, you can just write literally the word and. And so here's a hint of why Python tends to be pretty popular. People just like that it's a little closer to English. There's a little less of the cryptic syntax here. Now, this is correct, as this code will now work, but I've also used double quotes instead of single quotes. And I also omitted a few minutes ago from my list of data types in Python the word char. In Python, there are no chars. There are no individual characters. If you want to manipulate an individual character, you use a string, that is to say a str of size 1. Now, in Python, you can use single quotes or double quotes. I'm deliberately using double quotes everywhere just for consistency with how we treat strings in C. It's pretty common, though, to use single quotes instead, if only because on most keyboards you don't have to hold the shift key anymore. I mean, humans have really started to optimize just how quickly they want to be able to code. So using a single quote tends to be pretty popular in Python and other languages as well. They are fundamentally the same, single or double, unlike in C where they have meaning. So this is correct, I claim. And in fact, let me run this real quick. I'll open up my terminal window here. Let me get rid of the version in C and run python of agree.py, and I'll type in y. OK, I'll run it again and type in little y, and I'll stipulate it's going to work for no as well. But this isn't necessarily the only way we can do this. There are other ways to implement the same idea. And in fact, I can go about doing this instead. Let me go back up to my code here. And we saw a hint of this earlier. We know that lists exist in Python, and you can create them just by using square brackets. So what if I simplify the code a little bit and just say if s is in the following list of values, capital Y or lowercase y. It's not all that different logically, but it's a little tighter. It's a little more compact. So L if s is in capital N or lowercase n, I can express that same idea too. So here again, it's just getting a little more pleasant to write code. There's less like hitting of the keyboard. You can express yourself a little more succinctly. And using the keyword in, Python will figure out how to search the entire list for whatever the value of s is. And if it finds it, it will return true automatically, else it will return false. So if I run agree.py again and type in capital Y or lowercase y, that still now works. Well, I can tighten this up further if I want to add more features. Well, what if I want to support not just y, big Y and little y, but how about yes, or in case the user's yelling, or someone who isn't good with caps lock types in yes. Wait a minute, but it could be weird. Like, do we want to support this? Or this? I mean, this just gets really tedious quickly, combinatorically, if you consider all of these possible permutations. What would be smarter than doing something like this if you want to just be able to tolerate yes in any form of capitalization? Like logically, what would be nice? Exactly. Super common paradigm. Why don't we just force the user's input to all lowercase or all uppercase? Doesn't matter so long as we're self-consistent, and just compare against all uppercase or all lowercase. And that will get rid of all of the possible permutations otherwise. Now in C, we might have done something like this. We might have simplified this whole list and just said, let's say, we'll do, how about lowercase? So Y or yes, and we'll just leave it at that. But we need to force now s to lowercase. Well, in C, we would have used the C-type library. We would have done like toLower and called that function, passing it in, although not really, because in C-type, those operate on individual characters or chars, not whole strings. We actually didn't see a function that could convert a whole string in C to lowercase. But in Python, we're going to benefit from some other feature as well. It turns out that Python supports what's called object-oriented programming. And we're only going to scratch the surface of this in CS50. But if you take a higher level course in programming or CS, you'll explore this as a different paradigm. Up until now in C, we've been focusing on what's called really procedural programming. You write procedures, you write functions, top to bottom, left to right. And when you want to change some value, we were in the habit of using a procedure. That is a function. You would pass something, like a variable, into a function, like to upper or to lower, and it would do its thing and hand you back a value. Well, it turns out that it would be nicer, programming-wise, if some data types just had built-in functionality. Like, why do we have our variables over here and all of our helper functions, like to upper and to lower over here, such that we constantly have to pass one into the other? It would be nice to sort of bake into our data types some built-in functionality so that you can change variables using their own default built-in functionality. And so object-oriented programming, otherwise known as OOP, is a technique whereby certain types of values, like a string, aka stir, not only have properties inside of them, attributes, just like a struct in C, your data can also have functions built into them as well. So whereas in C, which is not object-oriented, you have structs, and structs can only store data, like a name and a number when implementing a person. In Python, you can, for instance, have not just a structure, otherwise known as a class, storing a name and a number. You can have a function like call that person, or email that person, or actual verbs or actions associated with that piece of data. Now, in the context of strings, it turns out that strings come with a lot of useful functionality. And in fact, at this URL here, which is in docs.python.org, which is the official documentation for Python, you'll see a whole list of methods, that is, functions that come with strings that you can actually use to modify their values. And what I mean by this is the following. If we go through the documentation, poke around, it turns out that strings come with a function called lower. And if you want to use that function, you just have to use slightly different syntax than in C. You do not do to lower, and you do not say, as I just did, lower, because this function is built into S itself. And just like in C, when you want to go inside of a variable, like a structure, and access a piece of data inside of it, like name or number, when you also have functions built into data types, aka methods. A method is just a function that is built into a piece of data. You can do s dot lower, open paren, close paren in this case. And I can do this down here as well. If s dot lower in quote unquote n or no, the whole thing, I can force this whole thing to lowercase. So the only difference here now is in object-oriented programming, instead of constantly passing a value into a function, you just access a function that's inside of the value. It just works because of how the language itself is defined. And the only way you know whether these functions exist is the documentation, a class, a book, a website, or the like. Questions now on this technique? All right, I claim this is correct. Now, even though you've never programmed, most of you, in Python before, not super well designed. There's a subtle inefficiency now on lines 3 and 5 together. What's dumb about how I've used lower, might you think? Yeah. Yeah, if you're going to use the same function twice and ask the same question, expecting the same answer, why are you calling the function itself twice? Maybe we should just store the result in a variable. So we could do this in a couple of different ways. We, for instance, could go up here and create another variable called t and set that equal to s.lower, and then we could just change this to be t here. But honestly, I don't think we technically need another variable altogether here. I could just do something like this. Let's change the value of s to be the lowercase version thereof. And so now I can quite simply refer to s again and again like this, reusing that same value. Now, to be sure, I have now just lost the user's original input. And if I care about that, if they typed in all caps, I have no idea anymore. So maybe I do want to use a separate variable altogether. But a takeaway here, too, is that strings in Python are technically what we'll call immutable. That is, they cannot be changed. This was not true in C. Once we gave you arrays in week 2 or memory in week 4, you could go to town on a string and change any of the characters you want, uppercasing, lowercasing, changing it, shortening it, and so forth. But in this case, this returns a copy of s forced to lowercase, it doesn't change the original string that is the memory, the bytes in the computer's memory. When you assign it back to S, you're essentially forgetting about the old version of S. But because Python does memory management for you, there's no malloc, there's no free, Python automatically frees up the original bytes, like YES, and hands them back to the operating system for you. All right, questions now on this technique. Questions on this. In general, I'll call out the Python documentation will start to be your friend, because in class we'll only scratch the surface with some of these things, but in docs.python.org, for instance, there's a whole reference of all of the built-in functions that come with the language, as well as, for instance, those with the string. All right, well, let me go ahead and, before we take a break, let's go ahead and create something a little familiar too, based on our weeks here in C. Let me propose that we revisit those examples involving some meow. So for instance, when we had our cat meow back in the first week and then second in C, we did something that was a little stupid at first, whereby we created a file, as I'll do here, this time called meow.py. And if I want a cat to meow 3 times, I can run it once like this, little copy paste, and now Python of meow.py, and I'm done. Now, we've visited this example like 2 times at least now in Scratch and in C. It's correct, I'll stipulate, but what's obviously poorly designed? What's the fault here? Yeah. It should just be a loop, right? Like, why type it 3 times? Literally copying and pasting is almost always a bad thing, except in C when you have the function prototypes that you need to borrow. But in this case, this is just inefficient. So what could we do better here in Python? Well, in Python, we could probably change this in a few different ways. We could borrow some of the syntax we proposed in slide form earlier, like give me a variable called I, set it to 0, no semicolon, while I is less than 3. If I want to do this 3 times, I can go ahead and print out meow, and then I can do I plus equals 1. And I think this would do the trick.
Hello, Lego Scratch.
And we're back in business already. Well, if I wanted to change this to a for loop, well,
I have no idea why you say
Python, it would be a little tighter, but this would not be the best approach. So for I in 0, 1, 2, I could just do print meow. Like,
just Lego would okay.
like this, and that too would get the job done. But to our discussion earlier, this would get stupid pretty quickly if you had to keep enumerating all of these values. Like, what did we introduce instead? The range function, exactly. So that hands me back way more efficiently just the values I want, indeed 1 at a time. So even this, if I run it a third or fourth time, we've got the same result. But now let's transition to where we went with this back in the day. How can we start to modularize this? Like, just like it would be nice, I claimed, if MIT had given us a meow function, wouldn't it be nice if, like, Python had given us a meow function? Maybe less compelling in Python, but how can I build my own function? Well, I did this briefly with the spell checker earlier, but let me go ahead and propose that we could implement now our own version of this in Python as follows. Let me go ahead and start fresh here and use the keyword def. So this did not exist in C. You had the return value, the function name, the arguments. In Python, you literally say def to define a function. You give it a name like meow. And now I'm going to go ahead and in this function just print out meow. And this lets me change it to anything else I want in the future. But for now, it's an abstraction. And in fact, I can move it out of sight, out of mind. Just going to hit enter a bunch of times to pretend like now it exists, but I don't care how it is implemented. And up here now I can do something like this. For I in range of 3, let me go ahead and not print meow anymore. Let me just call meow, and tightening up my code further. But I think, let's see, Python of meow.py, this is, I think, going to be the first time it does not work correctly. OK, so here we have, sadly, our first Python error.
No, not recursion yet. This is not recursion yet. The syntax is going to be different
from C, or Clang's output. Traceback is like the term of art here. This is like
recursion is when you use a function inside of itself, so to speak. I don't know, but this is just reusing the same function. It doesn't, so it's not like the function is using itself inside of itself, you know. So it's not recursion.
Trace back of all of the lines of code that were just executed, or really functions you called. The file name is uninteresting. This is like my code space specifically, but the file name is important here, meow.py. Line 2 is the issue. OK, I didn't get very far before I screwed up. And then there's a name error. And you'll see in Python, there's typically these capitalized keywords that hint at what the issue is. It's something related to names of variables. Meow is not defined. All right, you're programming Python for the first time. You've screwed up. You're following some online tutorial. You're seeing this. Reason through it. Like, why might meow not be defined? What can we infer about Python? How to troubleshoot logically. Maybe, is it because meow is defined after? You know, as smart as Python seems to be vis-a-vis C, they have some similar design characteristics. So let's try that. So let me scroll all the way back down to where I moved this earlier. Let me get rid of it way down there. I'll copy it to my clipboard. And let me just kind of hack something together. Let me just put it up here. And let's see if this works. So now, let me clear my terminal, run Python of meow.py. OK, we're back in business. So that was actually really good intuition, good debugging technique to sort of reason through it. Now, this is kind of contradicting what I claimed back in week 1, which was that, you know, the main part of your program, ideally, should just be at the top of the file. Like, don't make me look for it. It's not a huge deal with like a 4-line program. But if you've got 40 lines, 400 lines, you don't want like the juicy part of your program to be way down here and all of these functions way up here. So it would be nice, maybe if we actually have a
Today, stopper, yeah, but that's what the recursion supposed to do.
main function. And so it actually turns out to be a convention in Python to define a main function. It's not a special function that's automatically called like in C, but humans realized, you know what, that was a pretty useful feature. Let me define a function called main. Let me indent these lines underneath it. Let me practice what I'm preaching, which is put the main code at the top of the file. And wonderfully in Python now, you do not need prototypes. There's none of that hackish copying and pasting of the return type, the name, and the arguments to a function like we needed in C. This is now OK instead, except for one minor detail. Let me go ahead and run Python of meow.py. Hopefully now I've solved this problem by having a main function, but now nothing has happened. All right, even if you've never programmed in Python before, what might explain this behavior?
What? Def main. Nothing is calling main.
And how do I fix? Again, when you're off in the real world learning some new language, all you have is deductive logic to debug. Yeah. Right, so the solution, to be clear, in C was that we had to put the prototype up here, otherwise we'd get an error message. In this case, I'm actually not getting an error message, and indeed I'll claim that you don't need the prototypes in Python, just not necessary, because that was annoying, if nothing else. But what else might explain? Yeah, and back?
Hey, no.
Yeah, maybe you have to call main itself. If main is not some special status in Python, maybe just because it exists isn't enough. And indeed, if you want to call main, the new convention is actually going to be, as the very last line of your program typically, to literally call main. It's a little stupid looking, but you know, they made a design decision, and this is how now we work around it. Python of meow.py, now we're back in business. But now logically, why does this work the way it does? Well, in this case, top to bottom, line 1 is telling Python to define a function called main, and then define it as follows, lines 2 and 3. But it's not calling main yet. Line 6 is telling Python how to define a function called meow, but it's not calling these lines yet. Now, on line 10, you're telling Python call main. And at that point, Python has been trained, if you will, to know what main is on line 1, to know what meow is on line 6. And so it's now perfectly OK for main to be above meow, because you never called them yet. You defined, and then you called. And that's the logic behind this. Any questions now on the structure of this technique here? Now let's do one more then. Recall that the last thing we did in Scratch and in Python, Scratch and in C, was to actually parameterize these same functions. So suppose that you don't want main to be responsible for the loop here. You instead want to very simply do something like meow 3 times and be done with it. Well, in Python, it's going to be similar in spirit to C, but again, we don't need to keep mentioning data types. If you want meow to take some argument, like a number, n, you can just specify n as the name of that argument. Or you could call it anything else, of course, that you want. You don't have to specify int or anything else. In your code now, inside of meow, you can do something like for I in let's say I definitely now can't do this, because like that would be weird to start the list and end it with n. So if I can come back over here, what's the solution? How can I do something n times?
Why are there all these?
Yeah, using range. So range is nice because I can pass in now this variable n, and now I can meow, whoops, now I can print out, quote unquote, meow. So it's almost the same as in Scratch, almost the same as in C, but it's a little simpler. And if now I run meow.py, I'll have the ability now to do this here as well. All right, questions on any of this? Right now, we're sort of like taking the stroll through week 1. We're going to momentarily escalate things to look not only at some of these basics, but also other features like we saw with face recognition, with the speller or the like. Because of how many of us are here, we have a huge amount of candy out in the lobby. So why don't we go ahead and take a 10-minute break, and when we come back, we'll do even fancier, more powerful things with Python in 10. All right, so we are back. Among our goals now are to introduce a few more building blocks so that we can solve more interesting problems at the end, much like those that we began with. You'll recall from a few weeks ago, we played with this sort of two-dimensional Super Mario world, and we tried to print a vertical column of like 3 or more bricks. Well, let me propose that we use this as an opportunity to now tinker with some of Python's more useful, more user-friendly functionality as well. So let me code a file called mario.py, and let's just print out like that, the equivalent of that vertical column. So it's of height 3, each one is a hash. So let's do for I in range of 3 initially, and let's just print out a single hash. And I think now, Python of mario.py, voila, we're in business, printing out just that same pyramid there, or just that same column there. What if, though, we want to print a column of like some variable height where the user tells us how tall they want it to be? Well, let me go up here, for instance, and instead, how about we'll use, let's do this. How about from CS50 import, how about the getInt function as before? So it will deal with making sure the user gives us an integer. And now, in the past, whenever we wanted to get a number from a user, we've actually followed a certain paradigm. In fact, if I open up here, for instance, how about Mario 1.c from a while back? You might recall that we had code like this. And we specifically use the do while loop in C whenever we want to like get something from the user, maybe again and again and again until they cooperate, at which point we finally break out of the loop. So it turns out Python does have while loops, does have for loops, does not have do while loops. And yet pretty much any time you've gotten user input, you've probably used this paradigm. So it turns out that the Python equivalent of this is to do similar in spirit, but using only a while loop. And a common paradigm in Python, as I alluded earlier, is to actually deliberately induce an infinite loop, while true, capital T, and then do what you want to do, like get an int from the user, and prompt them for the height, for instance, in question. And then, if you're sure that the user has given you what you want, like n is greater than 0, which is what I want in this case because I want a positive integer, otherwise there's nothing to print, you literally just break out of the loop. And so we could actually use this technique in C. It's just not really done in C. You could absolutely in C have done a while true loop with the parentheses, lowercase true. You could break out of it and so forth. But in Python, this is like the Python way. And this is actually a term of art. This way in Python is Pythonic. Like this is the way everyone does it, quote unquote. Doesn't mean you have to, but that's sort of the way like the cool Python programmers would implement an idea like this, trying to do something again and again and again until the user actually cooperates. But all we've done is take away the do while loop, but still logically we can implement the same idea. Now below this, let me go ahead and just print out for I in range of n this time, because I want it to be variable and not 3. I can go ahead and print out the hash. Let me go ahead and get rid of the C version here, open my terminal window, and I'll run again Python of mario.py. I'll type in 3, and I get back those 3 hashes. But if I instead type in 4, I now get 4 hashes instead. So the takeaway here is quite simply that this would be the way, for instance, to actually get back a value in Python that is consistent with some parameter, like greater than 0. How about this? Let's actually practice what we preached a moment ago with our meowing examples. and kind of factoring all this out, let me go ahead and define a main function as before. Let me go ahead and assume for the moment that a getHeight function exists, which is not a thing in Python. I'm going to invent it in just a moment. And now I'm going to go ahead and do something like this. For I in the range of that height, well, let's go ahead and print out those hashes. So I'm assuming that getHeight exists. Let me go ahead and implement that abstraction. So define a function now called getHeight. Not going to take any arguments in this design. While true, I can go ahead and do the same thing as before. Assign a variable n, the return value of getInt, prompting the user for that height. And then if n is greater than 0, I can go ahead and break. But if I break here, I logically, just like in C, end up executing below the loop in question, but there's nothing there. But if I want getHeight to return the height, what should I type here on line 14 logically?
Return?
What do I want to return?
Return, just basically return.
Yeah, so I actually want to return n. And here's another curiosity of Python vis-a-vis C. There doesn't seem to be an issue of scope anymore, right? In C, it was super important to not only declare your variables with the data types, you also had to be mindful of like where they exist inside of those curly braces. In Python, it turns out you can be a little looser with things, for better or for worse. And so on line 11, if I create a variable called n, it exists on line 11, 12, and even 13 outside of the while loop. So to be clear, in C with a while loop, we would have ordinarily had not a colon, we would have had the curly brace like here and over here. And a week ago, I would have claimed that in C, n does not exist outside of the while loop by nature of those curly braces. Even though the curly braces are gone, Python actually allows you to use a variable anytime after you have assigned it a value. So slightly more powerful as such. However, I can tighten this up a little bit. Logically, and this is true in C, I don't really need to break out of the loop by using break. Recall that or know that I can actually, once I'm ready to go, I can just return the value I care about even inside of the loop. And that will have the side effect of breaking me out of the loop and also breaking me out of and returning from the entire function. So nothing too new here in terms of C versus Python except for this issue of scope. And I indeed returned n at the bottom there just to make clear that n would still exist. So either of those are correct. Now I just have a Python program that I think is going to allow me to implement this same Mario idea. So let's run Python of Mario.py and OK, so nothing happened. Python of Mario.py. What did I do wrong? Yeah, I have to call main. So at the bottom of my code, I have to call main here. And this is a stylistic detail that's been subtle. Generally speaking, when you are writing in Python, there's not a CS50 style guide per se. There's actually a Python style guide that most people adhere to. And in this case, double blank lines between functions is the norm. I'm doing that deliberately, although it might otherwise not be obvious. But now that I've called main on line 16, let's run Mario.py once more. Aha! Now we get there. Now we see it. Type in 3, and I'm back in business, printing out the values there. Yeah. Sure, why do I need the if condition at all? Why can't I just return n here as by doing return n? Or if I really want to be succinct, I could technically just do this. The only reason I added the if condition is because if the user types in -1, -2, I wanted to prompt them again and again. That's all. But that would be totally acceptable too if you were OK with that result instead. Well, let me do one other thing here to point out why we are using getInt so frequently, this new training wheel, albeit temporarily. So let me go back to the way it was a moment ago. And let me propose now to take away getInt. I claimed earlier that if you're not using getInt, you can just use the input function itself from Python. But that always returns a string or a str. And so recall that you have to pass the output of the input function to an int, either on the same line or, if you prefer, on another line instead. But it turns out what I didn't do was show you what happens if you don't cooperate with the user, with the program. So if I run Python of Mario.py now, works great, even without the getInt function. And I can do it with 4. Still works great. But let me clear my terminal and be difficult now as the user and type in cat for the height instead. Enter. now we see one of those tracebacks again. This one is different. This isn't a name error, but apparently a value error. And if I kind of ignore the stuff I don't understand, I can see invalid literal for int with base 10 cat. That's a super cryptic way of saying that CAT is not a number in decimal notation. And so I would seem to have to somehow handle this case. And if you want to be more curious, you'll see that this is indeed a trace back. And C tends to do this too, or the debugger would do this for you too. You can see all of the functions that have been called to get you to this point. So apparently my problem is initially in line 14, but line 14, if I keep scrolling, is uninteresting. It's main. But line 14 leads me to execute line 2, which is indeed in main. That leads me to execute line 9, which is in get height. And so, OK, here's the issue. So the closest line number to the error message is the one that probably reveals the most. Line 9 is where my issue is. So I can't just blindly ask the user for input and then convert it to an int if they're not going to give me an int. Now, how do we deal with this? Well, back in problem set 2, you might recall validating that the user typed in a number and using a for loop and the like. Well, it turns out there's a better way to do this in Python, and the semantics are kind of there. If you want to try to convert something for a number to a number that might not actually be a number, turns out Python and certain other languages literally have a keyword called try. And if only this existed for the past few weeks, I know, but like you can try to do the following with your code. What do I want to try to do? Well, I want to try to execute those few lines, except if there's an error. So I can say except if there's a value error, specifically the one I screwed up and created a moment ago. And if there is a value error, I can print out an informative message to the user like not an integer or anything else. And what's happening here now is literally this operative word try. The Python is going to try to get input and try to convert it to an int. And it's going to try to check if it's greater than 0 and then try to return it. Why? All of 3 of those lines are indented underneath the try block. Except if something goes wrong, specifically a value error happens, then it prints this. But it doesn't return anything. And because I'm in a loop, that means it's going to do it again and again and again until the human actually cooperates and gives me an actual number. And so this too is what the user would call cooperate. That means it's going to do it again and again and again until the human actually cooperates and gives me an actual number. And so this too is what the world would call Pythonic. In Python, you don't necessarily rigorously try to validate the user's input, make sure they haven't screwed up. You honestly take a more lackadaisical approach and just try to do something, but catch an error if it happens. So catch is also a term of art, even though it's not a keyword here. Except if something happens, you handle it. So you try and you handle it. So you sort of best effort programming, if you will, but this is baked into the mindset of the Python programming community. So now if I do Python of Mario.py and I cooperate, works great as before. Try and succeed. 3 works, 4 works. If, though, I try and fail by typing in cat, it doesn't crash, per se. It doesn't show me an error. It shows me something more user-friendly, like not an integer. And then I can try again with dog. Not an integer. I can try again with 5. And now it works. So we won't generally have you write much in the way of these try except blocks, only because they get a little sophisticated quickly, but that is to reveal what the getInt function is doing. This is why we give you the training wheels, so that when you want to get an int, you don't have to jump through all these annoying hoops to do so, but that's all the library is really doing for you, is just try and accept. You won't be left with any training wheels ultimately. Questions now on getting inputs and trying in this way? Anything at all? Yeah? It say that, oh, could you put the condition outside of the try block? Short answer, yes. And in fact, I struggled with this last night when tweaking this example to show the simplest version. I will disclaim that really, I should only be trying, literally, to do the fragile part. And then down here, I should be really doing what you're proposing, which is do the condition out here. The problem is, though, that logically this gets messy quickly, right? Because except if there's a value error, I want to print out not an integer. I can't compare n against 0 then, because n doesn't exist because there was an error. So it turns out, and I'll show you this, this is now the advanced version of Python, there's actually an else keyword you can use in Python that does not accompany if or elif. it accompanies try and except, which I think is weirdly confusing. A different word would have been better. But if you really prefer, I could have done this instead. And this is one of these design things where like reasonable people will disagree. Generally speaking, you should only try to do the one line that might very well fail. But honestly, this looks kind of stupid now. It's just unnecessarily complicated. And so my own preference was actually the original, which was, yeah, I'm trying a few extra lines that really aren't going to fail mathematically, but it's just tighter. It's cleaner this way. And here's, again, the sort of like, arguments you'll start to make yourself as you get more comfortable with programming. You'll have an opinion. You'll disagree with someone. And so long as you can back your argument up, it's pretty reasonable, probably. All right, so how about we now take away some piece of magic that's been here for a while. Let me go ahead and delete all of this here. And let me propose that we revisit not that vertical column and the exceptions that might result from getting input, but these like horizontal question marks that we saw a while ago. So I want all of those question marks on the same line. And yet I worry we're about to see a challenge here because print up until now has been putting new lines every
With one piece is left for the drawer. Congrats on not using AI and give it
where I worry we're about to see.
It's something about drawing is different than AI, you know?
We saw a while ago. So I want all of those might result from proposed magic that's been here for a while. Let me go ahead and delete all of this. Agree with someone, and so long as you can back your argument up, pretty reasonable, probably. All right, so how about we now take away some piece of magic that's been here for a while. Let me go ahead and delete all of this here. And let me propose that we revisit not that vertical column and the exceptions that might result from getting input, but these like horizontal question marks that we saw a while ago. So I want all of those question marks on the same line. And yet I worry we're about to see a challenge here because print up until now has been putting new lines everywhere automatically, even without those \n's. Well, let me propose that we do this. For I in the range of 4, if I want 4 question marks, let me just print 4 question marks. Unfortunately, I don't think this is correct yet. Let me run Python of Mario.py, and of course this gives me a column instead of the row of question marks that I want. So how do we do this? Well, it turns out if you read the documentation for the print function, it turns out that print, not surprisingly perhaps, takes a lot of different arguments as well. And in fact, if you go to the documentation for it, you'll see that it takes not just positional arguments, that is from left to right, separated by commas. Turns out Python supports a fancier feature with arguments where you can pass the names of arguments to functions too. So what do I mean by this? If I go back to VS Code here, and I've read the documentation, it turns out that yes, as before, you can pass multiple arguments to Python like this, like hello, comma, David, comma, Malin. That will just automatically concatenate all 3 of those positional arguments together. They're positional in the sense that they literally flow from left to right, separated by commas. But if you don't want to just pass in values like that, you want to actually print out, as I did before, a question mark. But you want to override the default behavior of print by changing the line ending. You can actually do this. You can use the name of an argument that you know exists from the documentation and set it equal to some alternative value. And in fact, even though this looks cryptic, this is how I would override the end of each line to be quote unquote, that is nothing. Because if you read the documentation, the default value for this end argument, does someone want to guess, is \n. So if you read the documentation, you'll see that \n is the implied default for this end argument. And so if you want to change it, you just say end equals something else. And so here, I can change it to nothing and now rerun Python of Mario.py. And now they're all on the same line. Now it looks a little stupid because I made that sort of week 1 mistake where I still need to move the cursor to the next line. That's just a different problem. I'm just going to go over here and print nothing. I don't even need to print \n because if print automatically gives you a \n, just call print with nothing and you'll get that for free. So let me rerun Python of Mario.py and now it looks a little prettier at the prompt. And to be super clear as to what's going on, suppose I want to sort of make an exclamation here. I could change the \n default to like an exclamation point just for kicks. And if I run Python of Mario.py again, now I get this sort of, exclamation with question marks and exclamation points as well. So that's all that's going on here. And this is what's called a named argument. It literally has a name that you can specify when calling it in. And it's different from positional in that you're literally using the name. Let me propose something else though, and this is why people kind of like Python. There's just kind of cool ways to do things. That's kind of a, you know, that's a three-line verbose way of printing out 4 question marks. You know, I could certainly take the, you know, shortcut and just do this, but that's not really that interesting for anyone, especially if I want to do it a variable number of times. But Python does let you do this. If you want to multiply a character some number of times, not only can you use plus for concatenation, you can use star or an asterisk for multiplication, if you will. That is concatenation again and again and again. So if I just print out quote unquote question mark times 4, that's actually going to be the tightest way, the most succinct way I can print 4 question marks instead. And if I don't use 4, I use n, where I get n from the user. Bang, like now I've gotten rid of the for loop entirely, and I'm using the star operator to manipulate it instead. And to be super clear here, insofar as Python does not have malloc or free or memory management that you have to do, guess what Python also doesn't have? Anything or question marks instead. And if I don't use 4, I use n, where that's kind of a, you know, it's a 3-line verbose way of printing out 4 question marks. Interesting. If you want to use plus for multiplication, if you will, that is, I can print 4. Now I've gotten rid of the for loop entirely. Manipulate free, which just means that all of that happens for you automatically underneath the hood. It's about 3 by 3, a grid of bricks. Do this in Python, we can do this in a couple of ways now. Let me go back to my mario.py and let me do something like for I in range of, we'll just do
Alright, people. So I guess that's it for now. The animation is unfinished, of course, because the first part of the animation is pretty complex. Here, let me show you again. So the beginning of the animation is pretty complex. That's why it took me so long to do. And also I was learning computer science too, so it takes a while for me to actually finish this. So basically, I mean, I can try to add in some more cool stuff here, like a little bit of more light, airbrush, soft, a little bit. So if the light coming from this, I can try this, you know, add light there. Light here, add light here. From the back, I'm just gonna do it like this. From below, from the front. Oh, from the I don't think there's much we can do from the front. This is from the top, bottom, top, and the front. Front, I can try to add in like the back, like oops. Oh man, yeah, that's the problem. I need to map it out. I mean, mask it out. You know what I mean? It won't be too big of a deal. Oh wait, what? Oh, wrong one. So basically we just do this. You know, and then we add in the shadow of this woman here. Oops. Wait, what the? Something like this. And then we're going to get this. A little bit of that. Something like that. It's like people taking snapshots of you. It's like people taking pictures of you. And then I need to come up with like cool poses so she can do it. So she can do cool poses while like cameras are slow-mo and stuff. It's just quick flashes. Yeah, I don't know what kind of cool pose I can do. I can go up here, Pinterest, you know. Let's see. Oh, I have to sign in. Oh gosh. Oh gosh, I forgot to sign. Oh wait, I cannot show you guys. Of course not. Dance. Oh, I have to sign in all over again now. Try another way. Tap yes. Use passkey. Continue. Turn on window hello. Oh. Try another way. Tap yes on device recording. Tap yes on phone or tablet would be the fastest way. What you gonna do knowing my Gmail anyway, you know? What you gonna do? You gonna send me virus? Oh my gosh, that would be bad. Just don't do it, guys. For the sake of my safety. Okay, so we got this. Good. Now we're just going
it
to...
is indeed the seesaw back.
Then we're just gonna need to get this working. And then this too. Keep me locked in. And I think we're good to go. Anyway, now we got... We can try some cool poses, not these though, but like some cool poses like this. And then we do like lighting again. So it's gonna take forever. But hey, it's worth it, people. It's worth it. But it's gonna take forever. I mean, take a while, a great while to deal with all of these. Gosh, all these stuff so cool, right? And then, you know, and then, oh wait. Okay, so for example, a pose like this, right? And then it would go like okay. Okay, pose like this. The light will go like this too. But then, okay, before flashing like this, it will go like Make her spin would be like the worst thing to making her spin would be the worst nightmare, you know. I mean, I can try, but still, it's going to be crazy hard. Okay, and then the light will shift slowly, and then before moving on to the pose, it's going to like this, you know, the same thing, flash, and then move on to the next pose. I don't know how long the video would take, but it's only like for. Yeah, that could be the length, you know, but like. Oh, there's a lot of cool ideas, you know, but I might be starting a trend, who knows. Okay, I will never start a trend, guys. Hopefully, but you know, it's okay to dream. Imagine this got trendy and then people start making their own versions. Okay, let's start. Okay, that's enough. Okay, thank you guys for watching. I'll continue tonight doing it by myself. Of course, not gonna stream because, like I said, I'm gonna play some Zelda Zone Zero too. That would be good, yeah, hopefully. But yeah, thank you guys for watching. The stream is rather boring because, like I said, I'm not going to stream that frequently anymore. I'm just gonna stream on Saturday and Sunday, and that's it. I'm going to university soon. It's gonna be freaking hard, but hey guys, I learned computer science. The reason why I like to go for computer science is because, hey man, I like creating stuff. As you can see, I showed you my my channel here. What the heck are these? Like this, shorts? No, not shorts. Video games, okay. Not video games, but like I like creating stuff, games, something people can try play. So that's why I learned computer science. I like not just games, but like programs that people use to benefit them. For example, I always wanted a program that I can try, like, I don't know, like I like making a program that would like make it easier for everyone to like animate, you know, like 3D characters, but like in anime style. Currently there's no program that do that except for like Miku Miku Dance or like other complex stuff, but like Miku Miku Dance is very complex. You have to import file. You still have to get your own Blender, you know, model. But like I make like an engine, make an AI. Damn, that would be another subject. I tried going for AI. I don't know, like AI. There's a lot of way you can define AI, like generative AI or like machine learning AI. It's a lot of AI types, and it depends on how you use it too. But like, but yeah. Anyway, thank you guys for watching. I'll see you next week, hopefully, or somewhere in like. I don't know how long it would take me to finish this video, but anyway, thank you guys for watching. I'll see you later. Can you do your crying sound before I go? Okay. It goes like that cooks for you? No. I mean, it would work, but like, I mean, it's alright. Like, I don't know. AI making. Oh no, that won't work. Because I'm trying to make like a program that you can express your creativity, okay? Not AI. Okay, as an artist, it's not like I'm throwing hate on AI. AI can create some cool stuff, you know, like video. There's a lot of like AI memes videos. Yeah, I mean, whatever. But artistically speaking, it's about human emotions, you know. The reason why most AI art looks pale, and not pale, but like bland, it looks boring. It's not because it's not good, you know, but it's because it's lack the story behind, you know. No spirit. Yeah, it's something like that. It lacks intention. Yeah, I mean, they not suck in particular in quality. In terms of quality, some of the AI are very good. The details are immaculate. I don't know what the word is, but like the details on some AI drawing AI, it's very good, and I like it for that. But it lacks intention and, like you said, spirit, or some people say soulless. You know, it lacks emotion, expressiveness, and overall creativity. You know. But it's not bad at all. It's not like bad, like, oh, it's not supposed to be exist, but it's just people keep like saying that. Okay, people keep defining AI drawings real art, and that is why people are angry. You know, it is art, but it's AI art, and AI art stand in its own categories. Okay, it's like having an eye without people. No. Oh, Barry's back. Barry's okay. AI is like Okay, let me find an analogy comparing between human art and AI art. Okay, so you can imagine. Okay, how do I? Okay, maybe there's no analogy. This is quite new, so I don't know. Something's missing in AI art. Yeah, like I said, it's missing intention. You crying, but you ha ha ha. Anyway, guys, thank you guys for watching the stream. I will come back to you guys next week, or probably somewhere in I don't know, but like I only streams in the weekend, so yeah, have a nice weekend, guys. Nice Sunday. It's currently Sunday for me. Hello, Silver Comet, and bye bye, I guess. Well, hope you guys had a great time watching my streams. It's 6 hours. I don't know what is scratching my face. I don't know how I slept last night, but I have like a freaking scratch on my face. I don't know how to fix it, but anyway, goodbye, guys. See you guys in the next stream, which is next week. Yeah, have a nice next week, guys. Okay, goodbye. Bye bye.